The promise of artificial intelligence often shines brightest in research notebooks and controlled experiments. Yet, when these systems are moved into production environments, reality is far harsher. Many sophisticated models never make it beyond prototypes, and those that do often degrade rapidly once exposed to real world data. Failures are complex, arising from both technical flaws and organizational shortcomings. Unlike static software, AI is deeply dependent on data distributions that are constantly shifting. As those distributions evolve, models lose their predictive power. Understanding why AI systems fail is not about pessimism, it's about preparation. By studying the failure modes, organizations can build resilience and prevent small cracks from becoming catastrophic breakdowns. The journey from notebook to production is fraught with obstacles. There is a deployment gap. Many well designed models simply never make it into production systems. Of those that do, rapid degradation is common. Performance declines within weeks or months as training assumptions no longer match reality. Failure modes are complex, combining infrastructure bottlenecks, data quality issues, and organizational misalignments. At the root lies the fact that AI is not static. Traditional software continues working until broken by code errors, but AI performance is hostage to constantly changing data. This dynamic nature means failure is not a possibility, it is a certainty unless teams anticipate and mitigate it. The majority of AI failures trace back to data. Distribution drift occurs when real world data shifts away from the training distribution, leaving models poorly calibrated. Quality degradation arises from missing values, corrupted logs, or inconsistent formatting that poison inputs. Label errors creep in when ground truth is weak, feedback loops are noisy, or human labeling is inconsistent. Finally, pipeline breakages occur when upstream schema changes or ETL modifications disrupt established flows, rendering models useless overnight. Data is the oxygen AI depends on, and when it becomes contaminated or unstable, the entire system falters. Even with good data, models themselves are vulnerable. Overfitting is a classic problem. Models that perform brilliantly on training data fail to generalize in production. Bias amplification turns subtle patterns in training data into magnified unfairness when deployed at scale, undermining trust. Inadequate retraining leaves models stale, as infrequent updates fail to capture evolving realities. Model staleness compounds this, as the world changes faster than the retraining schedule. The result is widening divergence between model predictions and reality. Models that once seemed cutting edge quickly become liabilities if not maintained diligently. Even the best models fail if the infrastructure cannot support them. Processing bottlenecks arise when GPU or CPU resources are insufficient, causing slow inference, missed service level agreements, and throttled throughput. Latency issues occur when storage or network delays plague distributed training, leading to extended development cycles. Container misconfigurations, such as poorly tuned Kubernetes clusters or Docker images, can starve workloads of resources. Cost explosions happen when auto-scaling misfires, generating cloud bills that spiral into tens of thousands of dollars overnight. Infrastructure must be tuned not just for peak performance, but also for resilience and efficiency, or it becomes the Achilles heel of the entire deployment. You can't fix what you can't see. This phrase captures the essence of monitoring failures. Many AI systems lack tracked metrics for latency, error rates, or drift indicators, leaving teams blind to deterioration. Absent alerting means issues are often discovered not by engineers, but by frustrated end users. Traceability deficits arise when there is no request tracking across components, prolonging root cause analysis and downtime. Finally, inadequate dashboards leave operations teams without a clear view of system health. Observability is the foundation of reliability, and without it, organizations operate blindfolded, reacting too late to prevent damage. Production failures are not always accidental. Sometimes they are deliberate attacks. Exposed endpoints invite abuse, model extraction, or theft of intellectual property. Secret leakage occurs when credentials or API keys are accidentally committed to repositories or embedded in containers, giving attackers easy access. Regulatory violations surface when AI systems fail to comply with frameworks like GDPR or HIPAA, leading to fines and service shutdowns. And adversarial attacks, in which carefully crafted inputs cause misclassifications, erode user trust, and sometimes cause real-world safety incidents. Security and compliance cannot be afterthoughts. They must be embedded into the DNA of AI infrastructure. Not all failures are technical. Often, the deeper cause is organizational. Siloed teams create misalignment between data scientists and operations engineers, producing models that succeed in labs but fail in production. Ownership gaps emerge when no one is accountable for retraining pipelines, leaving models to drift unmanaged. Missing playbooks extend downtime because there are no documented incident response procedures. Finally, expectation management failures occur when stakeholders are promised capabilities that AI systems cannot sustain, leading to trust collapse. Culture and governance matter as much as algorithms and hardware. Without alignment, even technically sound systems stumble. Real-world failures underscore the stakes. In fraud detection, undetected drift allowed criminals to exploit new patterns, resulting in losses exceeding $2.3 million before detection. A customer support chatbot became irrelevant as evolving slang and terminology outpaced its training, driving 28% churn in key customer segments. A healthcare diagnostic tool was shut down immediately by regulators when missing audit logs made its clinical recommendations unverifiable. A recommendation engine crashed during peak shopping season due to an unannounced upstream schema change, costing $150,000 per hour in losses. These are not theoretical warnings. They are documented incidents showing how fragile AI systems can be without robust safeguards. The lessons are sobering but clear. First, expect failure. AI systems will fail from data issues, shortcomings, infrastructure gaps, or organizational missteps. Second, monitor everything. Failures are inevitable without robust observability and retraining systems. Third, build reliability by pairing technical solutions with governance practices, ensuring resilience across the lifecycle. And finally, be proactive. Don't wait for catastrophic failure. Audit monitoring capabilities, implement data quality checks, define ownership boundaries, and create incident playbooks. Above all, build a culture that anticipates failure. In AI, success is not the absence of breakdowns, but the ability to respond, adapt, and recover quickly when they occur. Inference is the heart of real-time AI. Every click on a recommendation system, every query to a chatbot, every decision from an autonomous vehicle depends on inference delivering the right response at the right time. But in the real world, systems fail. Hardware crashes, networks partition, memory leaks creep in, and upstream services go down without warning. When inference fails, the consequences ripple outward instantly. For a high-volume e-commerce system, every second of downtime translates into lost revenue. For user-facing applications, latency spikes frustrate customers, driving them away. And in safety-critical systems such as healthcare diagnostics or self-driving cars, inference failures can place human lives at risk. The lesson is simple. Failures are not hypothetical. They are inevitable. Fault tolerance is therefore about designing systems that don't just aim for perfection, but instead anticipate imperfection. Systems that recover gracefully without data loss when, not if, components fail. Failures can enter AI inference systems from multiple angles. Hardware failures are common. GPU crashes, corrupted memory, node outages, or sudden power disruptions can instantly knock capacity offline. Network issues, from dropped connections to DNS errors to misbehaving load balancers, can disrupt the flow of requests. Software bugs add another layer of fragility, with memory leaks, container crashes, deadlocks, or resource exhaustion causing gradual or sudden degradation. Then there are external dependencies, upstream APIs, feature stores, and model registries that your inference pipeline depends on may themselves fail. AI systems face not only traditional infrastructure problems, but also ML-specific fragilities, model loading bottlenecks, inference timeouts, or corrupted artifacts. A resilient system recognizes this spectrum of risks and plans accordingly. The foundation of fault tolerance rests on four principles. First is redundancy. Deploy multiple replicas of inference servers across distinct failure domains to ensure there is no single point of failure. Second is isolation. Contain failures through bulkheading, resource quotas, and circuit separation so that one failing service cannot cascade through the system. Third is graceful degradation. When core systems fail, fallback models or heuristic rules maintain baseline functionality, preserving user experience even in degraded states. And fourth is resilience testing. It is not enough to design for resilience on paper. Teams must validate it regularly with chaos experiments and controlled failure injections. These principles acknowledge that perfection is impossible. Instead, they create robustness, ensuring that even under stress, the system bends but does not break. Replication provides the backbone of resilience. By deploying multiple replicas of inference servers behind a load balancer, traffic automatically routes away from failed instances to healthy ones. Kubernetes health probes and deployments automate healing, restarting pods when crashes occur. Horizontal pod autoscalers expand or contract capacity based on CPU, memory, or custom metrics, ensuring elasticity under demand. For GPU-intensive workloads, replication must go further. Over-provisioning by 20 to 30% ensures capacity to absorb sudden traffic spikes or handle the unexpected failure of nodes. Fault tolerance here is about elasticity and self-healing. Systems that can root around failures and regenerate capacity avoid catastrophic outages and preserve user trust. Even with replication, there will be moments when primary models fail. This is where fallback models serve as safety nets. These are lightweight, often less accurate but more stable models, deployed in parallel. When a GPU crash or latency spike is detected, traffic is diverted to the fallback. For example, in content moderation, if a transformer-based toxic content detector crashes, the system can fall back to a smaller but model or even regex-based filters. In recommendation systems, if personalized ML models become unavailable, fallback logic might deliver popularity-based or category-driven results. While not perfect, these mechanisms preserve core functionality, ensuring that the system continues to serve users, albeit at a reduced level of sophistication. Fallbacks buy time to restore full service without users experiencing total failure. One of the most dangerous failure patterns in distributed AI systems is cascading collapse, where one faltering service drags down others. Circuit breakers are the antidote. By monitoring error rates and latency, circuit breakers trip when thresholds are exceeded. For instance, more than 20% of requests failing. Once tripped, the breaker stops sending requests to the failing service, rejecting traffic preemptively to avoid overloading it further. After a cooldown, test requests probe for recovery. Circuit breakers can be implemented through Certus meshes like Istio or Linkerd, or libraries such as Resilience4j and Poly that follow the Hystrix pattern. The goal is to fail fast, shed load, and give failing services time to recover, preventing localized issues from spreading across the system. Retries are essential, but they must be handled carefully. Blindly retrying can amplify stress on already struggling services. The best practice is exponential backoff with jitter, where retries increase in spacing 100 milliseconds, 200 milliseconds, 400 milliseconds, 800 milliseconds, with random variation to prevent thundering herds. Equally important are strict timeouts. Model inference might allow 500 milliseconds to 2 seconds, depending on complexity. Feature retrieval, 150 to 300 milliseconds. The end-to-end pipeline, no more than 3 to 5 seconds. Monitoring retry success rates helps identify whether retries are healing failures or compounding them. Every retry consumes resources, so systems must balance recovery attempts against total load. Smart retries and disciplined timeouts transform retries from a liability into a resilience tool. Designing for fault tolerance on paper is not enough. Resilience must be tested. Chaos engineering introduces controlled failures to validate defenses. Teams simulate GPU crashes or node terminations, inject network latency or packet loss, throttle CPU and memory, and deliberately break dependencies like feature stores. During these experiments, they verify whether alerts trigger as intended, fallback models engage correctly, and recovery occurs within SLOs, all without data loss. Tools like Chaos Mesh, Gremlin, and Litmus Chaos make this systematic. The principle is simple. Test in controlled environments so that real-world failures do not come as surprises. Start small, in staging, and increase scope over time. Chaos engineering is the fire drill of AI reliability. Over time, several best practices emerge. First, design for failure. Treat failure as inevitable and prepare accordingly. Second, multi-region deployment spreads risk geographically, ensuring that regional outages do not cripple global services. Third, automate everything. Health checks, failovers, and recovery procedures should minimize human intervention. Fourth, regular testing. Resilience drills and chaos experiments should be scheduled and documented, training both systems and teams. Finally, business-aligned SLAs ensure that reliability goals are tied to real-world impact. Latency and availability must be defined in terms that matter to customers, not just engineers. Together, these practices ensure that fault tolerance is not an afterthought, but a disciplined, ongoing process. Fault tolerance in AI inference is about surviving, not avoiding failure. AI systems must be designed to handle both traditional infrastructure breakdowns and ML-specific failure modes. A layered defense, replication, fallback models, circuit breakers, retries, and timeouts ensures no single mechanism is a bottleneck. Chaos engineering validates resilience before crises strike. And above all, reliability must be treated as equal in importance to accuracy. Users care not only that AI is smart, but that it is always available, predictable, and safe. Fault tolerance builds trust, ensuring that AI systems are not just clever in the lab, but dependable in the world. Artificial intelligence APIs are no longer experimental toys. They are mission-critical components woven into user-facing applications, business operations, and customer experiences. A single outage in an AI API can ripple outward, causing lost revenue, frustrated users, and long-term damage to trust. Redundancy and failover are therefore not optional add-ons. They are strategic imperatives. By embedding resilience into design, we acknowledge a fundamental truth. Failures will happen. Servers will crash, regions will go down, and networks will falter. The question is not if, but when. Redundancy provides the safety net, ensuring alternative resources are ready to take over instantly. Failover mechanisms execute the handoff seamlessly. Together, they transform fragile systems into robust platforms capable of weathering disruption. Redundancy matters because downtime in AI APIs strikes directly at the heart of business and customer trust. When an AI-driven recommendation engine fails, customers see irrelevant results and leave. When a fraud detection API goes offline, businesses expose themselves to financial losses. When a conversational AI bot crashes, user frustration mounts, tarnishing brand reputation. Redundancy ensures high availability, which is the cornerstone of trust. Enterprises that invest in resilient AI infrastructure communicate a message. You can depend on us no matter what. In contrast, those that neglect redundancy gamble with customer loyalty. In the digital economy, availability is not a feature, it is the product. At its core, redundancy means eliminating single points of failure. This involves duplication across all critical layers. Compute redundancy deploys multiple replicas of inference servers across diverse infrastructure units, so one crash doesn't cripple capacity. Network redundancy provisions multiple load balancers, diverse network paths, and DNS failover rules to prevent bottlenecks or routing failures. Storage redundancy replicates model artifacts and embeddings across zones, ensuring models remain accessible even during outages. The philosophy is simple: assume everything can and will fail, then design so the system keeps working anyway. Redundancy is the art of expecting imperfection and engineering continuity. Redundancy without failover is wasted potential. Failover mechanisms ensure the backup resources step in seamlessly. Four patterns dominate. Active-active distributes traffic across all replicas, maximizing utilization and delivering instant failover, though it requires greater operational sophistication. Active-passive keeps backups on standby, cost-effective but slower to recover. Regional failover shifts traffic between geographic regions. Shielding services from large-scale outages. DNS failover, though slower, provides a last line of defense across providers by rerouting traffic via health check DNS updates. Each mechanism trades off cost, complexity, and recovery speed. The choice depends on business criticality and budget, but the principle is the same. No single failure should ever halt the system. Geographic distribution provides resilience at scale. Deploying inference servers across multiple zones and regions ensures that even natural disasters, power failures, or regional cloud outages cannot bring down the system. Multi-zone deployments protect against local failures, while multi-region deployments provide protection against continental disruptions. Replicating models in regional caches reduces latency, ensuring performance alongside resilience. Automated routing ensures traffic shifts to healthy regions in real time. Examples include AWS multi-AZ architectures, GCP's multi-region clusters, and Azure's availability zones. This strategy transforms AI APIs from fragile local services into global platforms capable of withstanding shocks at any scale. Load balancers are the control towers of redundancy. At the container orchestration level, Kubernetes services, ingress controllers, and meshes like Istio route around pod-level failures automatically. At the cloud load balancer level, services like AWS ALB and GCP load balancer handle cross-zone traffic, routing intelligently based on health. At the DNS level, global systems like Route 53 and Cloud DNS enable cross-region rerouting, powered by health checks that detect outages in seconds. The common thread is health probes. Without them, load balancers cannot distinguish healthy from unhealthy backends. With them, load balancing becomes the dynamic heartbeat of a resilient AI system. Models are useless without the data that powers them, making redundancy in databases and feature stores essential. For feature stores, read replicas enable scaling. Asynchronous replication covers offline use cases, and synchronous replication safeguards critical online features. For vector databases, multi-zone deployments and sharded replicas deliver high availability for semantic search. Replicated embedding indexes ensure consistency across regions. Here, friends, organizations face choices. Hot replicas, which provide instant failover but demand higher costs, or cold replicas, which are cheaper but slower to activate. The right balance depends on recovery time objectives, RTOs, and cost tolerance. In all cases, redundancy ensures data availability matches model availability. Failover mechanisms that are never tested cannot be trusted. Chaos engineering provides the discipline to validate redundancy. Teams simulate pod or node failures, ensuring automatic rescheduling restores service. They simulate zone outages, confirming regional routing works. They force database failovers, verifying replica promotion and connection handling. Tools like Chaos Mesh, Gremlin, and Litmus Chaos make these drills systematic. The goal is not to cause chaos, but to build confidence. By practicing failure, teams ensure that when real disruptions strike, the system responds predictably, not chaotically. Untested redundancy is no redundancy at all. Redundancy comes with costs. Active-active multi-region systems deliver near-perfect availability but demand enterprise budgets. Active-passive or single-region setups are cheaper but slower to recover. Startups may accept limited redundancy to save costs, while enterprises cannot risk it. The trade-off is clear. Higher redundancy buys reliability at higher expense. Visualizing this as a spectrum from startup tier with manual failover to enterprise tier with fully automated geo-distributed load balancing clarifies decision-making. The key is alignment. Match SLA promises with business criticality and budget realities. Overinvesting wastes resources. Underinvesting risks collapse. The balance must be intentional. From experience, several best practices emerge. Implement robust health checks that test actual functionality, not just process existence. Automate failover procedures using orchestration platforms and programmable DNS, eliminating manual delays. Replicate models and features across zones and regions to ensure consistency. Run regular chaos drills to expose weaknesses and build operational confidence. And above all, align redundancy strategy with business needs. Not all APIs require the same resilience. Critical fraud detection APIs demand multi-region active-active setups, while internal experimentation APIs may only need active-passive. Tailor redundancy to impact, balancing resilience and cost pragmatically. The essence of redundancy and failover for AI APIs can be summarized in 4 truths. First, redundancy eliminates single points of failure across compute, network, and storage. Second, automated failover mechanisms guarantee availability when infrastructure fails. Third, multi-region deployment with intelligent routing represents the enterprise gold standard for mission-critical AI. And fourth, redundancy must be validated through chaos testing and regular drills to prove its worth. The final lesson is sobering. Your AI services are only as reliable as the weakest component in your infrastructure. True resilience requires vigilance, investment, and discipline. It is not glamorous, but it is the difference between fragile promises and dependable AI. Artificial intelligence never sleeps. It powers recommendation engines around the clock, secures transactions in real time, and supports healthcare systems where seconds can mean lives saved. In this environment, high availability, often abbreviated HA, is not just a feature, but a mandate. High availability represents our collective commitment to minimize downtime and service disruption in mission-critical AI systems. It is quantified through the language of nines of uptime. 3 nines equates to 99.9% availability, or roughly 8.76 hours of downtime per year. 4 nines reduces that to just 52.6 minutes. And 5 nines, the gold standard, cuts downtime to a mere 5.26 minutes annually. Achieving such performance is not easy, nor is it cheap, but for applications like AI APIs, fraud detection, healthcare machine learning, and autonomous systems, anything less is unacceptable. This opening sets the stage. HA is about trust, resilience, and the expectation of continuous operation. While high availability is a concept well established in traditional IT, AI introduces new challenges that make the problem far more complex. Model accessibility becomes paramount. Machine learning models must be ready to serve inference requests regardless of infrastructure state. Downtime here doesn't just mean slower responses, it means business logic breaks, fraud goes undetected, or patient diagnoses stall. Training resilience is another requirement. Distributed training pipelines can take hours, days, or even weeks to run. A single node failure cannot be allowed to erase progress or corrupt model artifacts. Inference stability is equally vital. Inference APIs must withstand not just crashes, but also unpredictable traffic spikes, all while maintaining strict service level agreements. In other words, HA for AI requires resilience across the entire stack: compute, storage, and networking. It extends beyond uptime into performance continuity, ensuring that AI systems remain trustworthy in the face of inevitable disruptions. Building resilient AI systems requires a philosophy of engineering that assumes failure is not an exception, but a certainty. 4 principles define this philosophy. The first is redundancy, deploying multiple replicas across zones and regions to ensure no single point of failure exists. The second is isolation, designing so that failures in one component cannot cascade to others. This is achieved through resource separation, bulkheads, and fault domains. The third is failover, or the ability to automatically reroute traffic and workloads to healthy services when problems arise. And finally, resilience testing, running chaos drills and injecting failures regularly to validate design assumptions. These principles remind us that HA is not a static checkbox, but a continuous discipline. By planning for failure at every level, organizations transform fragility into resilience, ensuring that AI systems bend but do not break when stress arrives. At the compute layer, Kubernetes has become the backbone of high availability design. Standard practices include deployments with replica sets, ideally 3 or more, to ensure redundancy. Horizontal and vertical pod autoscalers dynamically adjust capacity based on demand or resource utilization. Pod disruption budgets safeguard against over-aggressive scaling or upgrades that reduce availability. Dedicated node pools ensure that critical ML workloads are insulated from noisy neighbors. Advanced configurations bring further resilience. GPU scheduling with node affinity and tolerations places jobs intelligently across hardware, while pod anti-affinity rules spread workloads across zones to mitigate localized outages. Readiness and liveness probes trigger auto-healing, restarting containers when they falter, and multi-zone clusters enable survival even in the event of a full data center outage. The anti-pattern to avoid is overcommitting GPU resources, which may look efficient in the short term, but guarantees contention and service degradation during failure events. Storage is the lifeblood of AI, and high availability here means both resilience and consistency. Persistent storage backends such as Ceph, AWS EBS, or GCP persistent disks provide replication across zones, ensuring durability. Where supported, multi-attach volumes allow fast failover between nodes. Storage classes must be chosen with redundancy in mind, balancing performance with resilience. For ML data storage, multi-region data lakes, and distributed file systems like S3, HDFS, or GCS keep training and inference data accessible at all times. Feature stores benefit from hot replicas that maintain low latency availability. Recovery mechanisms are equally important. Continuous snapshots and backups provide insurance. Point-in-time recovery allows rollback from corruption, and cross-region replication guarantees survivability even in regional failures. In essence, HA storage protects not only against hardware faults, but also against inconsistency during load and recovery, ensuring models and data are never out of reach. The network layer is the circulatory system of AI clusters. Intelligent load balancing with active health probes detects failures within milliseconds, rerouting requests seamlessly to healthy endpoints. Resilient ingress is achieved with multi-zone ingress controllers, NGIX, Istio, or Envoy, that offer automatic failover. Global routing, often managed through DNS failover services like Route 53 or Cloud DNS, ensures multi-region resilience, allowing traffic to shift seamlessly if one region falters. For mission-critical ML pipelines, dedicated connectivity with redundant interconnects reduces the risk of single network dependency. High-availability networking is not just about redundancy, but about speed. The faster the system can detect and reroute around failures, the less impact end users experience. In AI systems where every millisecond may affect outcomes, resilient networking is as important as resilient compute or storage. Distributed training introduces challenges distinct from inference. Checkpoint management is essential. Frequent checkpoints allow recovery without losing days of progress when nodes fail. Elastic training frameworks such as Horovod, DeepSpeed, or Kubernetes native operators enable training jobs to survive node loss gracefully, reallocating tasks to healthy nodes. Cost-effective resilience is often achieved through preemptible or spot instances, which are cheaper but ephemeral. To balance cost and availability, systems must be designed to resume seamlessly from checkpoints when spot instances vanish. The best practice is clear. Training jobs should always be architected to assume failure, automatically resuming from the last known good state using storage replicated across zones. High availability for training doesn't mean preventing failure. It means ensuring progress is never lost, no matter how turbulent the environment. Inference services face stricter uptime requirements since they are directly exposed to users. Multi-replica serving is non-negotiable. Inference servers like Triton, TorchServe, or Kserve should be deployed with at least 3 replicas across failure domains. Horizontal scaling ensures elasticity to meet traffic surges. Deployment strategies add another layer of safety. Canary and blue-green rollouts allow gradual model upgrades with automatic rollback if issues arise. Shadow models can run alongside production models, enabling resilience testing under real workloads. Advanced resilience measures include latency-based autoscaling, which prioritizes user experience, and circuit breakers that prevent dependency failures from cascading. The philosophy here is simple. Inference APIs must not only be accurate, but also relentlessly available, absorbing failures while sustaining service-level agreements. You cannot guarantee what you cannot measure. High availability is validated not by design documents, but by metrics. Key metrics to monitor include uptime per service and endpoint, failover events and recovery time, latency spikes during degraded states, replica mismatches, and resource utilization under failure conditions. Observability also extends into chaos engineering, where failures are injected intentionally. Node terminations, network partitions, disk failures, resource exhaustion to test system resilience. Tools like Chaos Mesh or Gremlin make this process systematic. The point is not to break systems recklessly, but to verify that HA mechanisms behave as intended. Observability and chaos testing provide evidence, not assumptions, that high availability is real, measurable, and reliable. High availability if not free. Each additional 9 of uptime requires exponentially greater investment. Free 9s, 99.9%, is achievable with single region active passive setups and automated failover, amounting to about 8.8 hours of downtime per year. 4 9s, 99.99%, demands multi-region active architectures, global load balancing, and real-time replication, reducing downtime to under an hour annually. 5 9s, 99.99%, requires fully engineered redundancy, instant failover, and complete duplication of infrastructure, allowing only 5 minutes of downtime per year. Each step doubles or triples costs. The critical lesson is to match availability goals to business needs. Over-engineering wastes resources. Under-engineering risks catastrophic outages. Availability must align with service level agreements and compliance obligations, balancing cost with impact. From experience, several best practices emerge for high availability AI clusters. Designed for failure by default, assume components will fail and build redundancy at every layer. Distribute across domains. Spread workloads across zones and regions to survive localized outages. Automate recovery. Failover and scaling should happen automatically, minimizing reliance on human intervention. Validate with testing. Chaos engineering and observability provide proof, not just assumptions. And finally, right-size investment. Align your HA tier with actual SLA and compliance requirements, avoiding waste while meeting obligations. These best practices transform HA from an aspiration into an operational reality, embedding resilience directly into the DNA of AI systems. The story of high availability in AI can be distilled into 4 takeaways. First, eliminate single points of failure by building resilience across compute, storage, and networking layers. Second, design for end-to-end resilience, ensuring both training and inference can survive failures. Third, prove your design works with observability and chaos testing. Don't rely on assumptions. And fourth, adopt strategic investment. Balance cost with uptime needs, matching availability levels to business impact. In the end, high availability is not just about keeping AI systems online. It is about building trust. It assures customers, regulators, and stakeholders that your AI infrastructure is reliable, resilient, and ready for the unpredictable realities of the world. Artificial intelligence workloads demand constant reliability, yet AI clusters, by their very nature, are large, complex, and inherently failure-prone. Pods crash, nodes go down, and GPU memory errors are common. Traditional manual recovery is simply too slow and too costly. Downtime means broken service level agreements, missed opportunities, and spiraling operational overhead. Auto-healing addresses this by embedding recovery directly into the infrastructure. With proper auto-healing, organizations can maintain higher uptime to meet strict SLAs, build resilience against inevitable pod and node crashes, and recover quickly with minimal human intervention. It transforms operations for reactive firefighting into proactive resilience. In short, auto-healing isn't just about convenience. It is about enabling AI systems to operate continuously, confidently, and at scale. Kubernetes is the engine of auto-healing because it never stops reconciling the desired state of the system with its actual state. Controllers continuously monitor resources and act whenever discrepancies are detected. At the pod level, Kubernetes can detect failed pods and restart them automatically, eliminating downtime from transient failures. At the node level, it can identify lost nodes and reschedule workloads efficiently, ensuring that jobs continue uninterrupted. Health probes add an additional layer of intelligence, verifying whether workloads are truly ready before routing traffic. Together, controllers, pod recovery, node replacement, and probes create a self-healing system. This design principle means AI clusters don't rely on humans to notice problems. They resolve them autonomously, preserving integrity and availability. Pod failures are routine in AI workloads, especially GPU-intensive ones prone to out-of-memory errors or CUDA faults. Kubernetes addresses this with restart policy options. Always ensures pods restart regardless of the exit reason. On failure, restarts only on non-zero exit codes, and never avoids restarting jobs intended to run once. In practice, when a GPU inference pod crashes, Kubernetes detects the failure, terminates the faulty pod, schedules a replacement, and routes traffic to the new pod only after it passes readiness checks. This cycle happens automatically and quickly, minimizing downtime. Pod level healing is the foundation of reliability for inference systems, ensuring that individual pod crashes never escalate into service outages. Nodes are the backbone of AI clusters, and when they fail, the impact can be severe. The Kubernetes node controller constantly monitors node heartbeats to detect failures. When a node goes down, it marks it unhealthy, evicts all pods, and reschedules them onto healthy nodes. Cloud provider integrations extend this capability. AWS auto-scaling groups, GCP node auto-repair, and Azure VM scale sets all support automatic node replacement. This means the system not only reacts by rescheduling workloads, but also actively restores lost capacity. Node-level healing combines Kubernetes orchestration with cloud elasticity to deliver fault tolerance at infrastructure scale. Probes are the intelligence layer that keeps AI workloads responsive and reliable. A liveness probe detects if a pod is stuck or unresponsive and restarts it automatically. A readiness probe ensures that pods only receive traffic when they are fully prepared to serve. Failing pods are removed from endpoints. A startup probe handles slow-starting workloads, such as large language models or GPU-heavy jobs, disabling other probes until initialization completes. Examples might include curling, health, ready, or model-loaded endpoints. Configuring probes properly prevents traffic from reaching unhealthy inference servers and guarantees consistent API responses. Without probes, auto-healing lacks context. With them, it becomes precise and dependable. Redundancy is a hallmark of high availability. Kubernetes replica sets and deployments ensure multiple replicas of AI workloads are always maintained. If one pod fails, the load balancer routes traffic to healthy replicas while the deployment controller spins up replacements to meet the defined replica count. For critical AI inference services, this means zero downtime even when pods fail. A kubectl get deployments command might show 3 replicas of an inference API or 2 replicas of a feature store, all ready, up to date, and available. This redundancy ensures that user-facing services remain uninterrupted no matter the state of individual pods. Some AI workloads demand more than simple stateless redundancy. Stateful sets preserve pod identity and storage, enabling consistent network identifiers and stable volume attachments. This is essential for distributed training systems, sharded databases, or vector stores where identity matters. With stateful sets, when a pod crashes, Kubernetes recreates it with the same identity, pod 0, pod 1, and reattaches its persistent volume. Operations happen in predictable order, ensuring consistency across scaling and updates. For AI systems, this means feature stores, model storage, and vector databases maintain integrity even in the face of failures. Stateful sets extend auto-healing beyond stateless apps into the complex world of persistent AI workloads. No auto-healing system should be trusted without testing. Chaos engineering validates resilience by deliberately injecting failures. Killing pods and nodes verifies automatic redeployment. Injecting resource contention or GPU memory errors tests how gracefully workloads recover. Simulating network partitions checks if systems can remain resilient when components lose connectivity. Tools like Chaos Mesh, Litmus Chaos, and Gremlin make these experiments systematic. Chaos testing reveals weaknesses that would otherwise surface only during production incidents. It ensures the healing mechanisms are not just theoretical, but practical, reducing surprises in real-world operations. Auto-healing principles apply across the AI pipeline. In training, checkpoints combined with job restarts prevent wasted computation when failures strike. Failed nodes are automatically replaced, allowing training to continue seamlessly. In feature stores, stateful sets ensure data integrity, while workflow engines like Airflow or Kubeflow retry failed tasks. For inference, quick pod replacement ensures low API downtime, while replicas distributed across zones guarantee regional resilience. Together, these mechanisms create an end-to-end self-healing pipeline where every stage, training, storage, and inference can recover from failure without halting the entire system. Several best practices maximize the effectiveness of auto-healing. Define effective probes for every AI model server, tailored to its behavior. Distribute workloads across multiple nodes, zones, and regions to minimize the blast radius of failures. Integrate with cloud tools like autoscalers and repair services to extend Kubernetes healing capabilities. Conduct chaos testing regularly to validate resilience in practice. Monitor healing events, pod restarts, node replacements, and probe failures to ensure SLAs are met. Finally, use resource requests and limits to prevent cascading failures from resource contention. These practices turn auto-healing from a theoretical capability into a proven operational discipline. The essence of auto-healing is this: Kubernetes can function as a self-healing engine for AI infrastructure. By combining pod restarts, node replacements, health probes, and replicas, organizations achieve comprehensive resilience. Regular chaos testing verifies these mechanisms in practice, ensuring reliability isn't just assumed, but demonstrated. Auto-healing isn't merely a convenience, it is a competitive advantage for teams running AI workloads at scale. It means higher uptime, faster recovery, and lower operational burden. More than that, it means trust. End users and stakeholders can depend on systems that recover automatically, invisibly, and consistently, even in the face of inevitable failures. Artificial intelligence systems are among the most complex infrastructures we operate today. They span distributed clusters, streaming data pipelines, GPUs, APIs, and multiple orchestration layers. With so many moving parts, failures are not rare events. They are guaranteed. The challenge is not whether failures occur, but whether systems are prepared to withstand them. Chaos engineering answers this challenge by flipping our perspective. Instead of waiting for failures to strike in production, we deliberately introduce them in controlled conditions. We break things on purpose to reveal weak points. We stress systems intentionally so that when the real world inevitably applies pressure, the system bends without breaking. For AI, this is transformative. Chaos engineering equips teams with confidence that their inference services, pipelines, and models can survive disruption, delivering reliability not by accident, but by design. The case for chaos engineering rests on three truths. First, AI infrastructure is complex and distributed. A single model serving endpoint might depend on dozens of services, feature stores, vector databases, orchestration frameworks, GPU schedulers, and monitoring dashboards. Each dependency creates a new potential point of failure. Second, failures are inevitable. Nodes crash, networks partition, APIs timeout, and GPU stall. Hoping these failures won't happen is wishful thinking. Third, chaos engineering builds proactive confidence. By simulating failures before they happen, organizations identify weaknesses in advance, harden their systems, and train their teams. Instead of panic during an outage, engineers respond with practiced calm because they've rehearsed it before. Chaos engineering is not about creating chaos for its own sake. It is about creating order out of inevitable disorder. Chaos engineering follows a systematic cycle grounded in scientific method. The first step is to define the steady state, metrics that describe normal behavior. For AI systems, this includes P95 or P99 latency for inference, throughput in requests per second, model accuracy, and baseline GPU or CPU utilization. Next, we inject controlled failure, deliberately creating disruptions with a clear scope and safety boundaries. Then, we observe system response, watching how the system deviates from the steady state. Finally, we improve and repeat, fixing vulnerabilities and running progressively more complex experiments. Each cycle builds confidence. Each failure injection makes the system stronger. This disciplined loop transforms chaos engineering from random breakage into a science of resilience. AI systems have unique components that require targeted chaos experiments. At the infrastructure layer, we simulate GPU node crashes, pod evictions, or resource exhaustion to test cluster resilience. At the network layer, we inject latency, packet loss, DNS failures, or API timeouts to examine service dependencies. For the data pipeline, we simulate delayed Kafka streams, schema changes, or corrupted batches, testing whether ingestion and validation processes recover gracefully. At the model serving layer, we test OOM errors, frozen inference pods, or conflicts between model versions. Each of these chaos targets reflects the reality that AI systems do not just fail as servers, they fail as models, pipelines, and data ecosystems. By targeting all these levels, chaos engineering validates resilience holistically. The ecosystem of chaos engineering tools is rich and growing. Chaos Mesh is a Kubernetes native platform designed for cloud-native environments. It orchestrates pod and node failures, network chaos, and I/O disruption. Litmus Chaos provides pre-built chaos experiments covering application-level and node-level failures for Kubernetes and beyond. Gremlin offers a commercial chaos-as-a-service solution with user-friendly interfaces, fine-grained blast radius control, and scheduling capabilities. Finally, service mesh tools like Istio or Envoy enable API-level chaos, injecting HTTP errors or request delays directly at the traffic layer. Each tool provides different strengths, but together they make chaos experiments systematic, repeatable, and safe. The key is integration, weaving chaos testing into the same pipelines where we test functionality, performance, and security. A classic chaos test begins with pod termination. Imagine an inference system handling 50 queries per second with a P95 latency under 200 milliseconds. The hypothesis: the system can handle random pod terminations without service degradation. The experiment uses Chaos Mesh to randomly kill inference pods. As pods vanish, Kubernetes reschedules replacements, while load balancers reroute traffic to healthy replicas. Engineers monitor latency, throughput, and error rates in real time. Success is measured by whether QPS remains stable and P95 latency stays below threshold. If the system holds steady, confidence grows. If not, the weaknesses are revealed for remediation. This test may seem simple, but it validates one of the most critical promises of Kubernetes, that no single pod failure should disrupt production. AI workloads are uniquely dependent on GPUs, which makes GPU chaos testing essential. A GPU failure experiment begins by removing the GPU device plugin from a node, simulating hardware loss. Kubernetes should detect the issue and reschedule workloads to healthy GPU nodes. Train jobs are expected to checkpoint progress, resume on new nodes, and continue without data loss. Recovery time is measured and progress continuity is validated. If jobs fail or data is lost, resilience mechanisms need improvement. This experiment proves whether training pipelines can survive the inevitable, a GPU crash mid-run. For large-scale distributed training that may take days, this validation is the difference between wasted compute budgets and seamless recovery. Pipelines, not just models, must be tested for resilience. Data ingestion delays can be simulated by slowing down Kafka or pub/messages, testing whether feature pipelines buffer and recover. Corrupted data injections validate whether drift detection or anomaly filters catch bad inputs before they poison training. Partial processing failures, such as killing ETL jobs mid-task, test whether retry logic and recovery workflows engage correctly. The expected outcomes are clear: auto recovery of pipeline components, retraining triggers activating when thresholds are crossed, data validation systems quarantining bad inputs, and alerting systems notifying teams. Together, these tests build confidence that ML pipelines remain healthy even when data misbehaves. Chaos engineering must be approached carefully. First, start small and scale gradually. Begin in staging environments with simple pod failures. Then, cautiously expand to multi-node outages or regional simulations. Second, automate chaos by integrating experiments into CI/CD pipelines. Pod failure tests after each deployment ensure resilience is continuously validated. Third, define clear abort conditions. Experiments must stop if critical thresholds are crossed, such as error rates exceeding 0.5% or P99 latency rising above 500 milliseconds. Finally, measure MTTR, mean time to recovery, as a key metric. Over time, the goal is to reduce MTTR consistently, proving resilience improvements. Chaos engineering is not about recklessness. It is about disciplined testing with safety valves. AI introduces unique challenges that chaos engineering must address. Beyond uptime metrics, resilience tests must measure not only availability, but also model accuracy and fairness under stress. A system may appear healthy while delivering increasingly inaccurate predictions, a silent failure mode. Silent drift detection is essential, as some failures cause gradual degradation rather than immediate crashes. Complex blast radius complicates experiments in multi-tenant GPU clusters, where collateral damage must be avoided. And finally, integrated observability is vital, combining infrastructure metrics with ML-specific telemetry to reveal the full picture. The unique risk of AI is this: infrastructure can look healthy while the models themselves silently fail. Chaos engineering must therefore expand its scope beyond servers and APIs to include accuracy, bias, and drift. The message of chaos engineering for AI is clear. First, it provides proactive reliability testing, surfacing weaknesses before users experience them. Second, it identifies AI-specific chaos targets, pods, GPUs, pipelines, and model-serving systems that must be validated under stress. Third, it leverages a rich tooling ecosystem of chaos mesh, litmus chaos, gremlin, and service meshes to make tests systematic. And fourth, it builds confidence for engineers, operators, and stakeholders that AI systems can survive the unexpected. The motto of chaos engineering is simple: break things intentionally so they don't break unexpectedly. By starting the chaos journey today, organizations prepare their AI systems for tomorrow's unpredictable realities. Modern enterprises no longer see cloud as a single provider decision. Instead, they recognize that different clouds bring different strengths, and by leveraging multiple providers, organizations unlock flexibility, resilience, and negotiation leverage. Multi cloud is not just a buzzword, it is a strategy for long term sustainability. By diversifying across providers, businesses avoid dependence on a single vendor, reduce the risk of outages, and align their infrastructure more closely with evolving regulatory and performance needs. This approach positions multi cloud as both a shield against disruption and a key driver of innovation. No single cloud provider excels at everything. AWS, Azure, and Google Cloud each have unique strengths, whether in GKU availability, compliance certifications, or managed AI services. Multi cloud enables diversified excellence, ensuring organizations can pick the best tool for the job. It also distributes risk, ensuring that no outage or provider disruption halts critical services. Moreover, multi cloud fosters service optimization, choosing the right mix of vector databases, ML pipelines, or edge services depending on which provider does it best. Finally, global compliance is easier in multi cloud architectures, as different regions and regulatory jurisdictions can be supported simultaneously. This big picture view frames multi cloud as the pragmatic evolution of enterprise infrastructure strategy. The push toward multi cloud is driven by business realities. Resilience and continuity come first. Geographic redundancy protects against regional outages. Vendor leverage follows. Avoiding lock in gives enterprises stronger negotiating positions on pricing and contract terms. Mergers and acquisitions introduce M&A reality, where inherited technology stacks often span different providers. Regulatory compliance requires data sovereignty, keeping sensitive information within certain geographies. Finally, proximity performance enhances user experience by placing workloads close to end users. Each of these drivers delivers tangible business value, offsetting the management complexity multi cloud introduces. AI workloads add new urgency to multi cloud adoption. GPU capacity and choice have become scarce commodities, and multi cloud access ensures organizations can secure the right chips where they are available. Specialized services, such as vector databases, managed ML stacks, or emerging AI accelerators, vary across providers, making it advantageous to mix and match. Performance optimization is achieved by placing inference near data sources or users, reducing latency. Hybrid alignment allows on-premises GPU clusters to integrate with multiple clouds for elastic training bursts. For AI-driven enterprises, multi-cloud is not just a strategy for resilience, it is the only way to secure scarce resources and optimize emerging technologies. Despite its appeal, multi-cloud is not universally beneficial. Small teams with limited operational maturity may be overwhelmed by the complexity. Workloads tightly coupled with a provider's deep path integration are poor candidates for migration. Data gravity constraints arise when massive datasets make egress costs prohibitive. Simplified compliance can sometimes be better achieved with a single certified provider rather than spanning multiple environments. Ultimately, a cost-benefit analysis must guide the choice. Multi-cloud only makes sense when the additional value outweighs the operational and financial overhead. Enterprises implement multi-cloud through several common patterns. Active-active keeps services running in parallel across providers, offering maximum resilience but high cost. Active-passive DR keeps a secondary environment on standby, balancing cost with recovery speed. Cloud bursting allows workloads to spill into a second provider during demand surges. Split by workload dedicates different services to different clouds, aligning workloads with provider strengths. Per region selection leverages different providers for compliance or performance in specific geographies. Often, enterprises use multiple patterns simultaneously, tailoring architecture to diverse needs. Managing data across clouds is the greatest challenge. Data gravity means large data sets should remain near compute to minimize latency and egress costs. Replication trade-offs force choices between asynchronous replication, which is cheaper but risks higher recovery point objectives, and synchronous replication, which is costlier but provides near zero data loss. Open table formats like Iceberg, Delta, or Hudi enable portable data lakes that work across platforms. Change Data Capture, CDC, provides efficient replication from OLTP systems into multi-cloud feature stores. Finally, egress optimization through caching and edge stores reduces cross-cloud data transfer fees. Data is the linchpin of multi-cloud success, and designing for portability and efficiency is essential. Connectivity and identity form the backbone of multi-cloud integration. Private connectivity through Direct Connect, Interconnect, or Express Route ensures secure high-bandwidth traffic flows. Zero Trust Security enforces MTLS, workload identity, and short-lived credentials consistently across providers. Unified Authentication provides seamless SSO via OIDC or SAML, giving teams a consistent identity experience across environments. Intelligent DNS routes traffic based on health and proximity, while IP management prevents conflicts across clouds with coordinated CIDR IPAM planning. In multi-cloud, networking and identity are not just technical details, they are strategic enablers of performance, security, and reliability. Multi-cloud success requires orchestration that unifies diverse environments. Kubernetes serves as the portability layer, standardizing container images and Helm charts. GitOps tools like Argo CD, your Flux, enforce declarative management across clusters. Multi-cloud control planes such as Anthos, Arc, Rancher, or Crossplane provide unified visibility and governance. Service Mesh Federation connects workloads across providers with consistent policies and end-to-end MTLS. Artifact mirroring ensures container and model registries are synchronized across environments, preventing version drift. These orchestration strategies turn fragmented environments into coherent, manageable platforms. Resilience requires visibility across every provider. Unified metrics through Prometheus with Thanos or Mimr aggregate data across clusters. Distributed tracing with open telemetry provides end-to-end visibility of requests, regardless of which cloud they traverse. Security standardization ensures consistent SBOM generation, image signing, and policy enforcement with OPA Gatekeeper. A central SIEM collects and enriches logs across clouds, enabling security teams to detect and respond to threats comprehensively. Cross-cloud observability and security unify fragmented infrastructures into a single pane of glass, empowering teams to manage risk proactively. Multi-cloud without governance risks spiraling costs. On average, 40% savings are possible with effective optimization, but 73% of enterprises overspend due to poor practices. Egress costs alone often consume 25% of multi-cloud budgets. Solutions include consistent tagging for unified cost attribution, resource optimization through right sizing and spot preemptible instances, and commitment management to balance long-term discounts without stranded spend. Multi-cloud requires financial as well as technical discipline. FinOps is the practice that ensures the promise of savings becomes reality. For AI, workload placement is critical. Training workloads demand GPU availability, high storage bandwidth, and reliable checkpointing. Inference services prioritize low latency regions, auto-scaling, and proximity to edge points of presence. Feature store distribution ensures read-optimized replicas sit near inference services to minimize latency. Model registry strategy ensures signed, versioned artifacts are mirrored across providers for consistency. Strategic placement transforms multi-cloud from a redundancy exercise into a performance enabler, ensuring AI workloads always run where they perform best. Success in multi-cloud comes from structure. Start by standardizing infrastructure with Terraform, container images, and CI/CD pipelines. Next, run a pilot program with a non-critical service on a secondary cloud to validate approaches. Build a shared services foundation, identity, registry, observability that spans providers. For data migration, use CDC with dual write patterns for seamless state replication. Finally, conduct validation exercises such as DR drills and performance tests. Studies show organizations following structured roadmaps are 3.5x more likely to achieve multi-cloud objectives on time and within budget. Multi-cloud introduces real risks when poorly managed. Copy-paste architecture, blindly replicating provider-specific services, creates hidden lock-in. Ignoring economics, especially latency and egress costs, leads to shocking invoices. Configuration drift across environments creates unpredictable behavior and outages. Operational underinvestment leaves teams without the runbooks or training to manage crises. Avoiding these anti-patterns requires discipline. Treat multi-cloud as a distinct engineering practice, not a checkbox feature. The story of multi-cloud is about purpose, discipline, and pragmatism. First, multi-cloud is a strategic decision, not a trend to follow blindly. Second, success requires portable platforms, disciplined operations, and strong data design. Third, implementation must be practical, starting small, testing thoroughly, and scaling only what works. And finally, multi-cloud builds resilience, leverage, and access to unique capabilities, but only for organizations ready to manage its complexity. For enterprises prepared to make the investment, multi-cloud is the foundation for global, resilient, AI-powered operations. Enterprises are no longer satisfied with single cloud strategies. To optimize for cost, redundancy, and access to specialized hardware, they increasingly run Kubernetes clusters across multiple cloud providers. But with this expansion comes the challenge of managing distributed systems. Kubernetes Federation, often called KubeFed, provides a unifying control plane. It brings consistency across clusters by ensuring uniform deployments, centralized policy enforcement, and streamlined traffic management, whether the objective is to maintain redundancy across continents or direct users to the nearest cluster for minimal latency. Federation offers enterprises the tools to orchestrate workloads globally. The promise is simple, yet powerful. Manage your clusters as one, even when they span clouds and geographies. The motivation for federation comes from the limits of isolated clusters. Without federation, teams must configure each cluster individually, duplicating effort and risking drift in configurations or policies. Federation enables consistent deployments, ensuring the same manifests, policies, and security baselines apply everywhere. It supports multi-region disaster recovery, allowing organizations to survive cloud or regional outages without downtime, and it powers global traffic routing, directing requests dynamically based on latency, availability, or load. These features combine into a single strategic advantage. Federation transforms Kubernetes from a local orchestrator into a global management plane, aligning with enterprise needs for resilience, compliance, and speed. KubeFed is the Cloud Native Computing Foundation's official framework for multi-cluster Kubernetes management. Its value rests on three pillars. First, resource synchronization. Deployments, services, and config maps are automatically propagated across registered clusters, maintaining alignment without manual duplication. Second, policy-driven placement. Workloads are intelligently routed to clusters that meet requirements for hardware, availability, or region. Third, multi-cloud and hybrid support. KubeFed operates seamlessly across AWS, GCP, Azure, and even on-premises clusters. This transparency means organizations can treat diverse environments as one cohesive platform. For teams managing AI, where GPU capacity and compliance vary across providers, KubeFed becomes the critical layer that unifies fragmented infrastructure. KubeFed delivers several capabilities that are indispensable for AI infrastructure. Multi-cluster deployments allow a single manifest to propagate applications across clusters, with lifecycle synchronization ensuring consistency. Selective placement lets teams target only clusters that satisfy specific criteria, such as GPU availability or regional compliance rules. Failover and migration provide resilience by automatically rescheduling workloads when clusters go offline or during planned upgrades. Finally, global service discovery offers a unified DNS layer, making services accessible across all federated clusters without friction. These features ensure that enterprises can not only distribute workloads intelligently, but also sustain operations under stress, a necessity for mission-critical AI systems. Consider a common AI scenario. Training might be run in Cloud A, where GPU-optimized clusters are cheapest and most abundant. Shared ML resources, such as a centralized feature store and model registry, remain synchronized across clouds, guaranteeing consistency in data and artifacts. Inference then runs in Cloud B, strategically placed near users to minimize latency. Kubernetes Federation ties these threads together, ensuring that deployments, policies, encryption, and processes and updates remain consistent across environments. The benefit is not just operational convenience, but lifecycle alignment, from data ingestion to training to serving. Every component of the ML pipeline can be orchestrated seamlessly, regardless of where it resides. To appreciate how federation works in practice, consider a simple YAML manifest for a federated deployment. With a few lines of configuration, an inference API can be deployed simultaneously to AWS and GCP clusters. The manifest defines placement rules targeting both clusters and a template for the workload. KubeFed handles the propagation, ensuring each cluster runs the same application with identical replicas and configurations. From the operator's perspective, this is one deployment, not two. The outcome is consistency without duplication, resilience without overhead, and simplified global management. This is the essence of federation, single point control for multi-cloud reality. Application resilience depends not only on deployments but also on traffic routing. KubeFed supports federated services which expose APIs globally with uniform endpoints. Multi-cloud DNS integration with providers like Route 53 or Cloud DNS enables unified discovery. Georouting ensures users are directed to the nearest healthy cluster, reducing latency for inference-heavy workloads. And in the event of outages, automatic failover transparently reroutes traffic to healthy regions, preserving availability without user disruption. For AI systems where milliseconds matter and outages can cripple trust, traffic management becomes as important as the workloads themselves. Federation ensures the network layer matches the resilience of compute. KubeFed is not the only option, and enterprises often explore alternatives. Google Anthos offers a comprehensive fleet management solution with integrated security and service mesh. Azure Arc extends Azure governance and policies to clusters running anywhere. Rancher and OpenShift provide multi-cluster dashboards with strong management features. At the application layer, Istio Federation connects services across clusters with advanced traffic control and MTLS security. The choice often comes down to trade-offs. KubeFed offers open source flexibility, while vendor-managed platforms provide additional features and support contracts. Enterprises must weigh autonomy against integration when selecting the right federation strategy. The impact of federation is tangible and measurable. Enterprises report 42% cost savings on GPU compute through cross-cloud arbitrage. 99.99% availability becomes achievable with multi-region federation strategies. Policy compliance improves by 68% when governance is centralized across clusters. And deployment speed triples compared to managing clusters individually. These outcomes prove that federation is not an academic exercise. It delivers direct financial, operational, and compliance benefits. By enabling optimal workload placement across clouds, federation empowers organizations to achieve a balance between cost efficiency, performance, and governance. Federation is powerful but not without difficulties. Operational complexity grows as a new control plane must be managed, monitored, and debugged. Network latency across clusters can degrade performance, particularly for data-heavy AI workloads. Identity management is non-trivial. Secrets, service accounts, and RBAC rules must be synchronized consistently across providers. Debugging complexity rises as failures in federated systems often span multiple environments, complicating root cause analysis. These challenges underscore a core truth. Federation requires maturity. It is not a shortcut, but a strategic capability that must be implemented with planning, observability, and expertise. Several best practices maximize the success of Kubernetes federation. Start small. Begin with just 2 clusters and expand gradually. Selective federation is key. Federate only workloads that truly benefit from multi-cluster deployment, not everything by default. Data locality matters. Move applications rather than massive data sets to avoid egress costs and latency. Integrate GitOps workflows, ensuring consistent configuration via tools like Argo CD or Flux. Build cross-cluster observability with unified logging, metrics, and tracing to monitor federated environments holistically. Finally, conduct regular disaster recovery testing, simulating cluster failures to validate failover readiness. For AI specifically, benchmark workloads across clusters to understand how hardware and placement affect training and inference performance. The essence of federation is orchestration at scale. First, it enables multi-cloud AI deployment, managing workloads seamlessly across diverse environments. Second, it optimizes workload distribution, placing training where GPUs are most cost-effective and inference where latency is lowest. Third, it provides options beyond KubeFed, with managed platforms like Anthos, Arc, and Rancher offering integrated experiences. And finally, federation demands operational maturity, robust networking, identity management, and disciplined operations are prerequisites for success. The message is clear. Kubernetes Federation transforms multi-cloud complexity into coordinated simplicity, but only for organizations prepared to embrace the rigor it requires. In the world of multi-cloud AI workloads, data is the lifeblood of every system. Without consistent access to the same data across environments, training pipelines stall, inference APIs break, and compliance efforts falter. Data replication ensures that no matter where the workload is running, whether on AWS, Azure, or Google Cloud, it can access up-to-date, reliable datasets. The drivers are clear. First, disaster recovery. Enterprises must maintain business continuity, and replicating data across providers allows services to survive outages that could otherwise cripple operations. Second, low latency access. Positioning data closer to compute resources and users ensures faster response times, which is essential for inference-heavy systems. Third, compliance. Regulated industries such as healthcare and finance must respect data residency requirements, keeping copies in specific jurisdictions. And fourth, cross-cloud pipelines. As training and inference span multiple environments, replication becomes the glue that enables seamless operation. In essence, replication is not an optional optimization. It is the backbone of resilient, performant, and compliant AI systems. While replication offers enormous benefits, it is not without significant challenges. Data gravity is perhaps the most pressing. AI datasets often span terabytes or even petabytes, creating immense inertia that makes them expensive and slow to move. Latency and consistency trade-offs emerge as systems must balance the desire for real-time synchronization with the practical limitations of performance at scale. Egress fees present another pain point, often exceeding the cost of storage itself when moving data across cloud boundaries. Schema drift introduces risks of corruption when formats or structures evolve inconsistently between providers. Finally, security must remain a constant priority, ensuring encryption and access controls persist during transit. Cloud providers typically charge for outbound transfers, so even with careful planning, costs accumulate quickly. These hurdles mean replication must be approached with discipline and strategy, aligning technology choices with both workload demands and budget constraints. Replication strategies fall into three categories. Synchronous replication provides real-time consistency. A transaction only commits after all replicas confirm. While this ensures perfect alignment, it increases latency and operational costs, making it best suited for critical transaction data. Asynchronous replication follows an eventual consistency model. The primary commits immediately and secondaries update later. This improves performance and reduces costs, making it acceptable for most AI training data where slight lag is tolerable. Finally, hybrid replication blends both approaches. Synchronous replication is applied to metadata and critical configurations, while asynchronous replication manages bulk datasets and large assets. This balance delivers both performance and consistency, making it ideal for machine learning production systems that demand speed without sacrificing reliability. Choosing the right model is about understanding the SLA, tolerance for delay, and the criticality of each dataset. Each layer of storage in the AI stack requires specialized replication approaches. For object storage, services like S3, GCS, and Azure Blob support native replication or can be synchronized using tools such as Cloud Sync, rclone, or storage gateways. CDN edge caching further accelerates delivery of static assets. For databases, cross-cloud managed options include Cloud Spanner's multi-region setup, Aurora Global Database, Cosmos DB multi-region writes, or MongoDB Atlas multi-cloud clusters. For data lakes, portable open formats like Apache Iceberg, Delta Lake, or Apache Hudi are essential for consistency across environments, with log-based incremental replication keeping updates efficient. Finally, for streaming systems, real-time replication tools like Kafka Mirror Maker 2, PubSub bridges, or Confluent Cloud's multi-cloud features allow event flows to span providers seamlessly. These options illustrate that replication is not one size fits all. Each storage layer requires tailored solutions to meet performance and consistency goals. AI workloads depend heavily on specialized data systems such as feature stores and vector databases. Feature stores like Feast or Tecton must ensure consistent feature values across environments, with offline and online replication guaranteeing that models trained in one cloud behave the same when served in another. Vector databases, Pinecone, Milvus, or Weaviate, require active-active replication to maintain embedding consistency, which is crucial for distributed inference systems. Read replicas enhance scalability and availability for vector search queries. These mechanisms ensure that replicated embeddings or feature values produce consistent model predictions no matter where they are queried. Without this alignment, models risk producing divergent results across regions, undermining trust and accuracy. For AI, replication at this layer is mission critical. It directly impacts the quality and reliability of predictions in production. To make replication tangible, consider Kafka Mirror Maker 2, a tool for streaming events across clouds. A simple configuration file defines connectors between clusters, such as replicating features and logs from AWS to GCP. Mirror Maker 2 provides key benefits. It enables cross-cloud event consistency, supports active-active replication for high availability, and preserves offset mappings to maintain event ordering. Topic renaming policies add flexibility for cross-environment naming conventions. For AI systems, this means that feature updates or model logs produced in one provider remain visible and consistent in another. Mirror Maker 2 exemplifies the broader theme. Replication tools not only move data, but also preserve integrity, continuity, and alignment, ensuring multi-cloud AI systems remain synchronized across environments. Replication cannot succeed without robust networking and strong security. Private interconnects such as AWS Direct Connect, Google Cloud Interconnect, or Azure Express Route reduce latency, cut egress costs, and isolate traffic from the public internet. Encryption is mandatory. TLS or MTLS must secure all replication traffic, while encryption at rest ensures protection in both providers. Key management systems, KMS, Key Vault, or cloud-native equivalents must coordinate across environments to maintain consistent governance. Monitoring and alerting provide visibility. Replication lag must be tracked, failed transfers detected, and data consistency audited regularly. In AI contexts, where sensitive user or enterprise data is involved, these practices are non-negotiable. They transform replication from a fragile bridge into a fortified highway connecting clouds. Replication strategies must balance competing demands. Performance versus cost is the most obvious. Synchronous replication provides stronger consistency, but drives up egress fees, latency, and operational complexity. Compliance versus agility creates tension, as regulatory requirements may mandate local copies or audit trails that restrict replication freedom. Operational complexity also increases with multi-cloud setups, as diverse tool chains, monitoring requirements, and recovery procedures become harder to manage. Architects must align replication strategies with the specific needs of workloads, SLAs, and regulatory obligations. There is no free lunch. Every gain in performance, compliance, or cost efficiency requires trade-offs elsewhere. The challenge is to design deliberately, avoiding accidental architectures that fail under pressure. From hard-earned experience, several best practices have emerged. First, use portable data formats such as Parquet, Avro, or Iceberg to ensure interoperability across providers. Second, replicate critical subsets rather than all data, focusing on the highest value assets to reduce costs. Third, monitor replication lag with custom metrics and alerts, ensuring consistency issues are detected early. Fourth, align with AI workloads. Asynchronous replication may suffice for training, while synchronous replication is essential for inference requiring real-time consistency. And fifth, test disaster recovery regularly. Quarterly drills validate resilience and expose weak spots before real outages occur. These practices make replication both sustainable and effective, reducing costs while safeguarding resilience. The lessons of data replication across clouds are clear. Replication is the backbone of multi-cloud AI, enabling consistency, availability, and compliance. Sync versus async trade-offs must be made thoughtfully, aligning replication models with workload needs and SLAs. Open formats are the glue that ensures interoperability and long-term portability. Security comes first, with encryption and access controls guarding sensitive AI data at every step. Finally, monitoring and testing transform replication from a plan into a proven reality. In short, replication is what allows multi-cloud AI systems to function as one unified platform rather than a collection of silos. Enterprises that master replication master multi-cloud. Artificial intelligence has brought us to an era where infrastructure costs can make or break innovation. Running AI at scale requires immense GPU power, high-performance storage, and specialized networking, all of which translate into substantial expenses. Yet, beneath the surface of these costs lies a strategic opportunity: cost arbitrage across multiple cloud providers. This is the practice of deliberately selecting the right provider and the right region for the right job, leveraging differences in pricing and performance to stretch budgets further. Multi-cloud arbitrage is not just about saving a few percentage points. For enterprises running massive training jobs or serving millions of inference requests, the financial difference can add up to millions annually. The essence is strategic choice, pairing workloads with the most cost-effective environment without compromising reliability or speed. Cost arbitrage in AI infrastructure is the intentional use of multiple cloud providers to take advantage of pricing differences and specialized offerings. It is a form of strategic multi-cloud deployment, where decisions are made not out of loyalty to one provider, but out of alignment with business value. The process involves balancing three factors: price, performance, and availability. Price dictates raw spend, performance ensures models train and infer efficiently, and availability guarantees resources when they are needed. This practice is particularly critical for AI workloads, especially GPU-intensive tasks, where hardware scarcity and high costs dominate the budget. By orchestrating workloads across clouds, enterprises gain flexibility. They can train large models where GPUs are cheapest, then shift inference closer to users for performance, creating an intelligent, cost-aware infrastructure strategy. AI infrastructure costs are not uniform. They vary dramatically across providers, regions, and commitment models. High-cost components, such as GPUs, NVMe storage, and premium networking, account for the majority of expenses. Pricing variability means that the same GPU instance can cost 30 to 40% less, depending on which cloud and region is chosen. Moreover, providers offer discount opportunities in the form of spot instances, preemptible virtual machines, and reserved capacity agreements, which can drive down costs further if workloads are fault-tolerant. For AI, where training large models can take days and inference APIs must scale elastically, these differences are not trivial. They represent millions of dollars in potential savings, as long as teams are disciplined enough to monitor, plan, and exploit them. Arbitrage becomes a financial lever, unlocking resources that can be reinvested into innovation rather than infrastructure overhead. To illustrate arbitrage, consider GPU pricing. A single type of GPU, say an NVIDIA A100, might cost one rate in Cloud A's US East region, a different rate in Cloud A's Asia region, and yet another in Cloud B's Europe region. Meanwhile, Cloud C may offer the same hardware in US Central for significantly less. The variation often exceeds 30 to 40% for identical hardware. A smart arbitrage strategy trains models in the lowest cost region or provider, then deploys inference closer to users for latency-sensitive tasks. This dual approach, cheap training plus local inference, creates both cost efficiency and performance optimization. In effect, enterprises no longer think of the cloud as a static choice, They treat it as a marketplace, selecting the best offer for each phase of the AI lifecycle. Beyond GPUs, storage and networking costs present further opportunities for arbitrage. Storage arbitrage reveals differences across object and block storage. For archival bulk data, Google Cloud Storage often delivers better pricing, while Amazon S3 shines with its ecosystem integration and tooling. For block storage, performance to price ratios can vary 15 to 25% across providers at similar IOPS levels. Network arbitrage is even more critical. Network egress fees, the charges for moving data out of a cloud, often become the hidden cost driver that erases savings if ignored. A terabyte of egress can cost $50 to $120, quickly undermining GPU arbitrage gains. The lesson here is simple. Arbitrage strategies must minimize cross-cloud data transfers. Savings are real, but they are fragile if architectures are careless about data movement. Organizations can implement arbitrage through a mix of strategies. Bursting leverages a secondary cloud for extra capacity during spikes in demand, avoiding premium rates on the primary provider. Workload splitting divides tasks intelligently, training in the cheapest GPU environment while serving inference in regions close to end users. Spot or preemptible VMs shift fault-tolerant workloads to whichever provider offers the lowest spot market price at that moment. And SaaS arbitrage takes advantage of specialized managed AI services, choosing providers that offer the most cost-efficient tools for particular model types. The strongest arbitrage frameworks combine these strategies, layering automation on top so that real-time pricing data drives intelligent placement decisions. Arbitrage is not a static design. It's a living process, adapting workloads to shifting markets. Executing arbitrage effectively requires sophisticated tooling. Infrastructure as code tools like Terraform and Pulumi enable portable deployments that can shift seamlessly between providers. Kubernetes Federation simplifies workload migration across container clusters, allowing AI applications to move dynamically. Cost monitoring tools, such as Cloud Health, KubeCost, or custom FinOps dashboards, provide visibility into real-time pricing differences and highlight arbitrage opportunities. Automated bidding systems can even place workloads on the cheapest available instances in real time, integrating pricing APIs with custom autoscalers. Together, these tools transform arbitrage from a manual decision into an automated, data-driven discipline. The future of cost arbitrage lies in this automation, where infrastructure is smart enough to move itself to where it is cheapest and most efficient. While promising, arbitrage is not without risks. Egress costs are the most dangerous, as cross-cloud transfers can quickly erase GPU savings. Operational complexity rises as teams juggle multiple dashboards, APIs, and SLAs. Migration overhead must be accounted for. Shifting workloads between providers consumes engineering time and adds process burden. Monitoring discipline is non-negotiable. Without it, cloud sprawl occurs and costs balloon. The risk is that enterprises treat arbitrage casually, failing to account for total cost of ownership. The truth is clear. Arbitrage can deliver substantial savings, but only when teams are disciplined, deliberate, and prepared to manage the complexity that comes with it. Case studies illustrate arbitrage in action. An LLM startup trains large models on spot GPUs in Google Cloud, saving 60 to 70%, then serves inference on AWS to leverage enterprise connectivity, combining cost savings with customer reliability. A gaming AI company dynamically shifts NPC behavior training between Azure and AWS based on hourly GPU price fluctuations, cutting annual infrastructure spend by 22%. A Fortune 500 enterprise demonstrated multi-cloud capability in negotiations, winning an additional 15% discount from its primary provider by proving it had credible alternatives. These stories reveal that arbitrage is not theoretical. It is already reshaping the economics of AI. Enterprises willing to experiment with cross-cloud strategies are reaping measurable financial advantages. To succeed with arbitrage, best practices must be followed. calculate true total cost of ownership, not just VM prices, but also egress fees, engineering time, and monitoring overhead. Automate placement decisions by combining FinOps data with orchestration platforms for real-time optimization. Develop an egress-aware data strategy, designing architectures that minimize unnecessary cross-cloud transfers. Leverage arbitrage in negotiations, using multi-cloud capability as bargaining leverage to win better discounts. Finally, document strategies as playbooks, predefined responses that execute when specific pricing thresholds are crossed. These playbooks transform arbitrage from opportunistic improvisation into repeatable, structured processes that scale. The story of cost arbitrage and multi-cloud AI can be distilled into four truths. First, arbitrage is a powerful financial lever, offering substantial savings for organizations running AI at scale. Second, GPUs, storage, network egress, and managed services are the primary areas where arbitrage delivers the highest return on investment. Third, success depends on automation and FinOps discipline, without which savings evaporate into complexity. And fourth, the financial impact is real. Properly executed arbitrage strategies can save enterprises millions annually, unlocking resources that fuel innovation rather than infrastructure spend. The ultimate message is clear. In the race to scale AI responsibly, cost arbitrage is no longer optional. It is a strategic necessity for any enterprise competing in the AI economy. Artificial intelligence is no longer a side experiment or a futuristic vision. It now underpins some of the most critical business and societal applications. Fraud detection systems prevent billions in losses, healthcare diagnostics guide life and death decisions, and recommendation engines shape customer engagement and revenue. When these systems go down, the consequences are immediate and severe. Regional outages are not rare. They can last hours or even days, and every minute of downtime compounds disruption. Beyond financial losses, outages damage trust, a currency far harder to restore. Disaster recovery, or DR, ensures that when failures strike, businesses maintain continuity, preserve regulatory compliance, and prevent erosion of customer trust. It is not a defensive luxury, but a core requirement for any enterprise that relies on AI as a business-critical asset. To design effective recovery strategies, enterprises must first understand the threats that could trigger them. Cloud region outages can arise from power failures, networking disruptions, or natural disasters affecting an entire geography. Data corruption poses another serious risk, whether from ransomware, insider error, or cascading software bugs undermining integrity. Infrastructure compromise, such as breaches in a model registry or feature store, can demand swift isolation to prevent systemic contamination. And compliance issues such as sudden regulatory changes may require rapid migration of data and workloads between regions. Recognizing this spectrum of threats highlights why DR must be multi-layered and adaptable. No single failure mode can be assumed, and resilience requires preparation for all of them. A robust DR strategy begins with measurable objectives. Two benchmarks dominate. RTO, or Recovery Time Objective, asks how fast systems can be restored after a disaster. RKEO, or Recovery Point Objective, asks how much data loss is acceptable during recovery. These metrics vary by workload. A financial fraud detection model may demand an RTO of under 15 minutes and a near-zero RPO, meaning downtime must be minimal and no transactions can be lost. A recommendation engine may tolerate a 2-hour RTO and an RPO of 1 to 2 hours, since temporary disruption is less catastrophic. By mapping recovery targets to business impact, organizations ensure resources are invested proportionately, prioritizing mission-critical workloads while optimizing costs elsewhere. Enterprises have several architectural options for disaster recovery, each balancing cost against recovery speed. Cold standby is the cheapest, keeping no active resources online and requiring manual spin-up during disaster. Its low cost comes at the expense of the longest recovery time, making it suitable only for non-critical workloads. Warm standby provisions pre-configured but scaled down resources / warm standby, striking a middle ground with moderate costs and medium recovery times. Hot active-active maintains full replicas across multiple regions, providing near instant recovery, but at the highest operational expense. Finally, hybrid approaches mix strategies, for example, running training in one region while replicating inference endpoints elsewhere to protect customer-facing services. The right architecture depends not on technology alone, but on business priorities. What balance of cost, speed, and risk is acceptable? At the heart of disaster recovery is data. Without synchronized, accessible data, failover is meaningless. Object storage replication through tools like S3 cross-region replication or GCS multi-region buckets ensures datasets remain accessible. Databases gain resilience with services such as Aurora Global Database, Spanner, or Cosmos DB, which replicate across geographies. Feature stores and vector databases, critical for AI systems, require both asynchronous and synchronous replication with configurable consistency. Yet, replication alone is insufficient. Organizations must conduct regular failover tests to validate RPO and RTO assumptions, ensuring that replication not only works in theory, but delivers in practice. The mantra is clear: test, verify, repeat. Without it, replication is just a hope, not a guarantee. A resilient DR strategy must ensure not just data availability, but also seamless traffic redirection. Global DNS failover with services like AWS Route 53 or Azure Traffic Manager automatically reroutes requests when a region fails. Anycast load balancing sends users to the nearest healthy region with real-time health checks. Network redundancy ensures VPNs and interconnects have failover paths, preventing bottlenecks during disaster. And certificate management verifies that TLS certificates are pre-validated across all regions, avoiding sudden authentication breakdowns during failover. In AI workloads, where users demand uninterrupted inference and low latency, network-level resilience ensures the transition from failure to recovery is invisible to end users. AI disaster recovery must extend beyond storage to cover the full ML lifecycle. Training jobs require checkpointing, allowing progress to resume in another region without losing days of computation. Model registries must mirror artifacts and metadata, enabling rapid redeployment elsewhere. Inference APIs must be multi-region and load balanced, with automated health checks ensuring quick failover. Shadow deployments, parallel replicas that validate behavior during transitions, add confidence that model performance remains intact under failover conditions. This end-to-end approach ensures DR is not just about keeping data safe, but about maintaining the entire AI pipeline in an operational state during crises. Hope is not a strategy. Disaster recovery plans that are never tested are fantasies, not protections. Regular chaos drills validate assumptions, exposing weaknesses before real failures strike. Regional outage simulations test resilience under worst-case conditions. Failover validation ensures DNS and routing mechanisms actually redirect as designed. Data integrity checks confirm replication lag stays within RPO limits and that datasets remain consistent. And team readiness drills, practicing playbooks under pressure, ensure that human operators know how to respond. The famous maxim applies here: everyone has a DR plan until it's time to execute it. Chaos drills transform plans into practiced, reliable responses. Disaster recovery does not occur in a regulatory vacuum. Data residency laws may require failover to remain within national boundaries, limiting DR options. Certification requirements under SOC 2, ISO 27001, or HIPAA demand formal DR documentation and proof of testing. Audit trail continuity ensures logs persist across failovers, maintaining compliance records, and data protection mandates require encryption during both replication and recovery. These constraints shape not just the architecture, but also the operational process of DR. Early collaboration between engineering, legal, and compliance teams ensures that DR strategies meet both technical and regulatory demands, avoiding costly missteps. Several best practices stand out from real world DR implementations. First, define clear recovery objectives. RTO and RPO must be explicit, workload specific, and tied to business impact. Second, automate failover to minimize human error and accelerate recovery. Third, replicate the full ML stack, not just data, to cover models, pipelines, and serving endpoints. Fourth, test regularly using chaos tools to validate readiness. And finally, balance cost and risk, selecting DR tiers that align with both workload criticality and budget. These practices transform DR from a static plan into a living discipline, building resilient AI infrastructure that survives regional failures while maintaining continuity. The core lessons of disaster recovery for AI are clear. DR is not optional, it is essential for business-critical AI systems. Multiple architectures exist: cold, warm, hot, and hybrid, offering flexibility to balance cost against recovery speed. A comprehensive strategy must include data replication, DNS failover, and regular chaos testing. And alignment with business requirements is non-negotiable. Compliance frameworks and service-level agreements must shape every DR plan. The ultimate truth is this: AI has become too important to fail. Disaster recovery ensures that even in the face of regional outages or crises, systems remain available, compliant, and trusted. In the enterprise world, the debate between on-premises and cloud has long dominated IT strategy. But the truth is, few organizations choose one extreme or the other. Instead, they blend the strengths of both environments, creating hybrid AI architectures. These setups acknowledge reality. Enterprises must balance compliance requirements, performance demands, and cost efficiency. Hybrid AI offers a middle ground: the ability to leverage existing investments in on-premise infrastructure while tapping into the elastic scalability of cloud services when demand spikes. It allows organizations to protect sensitive data while still innovating quickly, to serve latency-sensitive applications at the edge while running massive training jobs in elastic cloud clusters. In short, hybrid AI is not compromise. It is strategy, a deliberate blending of two worlds to maximize flexibility and control. Enterprises rarely commit exclusively to cloud or exclusively to on-prem. The reasons are compelling. Data residency and compliance drive many industries, healthcare, finance, and government, to keep sensitive information within local infrastructure. Latency-sensitive inference requires edge-based processing. Retail stores, autonomous vehicles, and factory floors cannot afford the round-trip delay of sending every request to a remote cloud. Cost control plays a role as well, since organizations have already invested millions into GPU and CPU clusters that remain valuable assets. And finally, burst workloads highlight the elasticity of hybrid design. Peak computation can spill into the cloud without the need to permanently over-provision local hardware. Together, these drivers explain why hybrid AI is not a temporary compromise, but a long-term enterprise strategy for balancing regulation, performance, and economics. Hybrid strategies come in distinct architectural patterns, each addressing different enterprise needs. One approach is training on-premises and serving in the cloud. Here, sensitive data remains local for compliance, but inference endpoints are distributed globally for scale and availability. Another approach flips the model: inference on-prem or at the edge, retraining in the cloud. This pattern provides low latency predictions where they are needed most, while the cloud offers elastic resources for retraining models. A third model is cloud bursting, where additional training capacity is borrowed from the cloud only during demand peaks. Finally, some organizations split workloads by data sensitivity, processing highly regulated or personally identifiable data locally while sending anonymized datasets to the cloud for further analytics. These patterns demonstrate the flexibility of hybrid AI. It is not a single design, but a toolbox of strategies adaptable to unique business pressures. On-premises infrastructure remains a cornerstone of hybrid AI. Compute infrastructure often consists of GPU and CPU clusters, either as bare metal or virtualized through VMware. Storage is provided by private object storage systems such as Ceph, MinIO, or NetApp, designed to handle sensitive data securely. Orchestration is critical. Kubernetes, whether through OpenShift, Rancher, or vanilla distributions, brings containerized workloads under consistent management, and security ties it all together. Enterprise IAM, firewalls, and gateways enforce strict access controls. These components give enterprises the confidence to host sensitive workloads locally while ensuring scalability through containerization and orchestration. On-prem is not disappearing. It is evolving, becoming a controlled, compliant foundation within a larger hybrid design. The cloud complements on-prem infrastructure with elasticity and global reach. For elastic GPU training, managed services like AWS SageMaker, Google Vertex AI, and Azure Machine Learning provide on-demand scale for heavy training jobs. For scalable model serving, Kubernetes deployments, managed APIs, and even serverless functions ensure inference endpoints adapt dynamically to load. The cloud also provides global distribution through CDNs, DNS services, and load balancers, ensuring users everywhere experience low latency, and managed data services, feature stores, vector databases, monitoring platforms provide ready-to-use infrastructure that accelerates deployment. Cloud services excel where elasticity, reach, and convenience matter most. In hybrid AI, they act as the flexible extension of local assets, ready to expand capacity, distribute workloads, and integrate with global ecosystems. The connective tissue of hybrid AI is networking. Private interconnects like AWS Direct Connect, Azure Express Route, and Google Cloud Interconnect provide high bandwidth, low latency links between environments. VPN tunnels secure smaller deployments or act as secondary paths. Service-to-service authentication ensures secure communication, with mutual TLS, MTLS enforcing trust across boundaries. Finally, unified service discovery provides consistent DNS and routing across hybrid endpoints, so services appear seamless regardless of where they run. Without robust connectivity, hybrid AI collapses into silos. With it, enterprises achieve the illusion of a single, coherent platform spanning on-premises and cloud. Networking is the hidden foundation that makes hybrid AI operationally viable. A practical example illustrates the power of hybrid AI. Step 1. Data collection. Raw data is captured and stored on-premises to satisfy compliance. Step 2. Feature engineering. Pre-processed or derived features are pushed into a cloud feature store. Step 3. Model training. In the cloud, anonymized or augmented data fuels elastic GPU clusters for rapid training. Step 4. Deployment. Model artifacts are synced back to on-prem for local inference, ensuring compliance and low latency. This flow demonstrates how hybrid design allows organizations to meet both regulatory demands and performance needs, keeping sensitive data secure while still harnessing cloud scale for training. Hybrid AI is not about compromise. It's about orchestration, ensuring the right task happens in the right place. Hybrid AI is powerful, but far from simple. Data gravity makes moving large data sets across environments expensive and time-consuming. Observability gaps appear when monitoring and debugging tools don't span on-prem and cloud uniformly. Security inconsistency arises from managing multiple IAM systems and secrets engines. Performance impact can creep in, with latency introduced by cross-environment network calls, and vendor lock-in risks loom when organizations rely too heavily on cloud-specific ML services. These challenges are real and, if unaddressed, can derail projects or inflate costs. Hybrid success requires deliberate planning, anticipating these pitfalls early in the architecture phase rather than retrofitting fixes after deployment. Thankfully, a strong ecosystem of tools supports hybrid AI operations. Kubeflow provides portable ML pipelines running consistently across environments. MLflow offers a hybrid-friendly model registry and experiment tracking system. Service meshes, such as Istio and Linkerd, enable secure, policy-driven traffic management across clusters. Data fabrics create unified access layers, abstracting data across on-prem and cloud. And hybrid Kubernetes management platforms, Google Anthos, Azure Arc, unify operations, governance, and monitoring across clusters. Together, these tools bridge the gaps, transforming hybrid AI from a patchwork of environments into a cohesive operational framework. Experience reveals clear best practices for hybrid AI. Data locality comes first. Workloads should be placed as close to their data as possible to minimize latency and egress costs. Consistent infrastructure, identical containerization, IAC, and orchestration ensures workloads can move easily between environments. Unified security demands standardization, with secrets and IAM centralized through platforms like HashiCorp Vault or Cloud KMS. End-to-end observability must be enforced, combining Prometheus, OpenTelemetry, and centralized logging across all environments. Finally, resilience planning is critical. Organizations must regularly test failover between cloud and on-prem, ensuring continuity when one side falters. The mantra is clear, designed for portability from day one. Hybrid AI succeeds only when consistency, security, and observability are embedded into every layer. The lessons of hybrid AI can be summarized in 4 themes. First, hybrid equals balance. It combines compliance, latency optimization, cost control, and scalability in a single architecture. Second, cross-environment pipelines define modern AI workflows, blending on-prem data with cloud scale. Third, portability is critical, with Kubernetes and MLOps stacks serving as the bridges between environments. And fourth, success depends on fundamentals, strong networking, unified IAM, portable pipelines, and robust observability. Hybrid AI is not the easiest path, but for enterprises balancing regulation, performance, and innovation, it is often the only viable one. Artificial intelligence is often thought of as something that lives in massive data centers, crunching information in the cloud. But increasingly, AI is moving closer to where data is generated, to cameras, sensors, vehicles, and even handheld devices. This paradigm is called Edge AI. At its core, Edge AI means running machine learning algorithms directly on or near the data source, whether on a device, a gateway, or an on-premises server, rather than sending everything back to a central cloud for processing. Real-world applications abound. Cameras monitoring hospital rooms, robots on factory lines, kiosks in retail stores, or autonomous vehicles navigating city streets. The critical advantage lies in reducing round trips to the cloud, enabling faster responses, greater privacy, and more efficient resource use. In short, Edge AI matters because it makes intelligence immediate, private, and affordable, qualities that cloud-only approaches often struggle to deliver. 4 forces are propelling enterprises toward Edge AI adoption. The first is latency, where sub-100 millisecond response times are essential for safety systems or seamless user experiences. The second is bandwidth. Sensor networks and cameras can generate terabytes of data per day, and streaming all of it to the cloud creates bottlenecks and ballooning costs. The third is privacy and compliance. Regulations like GDPR increasingly demand that sensitive data stay local, and keeping processing on-device ensures both security and compliance. Finally, resilience plays a crucial role. Edge AI systems continue functioning during connectivity outages while also reducing cloud egress costs. Taken together, these 4 drivers, latency, bandwidth, privacy, and resilience, create a compelling business case. Across industries, they are shifting AI from centralized models toward distributed intelligence deployed directly where work happens. Edge AI is supported by a layered technology stack. At the hardware level, we find devices like NVIDIA Jetson modules, x86 machines paired with GPUs or TPUs, ARM-based system on chips, and rugged industrial PCs. On top of this sits the operating system and runtime, often Linux distributions augmented with Jetpack, CUDA, OpenVINO, or platform-specific APIs like Apple's Core ML or Android's NN API. Models themselves are converted into portable formats. ONNX for interoperability, TensorRT engines for high performance, TF Lite for mobile, or Core ML for Apple ecosystems. Finally, at the application and management layer, developers expose inference via gRPC or REST services, orchestrate messaging locally, push over-the-air updates, and manage fleets at scale. This stack transforms raw hardware into intelligent, managed systems capable of performing real-time machine learning in the field. The promise of edge AI becomes clear when we examine its use cases. In computer vision, it powers defect detection on factory lines, checkout-free retail experiences, and PPE compliance monitoring for worker safety. In audio and natural language processing, it enables wake word detection, offline multilingual speech recognition, and voice kiosks in call centers. In industrial IoT, it supports predictive maintenance and anomaly detection in real time, allowing machines to warn of faults before they fail. And in mobility, it underpins autonomous navigation, vehicle-to-everything communication, and advanced driver assistance systems. These examples demonstrate that edge AI thrives wherever immediate decisions are required, data volumes are massive, or connectivity cannot be guaranteed. It shifts intelligence from the cloud to the front lines of interaction, where speed and reliability matter most. It is tempting to think of edge and cloud AI as rivals, but the truth is they are complementary. Edge AI handles real-time inference, filtering, and pre-aggregation of data close to its source, minimizing latency and bandwidth consumption. Cloud AI, on the other hand, manages heavy lifting, training large models, coordinating fleets of devices, storing global registries, and running advanced analytics. Synchronization bridges the two. Edge devices send telemetry upward for analysis, while the cloud pushes optimized models and updated policies downward. The optimal AI architecture is therefore hybrid. It leverages the cloud for what it does best, scale and heavy compute, while relying on the edge for immediacy and resilience. The future of AI is not edge or cloud, but edge and cloud working in concert. Deploying AI at the edge is not without challenges. Compute memory and power limitations mean that models must be smaller and more efficient than their cloud-deployed counterparts. Intermittent connectivity requires offline-first design principles so that systems continue working during outages. Hardware heterogeneity complicates development, since edge environments include everything from ARM chips to GPUs and NPUs, requiring portable solutions and specialized compilers. Finally, physical security cannot be ignored. Devices deployed in the field are vulnerable to tampering and theft. These constraints highlight that edge AI requires a different design mindset. Success depends not just on porting existing models, but on rethinking workflows to account for resource limits, network gaps, and real-world physical risks. Meeting the constraints of edge environments requires aggressive optimization. Techniques can shrink models by up to 90% without unacceptable accuracy loss. Quantization converts floating point operations into INT8 or FP16, accelerating inference with frameworks like TensorRT, TF Lite, or OpenVINO. Pruning and distillation reduce parameters or transfer knowledge from large teacher models into smaller student models, retaining accuracy while cutting resource demands. Accelerator-aware compilers like TVM or XLA tune models for specific hardware targets, squeezing out maximum efficiency. Finally, pipeline optimizations such as Operation Fusion, zero-copy memory transfers, and asynchronous I/O further streamline performance. This toolkit transforms heavyweight cloud models into lean, efficient edge deployments that fit within tight power and memory envelopes while maintaining usability. Moving from a proof of concept to production requires operational rigor. Packaging is the first step, Models and code are containerized with Docker or bundled into lightweight packages optimized for constrained devices. Orchestration follows using lightweight Kubernetes distributions, such as K3s or micro K8s, or fleet managers like Balena and Azure IoT Edge. Update mechanisms must support staged rollouts, blue-green deployments, and automatic rollback to minimize risk. Finally, observability ensures visibility into the field. Local logs and metrics are collected and forwarded to the cloud using Prometheus or OpenTelemetry. At scale, these practices ensure not only that edge models are deployed widely, but also that they remain manageable, observable, and upgradable across thousands of devices. Security is non-negotiable for edge AI. At the hardware level, secure boot mechanisms with TPMs or trusted execution environments prevent tampered devices from running unverified code, while full disk encryption protects data at rest. In communications, mutual TLS ensures device-to-cloud traffic is authenticated and encrypted, with certificates rotated regularly. For identity, scoped tokens and least privilege principles limit what devices and services can access. Supply chain security is equally critical. Signed containers, SBOMs, and provenance tracking ensure that only trusted models and artifacts are deployed. Together, these practices create a layered defense, protecting edge systems against tampering, interception, and exploitation while upholding compliance requirements in sensitive industries. Edge AI is not only about technology, it's also about economics. Cost reduction strategies include minimizing cloud egress fees and GPU compute costs by running inference locally. Hardware efficiency is achieved by right-sizing accelerators, ensuring workloads run on the smallest feasible device without overspending on premium hardware. Hybrid analytics saves bandwidth by uploading only processed features or events rather than raw video or sensor streams. Return on investment can be measured through latency service level objectives, accuracy of predictions, uptime, and cost per inference event. When designed correctly, Edge AI does not merely perform better, it saves money, reduces dependence on expensive centralized compute, and delivers measurable business value. The lessons of Edge AI can be distilled into a few clear points. First, Edge AI delivers real-time, private, resilient, and cost-effective intelligence by processing data closer to its source. Second, success depends on designing for constraints, optimizing models for limited resources, and ensuring offline resilience. Third, the strongest architectures embrace a hybrid approach, combining edge immediacy with cloud scalability. Fourth, infrastructure investments in security, observability, and update mechanisms are non-negotiable from the start. And finally, the best way to begin is small, with a focused proof of concept solving one business problem, proving value, and scaling outward. Edge AI is not a futuristic dream. It is a present-day necessity, reshaping how organizations deliver intelligence in a connected world. Artificial intelligence is no longer confined to distant data centers. Increasingly, it is moving closer to the very places where data is generated: retail stores, hospital rooms, traffic intersections, and urban infrastructure. This shift is called Edge AI, the practice of running inference and decision-making directly at or near the data source. The value is profound. By processing data locally, organizations enable faster decisions, enhanced privacy, and smarter operations without depending entirely on the cloud. For industries like retail, healthcare, and smart cities, the implications are transformative. Each of these domains has unique requirements for latency, privacy, cost, and safety, which makes centralized architectures insufficient. Edge AI addresses these needs by combining local inference with the shared benefits of real-time response, reduced cloud dependency, and greater compliance. At its core, Edge AI is about balance, protecting sensitive data while still harnessing AI's power, all with minimal latency. Retail is a natural fit for Edge AI because it thrives on immediacy and personalization. Consider checkout-free stores, where computer vision identifies products placed into baskets, eliminating queues and friction at the point of sale. Customers simply walk out, and payment happens seamlessly in the background. Beyond transactions, Customer analytics provide deep insights by tracking foot traffic patterns, analyzing dwell time, and even gauging sentiment through facial expressions. Retailers optimize layouts and promotions in real time. Inventory management benefits as well. Smart shelves detect when stock is low or when potential theft occurs, generating alerts instantly without sending video streams to the cloud. Finally, personalization brings it all together. Digital signage adapts content dynamically based on nearby shoppers, offering targeted promotions without transmitting identifiable data externally. In retail, Edge AI enhances efficiency, reduces operational costs, and delivers customer experiences that feel natural, immediate, and engaging. Why does retail in particular need Edge AI? The drivers are clear. Latency is critical. Milliseconds matter during checkout. A cloud round trip, even of a few hundred milliseconds, disrupts the smoothness customers expect. Privacy is another major factor. CCTV footage and customer analytics involve highly sensitive data. Processing locally ensures this information never leaves the premises unnecessarily. Cost considerations also loom large. Streaming high-definition video from thousands of stores to the cloud would be financially prohibitive. Finally, customer experience demands responsiveness. Modern shoppers expect seamless interactions, doors that unlock instantly, shelves that recognize activity, and kiosks that respond without delay. Retail Edge AI delivers on these expectations, making intelligent retail possible at scale. Healthcare demonstrates some of the most critical applications of Edge AI, where the stakes are not convenience, but life itself. Bedside monitoring enables continuous analysis of patient vitals, detecting early warning signs of deterioration without relying on constant connectivity. Medical imaging systems equipped with on-device AI can triage scans immediately, prioritizing urgent cases for radiologists and saving precious minutes in emergencies. Smart medical devices, from infusion pumps to wearable health trackers, embed machine learning to operate autonomously, reducing clinician burden and catching anomalies in real time. In telemedicine, Edge AI ensures low-latency video and audio analysis, enabling responsive diagnostics even in areas with limited bandwidth. Each of these cases illustrates the transformative power of Edge AI, making care proactive, responsive, and resilient in environments where network dependency is unacceptable. Healthcare's reliance on Edge AI is driven by four forces. First is compliance. Regulations like HIPAA and GDPR mandate that protected health information must remain under strict access controls. Local processing ensures data sovereignty. Second is reliability. Patient monitoring and critical care systems cannot fail during network outages. They must continue to function independently. Third is safety. Decisions made in healthcare can be life-critical, and deterministic performance without cloud dependence is mandatory. Fourth is integration. Hospitals already rely on extensive IT infrastructure, PACS imaging systems, and medical devices. Edge AI must integrate seamlessly with these systems to be viable. For healthcare, Edge AI is not simply beneficial, it is essential for safe, compliant, and reliable care delivery. Smart cities epitomize the scale of Edge AI. Traffic management uses intelligent detection to adjust signal timing dynamically, cutting commute times by as much as 25%. Public safety improves through anomaly detection on surveillance feeds, enabling local alerts, without streaming endless video to central servers. Smart lighting adjusts brightness based on pedestrian density, weather, and time of day, conserving energy while improving safety. And environmental monitoring relies on distributed sensors to track air quality, noise, and energy usage, enabling data-driven urban planning. In smart cities, Edge AI scales to thousands of endpoints, managing petabytes of data locally and making decisions that improve daily life for millions of residents. The push for Edge AI in urban environments is propelled by scale, latency, bandwidth, and sovereignty. First, thousands of sensors and devices generate enormous data volumes daily. Without local processing, centralized systems would collapse under the weight. Second, latency matters. traffic systems, and public safety applications demand responses in under 100 milliseconds, delays that cloud round trips cannot support. Third, bandwidth reduction is essential. Processing at the edge reduces network traffic by as much as 90% compared to streaming raw video and sensor data. Finally, data sovereignty is non-negotiable. Municipalities increasingly mandate that citizen data remain within jurisdictional boundaries. These drivers make edge AI not just desirable, but indispensable for building resilient, efficient, and compliant urban systems. Despite its promise, edge AI faces common hurdles across industries. Hardware heterogeneity complicates deployments. Devices range from powerful gateways to constrained IoT sensors, demanding flexible frameworks. Model optimization is necessary to fit cloud-scale AI into edge environments, where compute, memory, and power are limited. Security and trust are paramount, as devices deployed in public or exposed environments are vulnerable to tampering, model theft, and breaches. Finally, fleet management at scale becomes a logistical challenge. Updating, monitoring, and ensuring consistency across thousands of devices requires robust orchestration systems. These challenges remind us that edge AI is not a plug-and-play technology. It demands discipline, specialized tooling, and continuous innovation to succeed at scale. The story of edge AI use cases can be distilled into 4 key points. First, edge AI is the foundation of real-time, private, cost-efficient processing across industries. By moving computation closer to the source, organizations unlock performance, privacy, and efficiency. Second, retail is being transformed with frictionless shopping, customer analytics, and personalized experiences all made possible by local inference. Third, healthcare is innovating, meeting compliance mandates and delivering life-critical reliability through bedside monitoring, imaging triage, and autonomous devices. Fourth, smart cities are evolving, with edge AI providing the scale and immediacy required for modern urban infrastructure while preserving sovereignty and bandwidth. The overarching message is this: edge AI is no longer optional. As regulations tighten, latency demands rise, and distributed systems grow. Edge AI becomes a strategic necessity, the very architecture of the intelligent future. Artificial intelligence has long been associated with data centers and cloud platforms. Yet increasingly, the demand for intelligence is shifting outward, closer to where data is created, in cameras, robots, drones, kiosks, and countless IoT devices. This is the world of edge AI, and at the heart of it sits NVIDIA's Jetson platform. Jetson brings GPU-accelerated computing into compact embedded modules, delivering supercomputer-level performance directly to the edge. This capability transforms what's possible in real-time applications, analyzing video streams as they happen, enabling autonomous robots to navigate complex environments, or allowing smart city systems to make decisions without waiting for cloud responses. The power of Jetson lies in its design philosophy, combining ARM CPUs with CUDA-capable GPUs in small, efficient form factors that allow intelligence to live wherever it's needed most. In essence, Jetson democratizes AI at the edge, bringing once impossible workloads into everyday devices. Jetson is NVIDIA's purpose-built hardware platform for edge AI. It marries ARM-based CPUs with CUDA-capable NVIDIA GPUs, packaging them into modules small enough for embedded systems, yet powerful enough to deliver supercomputer-class performance. Optimized particularly for vision, robotics, and autonomous systems, Jetson devices are designed to handle real-time processing directly on location. This means drones can adjust their flight path mid-air. Robots can react instantly to obstacles, and industrial cameras can detect defects as products roll off the line. Jetson supports the most widely used AI frameworks: PyTorch, TensorFlow, ONNX, ensuring that models trained in the cloud can be seamlessly deployed at the edge. This portability, combined with immense efficiency, makes Jetson the go-to platform for engineers, researchers, and enterprises aiming to unlock AI in constrained environments. Several reasons explain why Jetson has become the leading-edge AI platform. First, GPU acceleration. With dedicated CUDA cores, Jetson modules process neural networks far faster than CPU-only alternatives, making real-time inference achievable. Second, compactness and power efficiency. With modules consuming between 5 and 60 watts, Jetson devices fit easily into drones, robots, or IoT enclosures without demanding data center levels of power. Third, scalability. A Jetson family ranges from entry-level modules for hobbyists and prototyping to industrial-grade units powering advanced robotics. Finally, the Jetpack SDK provides a complete, pre-packaged development environment, including drivers, CUDA, TensorRT, and cuDNN, all optimized to work seamlessly with Jetson hardware. Together, these elements mean developers can focus less on integration headaches and more on innovation. Jetson is not just hardware. It is a carefully crafted ecosystem purpose-built for AI at the edge. The Jetson family spans a continuum of performance, power, and scale. At the entry point is the Jetson Nano, designed for students, hobbyists, and early-stage prototypes, perfect for learning AI fundamentals or testing simple edge applications. Moving upward, the Jetson TX2 offers mid-tier performance, popular in drones and vision-based applications, striking a balance between efficiency and compute power. The Jetson Xavier NX represents a leap in compact but professional-grade performance, ideal for robotics and deployed inference. Above this sits the AGX Xavier, designed for enterprise-grade robotics and autonomous machines demanding high throughput and advanced perception. Finally, the latest Orin series delivers cutting-edge performance with unprecedented TOPS numbers, making it the premier choice for modern AI workloads. This spectrum ensures there is a Jetson device suitable for virtually any edge AI application, from tinkering to enterprise deployment. The Jetson product line demonstrates extraordinary scalability. At the low end, the Nano delivers around 0.5 TFLOPS of AI compute with 128 CUDA cores and 2 to 4 gigabytes of memory, consuming as little as 5 watts. At the mid-range, the Xavier NX delivers 21 TOPS with 384 to 512 CUDA cores paired with 8 to 16 gigabytes of memory. At the high end, the AGX Orin pushes into the realm of 275 TOPS, boasting over 2,000 CUDA cores and up to 64 gigabytes of LPDDR5 memory, while consuming between 15 and 60 watts depending on the workload. Across this family, form factors remain compact, ranging from 70 by 45 millimeters to 100 by 87 millimeters. What stands out is not just raw performance, but performance per watt. Each generation delivers more power efficiency, enabling previously unthinkable AI deployments at the edge. The Jetson family doesn't just scale in capability, it scales intelligently, balancing compute, energy, and cost for diverse needs. Hardware alone is not enough. Jetson's success comes from its rich software ecosystem. The Jetpack SDK provides the operating system, drivers, CUDA toolkit, cuDNN, and TensorRT, ensuring optimized inference performance out of the box. DeepStream SDK offers a powerful video analytics pipeline, allowing multi-stream video processing at scale. Essential for smart city and surveillance applications, the TAO toolkit empowers developers to perform transfer learning and fine-tune pre-trained models on domain-specific datasets with minimal effort, accelerating adaptation. Meanwhile, the Isaac SDK supports robotics development, providing simulation environments, navigation libraries, and perception modules. Together, these tools form a comprehensive software stack, enabling developers to prototype, optimize, and deploy AI applications quickly. The ecosystem transforms Jetson from a chip into a full-fledged platform, one where hardware and software are harmonized to accelerate edge AI adoption. Jetson powers an expansive array of use cases across industries. In computer vision, Jetson modules support real-time object detection, defect inspection, and quality control in manufacturing, often analyzing multiple camera streams simultaneously. In robotics, they enable autonomous navigation, SWAM, simultaneous localization and mapping, and precise manipulation through multi-sensor fusion. In healthcare, Jetson modules form the backbone of portable imaging devices, AI-driven diagnostic assistants, and bedside monitoring systems, all while preserving patient privacy through local data processing. In retail and smart cities, Jetson supports intelligent surveillance, customer analytics, traffic monitoring, and crowd management. These applications highlight Jetson's versatility, a platform robust enough for mission-critical industries, yet compact enough for embedded deployments. Wherever real-time intelligence is required, Jetson devices are at the forefront. Why choose Jetson over competing edge AI boards? The answer lies in performance and ecosystem. First, GPU acceleration. Jetson dramatically outperforms CPU-only boards when running neural networks, thanks to CUDA cores designed for parallel workloads. Second, the CUDA and TensorRT ecosystem. NVIDIA has invested heavily in hardware-accelerated libraries that optimize inference far beyond what generic hardware can achieve. Third, community and support. Jetson benefits from a massive developer community, extensive documentation, and enterprise-grade support options from NVIDIA, lowering the barrier to entry. Fourth, scalability. The same software stack works across the entire Jetson product family, allowing developers to scale applications from the Nano to the Orin without re-architecting their code. Competing alternatives may address niches, but none match Jetson's blend of power, ecosystem, and long-term support. Jetson is not just about prototypes. It is designed for production. Hardware integration is streamlined, with modules easily embedded into custom carrier boards and OEM designs thanks to standardized interfaces and pinouts. For operations, fleet management is critical. NVIDIA Fleet Command and Kubernetes-based orchestration enable enterprises to manage thousands of devices remotely, monitoring health, performance, and workload allocation. Software updates are supported via secure over-the-air delivery, ensuring that models, applications, and system software remain current across fleets. Applications can be packaged in containers for reproducibility and portability, simplifying deployment pipelines. Finally, security is embedded into the hardware with secure boot, encrypted storage, and hardware root of trust, protecting sensitive AI models and ensuring integrity. These features prove Jetson is ready not just for labs, but for the field, where scalability and security matter most. The NVIDIA Jetson platform is best understood as a compact powerhouse designed to bring AI to the edge. It delivers industry-leading GPU acceleration, making real-time inference feasible in constrained environments. The product family ranges from the entry-level Nano to the enterprise-grade Orin, scaling to meet any workload or power envelope. A comprehensive software ecosystem, Jetpack, DeepStream, Tau, and Isaac SDKs ensures rapid development and optimization. Jetson thrives in domains like vision, robotics, healthcare, and smart cities, where immediacy, privacy, and resilience matter. Its advantages over alternatives lie in performance, ecosystem support, and scalability. Finally, its deployment readiness, from hardware integration to fleet management and security, makes it a production-grade solution. The overarching message is clear. Jetson is not just another edge board. It is a full ecosystem, purpose-built to accelerate AI wherever intelligence is needed most. Before you can unlock the full potential of your NVIDIA Jetson device, you need the right software foundation. That foundation is Jetpack SDK, NVIDIA's all-in-one software stack, purpose-built for edge AI. Think of Jetpack as the bridge between hardware and applications, the glue that enables CUDA cores, deep learning accelerators, and multimedia drivers to work together seamlessly. With Jetpack installed, a Jetson device stops being just a compact board and transforms into a complete edge AI workstation. This guide provides a structured pathway for developers and engineers, from understanding what Jetpack is to installation, configuration, troubleshooting, and validation. The goal is clear. By the end, your Jetson will be ready not just to boot, but to run demanding AI workloads efficiently and reliably, laying the groundwork for real-world deployment. Jetpack SDK is NVIDIA's comprehensive software stack for Jetson devices. It includes everything needed to run AI at the edge. At its core is an Ubuntu-based operating system image, providing stability and familiarity for developers. Integrated into this OS are the tools that power modern AI. CUDA, NVIDIA's parallel computing framework, cuDNN, a deep learning library optimized for GPUs, and TensorRT, a high-performance inference engine that squeezes every ounce of efficiency from neural networks. Beyond this, Jetpack ships with the DeepStream SDK for video analytics and a full suite of multimedia APIs and drivers for handling sensors, cameras, and encoders. In short, Jetpack is not just an operating system, it is a complete AI software environment designed to make Jetson devices deployment-ready out of the box. Why invest time in Jetpack rather than piecing together libraries manually? The answer lies in optimization, performance, and simplicity. First, Jetpack is custom-tuned for Jetson hardware. Every driver, library, and kernel patch is designed to maximize efficiency. Second, it ensures maximum GPU performance, unlocking the parallel processing power of CUDA cores to handle AI inference at scale. Third, it offers simplified development, with pre-optimized libraries that streamline work in computer vision, natural language processing, and robotics. And finally, Jetpack receives regular updates, staying aligned with the broader CUDA ecosystem so developers can access the latest features and performance improvements. Jetpack matters because it turns a Jetson device into a turnkey AI platform, saving countless hours of configuration and delivering results faster. There are two main ways to install Jetpack. The first is via the NVIDIA SDK Manager. This method involves flashing the Jetson device with a complete Jetpack image from a host Ubuntu PC. It provides full control, allowing developers to install additional components post-flash, and ensures the latest version is always in use. The second option is to use pre-flashed developer kits. These come with Jetpack already installed and can be updated via the package manager. For major upgrades, the SDK manager remains the recommended path. The choice depends on context. SDK manager for flexibility and control, or pre-flashed kits for convenience and speed. Either way, the outcome is the same: a Jetson device equipped with the full Jetpack stack, ready for AI. Preparation begins with hardware. First, choose your platform, whether Jetson Nano, Xavier, or Orin. Select based on your performance needs. Second, gather the necessary peripherals: an HDMI monitor, USB keyboard and mouse, and either a microSD or eMMC module for storage. Third, power is crucial. Underpowered adapters cause instability, so use NVIDIA's recommended supply, typically 5 volts, 4 amps, or higher depending on the model. Finally, connectivity must be planned. Ensure you have an Ethernet cable or a compatible Wi-Fi adapter, since updates and package downloads require reliable network access. With hardware, power, and connectivity in place, your Jetson is ready for installation. Installation begins on the Ubuntu host PC. First, update the system, sudo apt update. Then download the SDK Manager package from NVIDIA's developer site. Install with sudo apt install /sdkmanager_latest.deb. Once installed, launch it with the command SDK Manager. A critical note: SDK Manager requires Ubuntu 18.04 or newer. It will not run on other Linux distributions or operating systems. The Manager provides a graphical interface that simplifies the flashing process, presenting options for Jetson models, Jetpack versions, and add-on components. SDK Manager is your control center, orchestrating every aspect of the Jetpack installation. The most important step is flashing Jetson with a Jetpack image. Begin by connecting the hardware. Use a micro USB or USB-C cable to connect Jetson to the host PC depending on your model. Put the Jetson into recovery mode by holding the recovery button while powering on. Once connected, launch SDK Manager, select your device model, and choose the Jetpack version you wish to install. Then begin the flashing process. This installs the Ubuntu base OS, CUDA, cuDNN, TensorRT, and all necessary drivers. At the end of this process, your Jetson has transformed from bare hardware into a fully functioning AI development platform. After flashing, power on the Jetson and complete the initial setup. Configure your username and password, and set up network settings for Wi-Fi or Ethernet. Immediately perform a full system update with sudo apt update and sudo apt upgrade -y. This ensures your system has the latest security patches and package updates. During setup, you will be prompted to accept NVIDIA's license agreements. Once completed, your device is operational, with Jetpack now running as the software foundation. The first boot setup is about personalization and bringing the system fully online. Verification is essential to confirm Jetpack is working correctly. Begin with CUDA. Run nvcc-version to check that the compiler version matches your Jetpack. Next, confirm TensorRT with Python 3-c import TensorRT print TensorRT current version. Finally, test real workloads. Run deep-stream demos or use camera capture examples to ensure multimedia and AI pipelines function properly. This verification stage provides confidence. Your Jetson is not just booted, but correctly configured, optimized, and ready for AI application deployment. With Jetpack verified, you can extend functionality, install PyTorch and TensorFlow builds optimized for Jetson from NVIDIA's repositories to enable deep learning workflows. Enable Jetson.gpio for connecting sensors and IoT devices. Fine-tune performance by adjusting swap space and power settings to better handle heavy inference loads. Finally, explore the Jetson Zoo, a community-maintained repository offering additional AI libraries and optimized packages. These extras enhance your Jetson beyond the baseline, tailoring it for advanced robotics, computer vision, or IoT innovation. Inevitably, issues may arise during installation, but most have straightforward solutions. Power problems manifest as random shutdowns or instability, often caused by underrated adapters. The fix is to use NVIDIA's recommended supply. Storage limitations can derail flashing if the SD card or eMMC is too small. Always use at least a 32GB Class 10 micro SD card or larger eNMC module. Software compatibility issues may surface as flashing errors or SDK manager crashes. These are usually resolved by updating SDK manager or ensuring your host PC runs a supported Ubuntu version. For persistent issues, NVIDIA's documentation and community forums provide guidance and solutions. The key is preparation and patience. Most issues are solvable with the right information. The journey of installing Jetpack SDK on Jetson boils down to 4 key lessons. First, Jetpack is the foundation. Every Jetson AI project begins here, as it provides the software backbone. Second, installation options matter. SDK Manager offers flexibility and control, while pre-flashed kits provide speed and convenience. Third, verification is non-negotiable. Always test with scripts and demos before deploying production workloads. And fourth, troubleshooting is part of the process. Anticipate common issues and leverage documentation and forums to overcome them. With Jetpack installed and configured, your Jetson device is no longer just hardware. It is a ready-to-use AI powerhouse, prepared for the challenges of edge computing. Artificial intelligence workloads can live in many places, on the edge, in the cloud, or in some hybrid combination of both. Where they live matters deeply. It defines not just performance, but also cost, compliance, and user experience. Latency requirements dictate whether a system can wait seconds or must react in milliseconds. Cost and scalability considerations push us to weigh capital investment against operational expense. Privacy and compliance bring in regulatory realities. Can sensitive data leave the device, or must it remain local? And ultimately, user experience ties it all together. Reliability, availability, and responsiveness define whether an AI solution delights or disappoints. There is no universal answer. The best deployment model is always contextual, a reflection of technical requirements and business constraints. That is why this trade-off matters. Getting it wrong undermines trust and efficiency, but getting it right unlocks value at scale. Edge AI shines in scenarios where immediacy and privacy are paramount. Ultra-low latency defines its biggest strength, delivering sub-100 millisecond responses essential for autonomous systems, critical infrastructure, and immersive user interactions. Offline operation is another benefit, enabling AI-powered systems to function in remote areas, disconnected environments, or during network outages. Edge AI also embodies privacy by design, by keeping data local. It minimizes exposure of sensitive information, reduces compliance overhead, and ensures sovereignty. Finally, bandwidth savings make Edge AI economical. Instead of streaming raw video or sensor data to the cloud, Edge systems process locally and send only summaries or insights, cutting costs dramatically. Taken together, these qualities position Edge AI as indispensable wherever real-time responsiveness, data sensitivity, or bandwidth constraints define the environment. Yet Edge AI is not without challenges. Resource constraints limit the size and complexity of models, requiring specialized optimization such as quantization, pruning, and distillation. Deployment challenges emerge at scale, distributing updates, managing versions, and ensuring consistency across thousands of devices is far harder at the edge than in centralized clouds. Device heterogeneity adds friction as a diverse ecosystem of chips, accelerators, and operating systems complicates testing and optimization. And security vulnerabilities loom large, with devices physically deployed in the field. Risks of tampering, theft, or adversarial attacks increase. These weaknesses do not negate the value of Edge AI, but they remind us that it is not a silver bullet. To succeed, Edge deployments require disciplined engineering, strong fleet management, and robust security practices. If Edge offers immediacy, cloud offers scale. Cloud AI platforms provide the computational muscle for today's most advanced models, from billion-parameter language models to complex multimodal systems. Their defining feature is elastic scalability. They scale up for massive training runs and scale down for lighter inference loads, matching demand efficiently. They centralize resources with a unified model registry, enabling version control, automated pipelines, and continuous integration within a single MLOps ecosystem. Fleet-wide management becomes straightforward. Updates, monitoring, and troubleshooting are all orchestrated from one control plane. Finally, the cloud provides access to advanced hardware, GPUs, TPUs, and accelerators, without capital expenditures or the burden of maintenance. This operational simplicity, paired with vast compute, makes cloud AI indispensable for workloads that are heavy, dynamic, or experimental. Despite its power, cloud AI faces hard limits. Latency constraints are fundamental. The round trip to cloud servers, often 100 to 500 milliseconds, is too slow for safety-critical or interactive use cases like autonomous driving or industrial safety. Cost inefficiencies arise from streaming massive raw datasets, video, audio, sensor telemetry, to centralized servers, with expenses compounding across storage, bandwidth, and compute. Privacy vulnerabilities increase as transmitting sensitive data off-site complicates compliance and elevates risk. And finally, network dependencies create fragility. Cloud-only systems falter when internet connectivity fails, making them unsuitable for mission-critical applications in unstable environments. These limitations reveal that while the cloud is powerful, it is not universally appropriate. It excels when immediacy and sovereignty are secondary, but it struggles when they are primary. For many enterprises, the answer is not edge or cloud, but both working together. Hybrid approaches combine strengths while mitigating weaknesses. At the edge, devices deliver real-time inference, data filtering, and privacy-preserving anonymization, all while continuing to operate during connectivity gaps. In the cloud, systems aggregate datasets for training, manage global registries, and orchestrate fleets. A retail checkout-free store illustrates this well. Cameras at the edge process customer movements in sub-50 milliseconds, while the cloud aggregates behavior across stores, updates recognition models, and handles inventory analytics. Hybrid deployments enable a division of labor. Immediacy at the edge, scale in the cloud. It's a pragmatic model, not theoretical, but already dominant across industries. The hybrid pattern plays out across industries. In healthcare, diagnostic imaging benefits from edge-based preliminary analysis for immediate insights, while the cloud anonymizes and aggregates data for retraining to improve accuracy. In autonomous vehicles, edge intelligence handles critical driving decisions, while the cloud provides fleet learning, sharing road conditions and optimizing routes across vehicles. In smart cities, edge devices process real-time traffic to optimize signal timing, while the cloud analyzes broader mobility patterns to guide infrastructure planning. In retail, edge AI personalizes in-store experiences, while cloud systems run recommendation engines based on cross-store data. These examples demonstrate the hybrid approach is not a compromise. It is a practical architecture aligning technical realities with business needs. When choosing between edge, cloud, or hybrid, enterprises must weigh four critical factors. Latency tolerance. If responses must occur in 10 to 100 milliseconds, edge is mandatory. If seconds suffice, cloud is viable. Data sensitivity. Highly regulated or personally identifiable data should remain local, while non-sensitive or anonymized data can safely flow to the cloud. Scale and cost dynamics. Edge relies on dedicated hardware sized to workload, while the cloud offers elastic resources but with ongoing costs. Connectivity profile. Intermittent or bandwidth-constrained environments demand edge. Robust, high-bandwidth networks allow cloud reliance. Each decision flows from these trade-offs. The optimal deployment model emerges not from generic best practices, but from a tailored match between requirements and constraints. The trade-offs between edge and cloud AI can be distilled into clear lessons. Edge excels at speed, privacy, and resilience, providing sub-100 millisecond responses and continuous operation during outages. Cloud excels at scale, manageability, and flexibility, powering massive models and centralized control. Hybrid dominates in practice, blending edge and cloud to achieve 99.9% availability, 40 to 60% bandwidth savings, and true 24/7 operation. Ultimately, deployment decisions must align with three anchors: service-level agreements, ensuring promised performance and availability; compliance obligations, respecting data sovereignty and security; and return on investment, balancing hardware, network, and operational costs. The strategic message is simple. Don't choose edge or cloud by default. Choose based on what your use case demands. In the world of enterprise AI, alignment is everything. In today's rapidly evolving AI landscape, one challenge remains persistent. How do we take models trained in the cloud and deploy them seamlessly across an increasingly diverse set of devices? This is where ONX runtime for edge models comes into play. ONX, short for Open Neural Network Exchange, provides a standardized, open format for representing machine learning models. The runtime, maintained by Microsoft, brings those models to life by running them efficiently across a wide range of hardware, from x86 and ARM processors to GPUs, NPUs, Jetson boards, and even mobile devices. The vision is ambitious yet practical. Train once, deploy anywhere. For enterprises, this ensures that investments in training workflows are not locked into a single framework or hardware vendor. For developers, it means reduced friction, fewer rewrites, and the confidence that models will run reliably at the edge, where resources are constrained but performance matters most. The Open Neural Network Exchange, ONNX, is more than just another file format. It is a movement toward interoperability in AI. Built as an open standard, ONNX allows models trained in different frameworks to be represented in a unified way. This universality solves a long-standing challenge. Historically, a PyTorch-trained model could not easily be used in TensorFlow, and vice versa. With ONNX, those walls fall away. Frameworks including PyTorch, TensorFlow, scikit-learn, and Hugging Face all support ONNX exports. The value proposition is clear. Train in one framework and deploy anywhere. For edge AI, ONNX takes this one step further by being lightweight and optimized for inference. Unlike heavier formats, ONNX models can be stripped of redundancies and tuned for constrained environments, making them ideally suited for real-time applications on devices with limited power and memory. If ONNX is the format, then ONNX Runtime is the engine that powers it. Developed and maintained by Microsoft, ONNX Runtime is a cross-platform inference engine capable of running on everything from CPUs and GPUs to NPUs, Jetson devices, and embedded hardware. Its versatility is reflected in its execution providers, specialized integrations for different hardware backends. For example, it can use CUDA or TensorRT for NVIDIA devices, DirectML for Windows accelerators, and NNAPI for Android phones. This flexibility allows developers to write code once and deploy it anywhere, confident that the runtime will optimize execution for the underlying hardware. Additional features like quantization for efficiency and cross-language APIs in Python, C++, Java, and C# make ONNX Runtime not just portable, but also developer-friendly. In short, it's the universal runtime for a heterogeneous AI world. ONNX Runtime stands out for edge AI deployments because of 4 key advantages. First, portability. A single ONNX model can run across different hardware platforms with no modification, eliminating silos and accelerating time to deployment. Second, performance. ONNX Runtime includes optimized kernels that take advantage of hardware acceleration, ensuring that models run efficiently even under strict resource limits. Third, flexibility. Unlike specialized runtimes that only support deep learning, ONNX supports both deep learning and traditional machine learning models in the same format. Fourth, compatibility. ONNX integrates seamlessly with TensorRT, OpenVINO, CoreML, and other edge ecosystems, making it an adaptable partner for multi-device strategies. These traits combine to make ONNX the natural choice for organizations deploying AI across fleets of heterogeneous devices, where consistency and reliability are non-negotiable. Exporting models to ONNXS is intentionally straightforward. Consider a PyTorch example with the ResNet 18 model. With just a few lines of code, you can generate a .onxs file that is portable across frameworks and devices. Using torch.onxs export, developers provide the model a dummy input matching the expected shape, typically batch size, channels, height, width for image models, and desired input and output names. The result is a self-contained onxs file ready for deployment. This simplicity matters. Instead of complicated conversion processes, developers can bridge the gap between training and deployment in minutes. The output, ResNet 18.onxs, becomes a universal asset capable of being deployed on a server, a Jetson device, or a smartphone, all without retraining or rewriting code. Once exported, running an ONNX model with ONNX Runtime in Python is remarkably simple. A few lines of code suffice. You initialize an inference session, prepare input data in the expected shape and format, and then call .run to get predictions. ONNX Runtime automatically selects the best execution provider available, ensuring efficient use of your hardware. Developers also have the option to specify execution providers explicitly, prioritizing GPU acceleration over CPU when available. The output, typically a NumPy array of predictions, is immediately ready for downstream processing. This lightweight workflow exemplifies why ONNX Runtime is developer-friendly. It abstracts away the complexity of heterogeneous hardware, while still allowing fine-grained control for performance tuning. ONNX Runtime serves as a central hub for hardware-specific execution providers, EPs. These EPs are the secret to delivering optimized performance across diverse environments. For Intel CPUs and VPUs, the OpenVINO execution provider accelerates inference. On iOS devices, ONNX integrates with Apple's CoreML for optimized mobile inference. On NVIDIA Jetson boards, TensorRT execution providers deliver unmatched acceleration for edge workloads. For Android devices, the NNAPI execution provider leverages built-in accelerators to run models efficiently. The beauty of OnNX runtime is that the same model works across all of these environments. A single OnNX file achieves cloud-to-edge parity while still enjoying hardware-specific performance boosts. This is what makes OnNX so powerful. Developers don't just write once and run anywhere. They write once and run optimally anywhere. OnNX runtime doesn't stop at portability. It actively optimizes models for efficiency. Quantization converts models from FP32 to INT8 or FP16, dramatically shrinking their size and accelerating inference with minimal accuracy loss. Graph optimization fuses operations, eliminates redundancies, and prunes unused nodes, reducing computational overhead. Execution providers ensure the best backend is chosen automatically, further streamlining runtime performance. These optimizations are not luxuries, but necessities for edge environments where computational resources, memory, and power are inherently limited. With these tools, OnNX runtime ensures that models not only run, but thrive in real-world edge scenarios where constraints are unavoidable. The impact of OnNX runtime is evident across industries. In computer vision, smart cameras deploy YOLO 5 models exported to OnNX for real-time object detection in surveillance and retail. In predictive maintenance, factories use OnNX-powered ML pipelines to analyze sensor data, predicting failures before they occur and minimizing downtime. In retail intelligence, edge devices deliver real-time personalization at the point of sale, adapting promotions and experiences to individual customers. These examples highlight the versatility of OnNX runtime. It is not tied to a single vertical, but is adaptable across contexts. The common thread is clear. OnNX provides optimized, portable inference that makes AI practical across heterogeneous fleets of devices. The story of OnNX runtime for edge models can be summarized in 4 truths. First, OnNX provides a universal model format, making true portability possible across frameworks and devices. Second, OnNX runtime delivers optimized inference that works equally well in the cloud and at the edge. Third, hardware acceleration and quantization ensure efficiency in resource-constrained environments. And fourth, OnNX is essential for scaling AI across heterogeneous fleets, providing consistency where fragmentation has long been a challenge. The overarching message is this: OnNX is not just a tool, it is a cornerstone of modern AI deployment strategy. With a single command, pip install OnNX runtime, developers can unlock the ability to bring AI models to life anywhere, from smartphones to supercomputers, with confidence and efficiency. Deploying AI on edge devices introduces a difficult reality. The same models that thrive in cloud data centers are often far too large and power hungry for small devices like smartphones, sensors, or embedded boards. Quantization is the solution that bridges this gap. By reducing the numerical precision of model weights and activations, moving from floating point 32-bit to lower precisions like FP16, int8, or even int4, quantization makes models dramatically smaller and faster while consuming less energy. This is not just a performance hack. It is a fundamental enabler of edge AI. Quantization allows advanced deep learning systems to run within the limited compute, memory, and power budgets of microcontrollers, system-on-chips, and IoT devices. In practice, this means high-quality models can be deployed in the wild from drones to wearables to industrial sensors, without needing constant connection to the cloud. Quantization brings benefits across 4 dimensions: latency, memory, power, and deployability. Latency improves because integer operations such as INT8 execute significantly faster than floating point operations on many edge processors. Memory usage shrinks because weights and activations require fewer bits, often achieving a 4 times reduction when moving from FP32 to INT8. Power consumption drops because fewer bits mean fewer transistors firing per operation, which is critical for battery-powered devices. Finally, deployability improves as quantization enables complex models to fit within the limited memory budgets of microcontrollers or small system-on-chips. In other words, quantization turns state-of-the-art AI into something that can live in the palm of your hand, making intelligence ubiquitous. At the heart of quantization are three key concepts. First, bit width reduction, moving progressively from FP32 to FP16 or BF16, then to INT8 or INT4, with each step trading precision for efficiency. Second, quantization parameters. These map real values to integers using a scale and 0 point, formalized by the equation Q equals round x over scale plus 0 point. This mapping ensures that integer math approximates floating point behavior. Third, granularity choices. Quantization can be applied per tensor or per channel. Per tensor is simpler but may lose accuracy, while per channel quantization, especially for weights, usually preserves accuracy better. A final distinction is between symmetric and asymmetric quantization. Symmetric works well for weights, while asymmetric is common for activations to better capture full value ranges. These concepts form the building blocks of every quantization strategy. There are two main approaches to quantization. Post-training quantization, PTQ, requires no retraining and is fast to implement. It uses a representative calibration dataset to determine scaling factors and works well for many convolutional networks and some transformers. PTQ is ideal as a first attempt due to its simplicity and low engineering cost. Quantization-aware training, QAT, goes further, simulating quantization effects during training. This requires more effort and training time, but preserves accuracy, especially for aggressive quantization such as INT8 or INT4. QAT is essential for models that are sensitive to precision loss, such as transformers with attention mechanisms. The rule of thumb is clear. Start with PTQ to quickly measure gains, then switch to QAT if accuracy falls below acceptable thresholds. Quantization is only as useful as the hardware that supports it. Fortunately, today's edge hardware landscape is rich. ARM CPUs with Neon extensions support fast INT8 operations, making quantization accessible on most smartphones and embedded boards. NPUs and edge TPUs, like those in Google Coral or mobile SoCs, natively accelerate INT8 inference. NVIDIA Jetson devices leverage TensorRT to support both INT8 quantization and mixed precision, combining INT8 for efficiency with FP16 for accuracy-sensitive layers. On the consumer side, Apple's Core ML and Android's NNAPI both prioritize low-precision inference, ensuring quantized models run efficiently on mobile hardware. Across this spectrum, quantization aligns with hardware trends. Lower precision is the future, and devices are being optimized to run it natively. To see quantization in action, consider a PTQ workflow. First, collect a small calibration set, typically 100 to 1,000 samples representing real-world data. Then, export your trained PyTorch model to ONNX format. Using ONNX Runtime's quantization APIs, run static PTQ with your calibration dataset. This process maps floating point weights and activations into int8, producing a new ONNX file with quantized parameters. The result is striking. Inference often becomes 2 to 4 times faster, with memory and power savings that make the model deployable on edge hardware. TTQ is accessible, fast, and often good enough for production, particularly when representative calibration data is chosen carefully. For more sensitive models, QAT provides the accuracy-preserving path. In PyTorch, the process involves fusing supported operations, such as convolution, batch normalization, and ReLU, then preparing the model with quantization-aware configurations. During training, quantization effects are simulated, so the model learns to adapt to lower precision math. After a brief fine-tuning period, often 5 to 20% of the original epochs, the model is converted into INT8 modules. The advantage of QAT is resilience. Even aggressive quantization schemes like INT8 or INT4 maintain accuracy close to FP32 baselines. This is especially important for transformer-based models, which are notoriously sensitive to quantization. QAT requires more effort, but pays dividends in performance without sacrificing accuracy. TensorFlow Lite simplifies PTQ for TensorFlow trained models. Developers begin by converting a saved model into TF-Lite format using the TF-Lite converter. By enabling optimization flags and providing a representative dataset, the converter quantizes weights and activations into INT8. The resulting .tf-lite file is compact and ready to run efficiently on mobile or embedded devices. Developers can optionally enforce full INT8 quantization, including input and output types, which is required for deployment to specialized hardware like Google's Edge TPU. This flexibility makes TF-Lite PTQ a popular choice for mobile developers, delivering models that balance efficiency, portability, and compatibility across a broad ecosystem of devices. NVIDIA's Jetson devices bring additional power through TensorRT INT8 optimization. The workflow begins by exporting a model to ONNX, then building an INT8 engine with calibration data. TensorRT allows mixed precision, meaning accuracy-sensitive layers remain in FP16 while the rest run in INT8 for maximum efficiency. The performance gains are substantial, often delivering 1.5 to 3 times speedups compared to FP16 alone. The validation strategy involves monitoring accuracy drop, adjusting calibration, and enabling per-channel quantization as needed. For developers targeting Jetson, TensorRT represents the gold standard of edge AI optimization, combining quantization with NVIDIA's mature acceleration ecosystem. Quantization is powerful, but careless application can undermine models. 4 guardrails must always be observed. First, use representative calibration datasets. If calibration data does not match the real-world distribution, accuracy will suffer. Second, enable per-channel quantization for convolutional weights, preserving dynamic ranges across channels. Third, skip overly sensitive operations like layer normalization or softmax inattention models, which depend heavily on precise values. Fourth, for transformers, use specialized techniques like quantization-aware training or smooth quant log-scaled activations to tame outliers. These guardrails ensure quantization delivers efficiency without unacceptable trade-offs in accuracy. Successful quantization requires rigorous validation. Start with accuracy metrics. Measure top 1 accuracy, F1 score, or word error rate against FP32 baselines, targeting less than 1% degradation. Next, validate performance metrics, including latency at the 50th and 95th percentiles and overall throughput on target hardware. Monitor resource usage, such as power draw and thermal headroom, to ensure devices can sustain workloads. Finally, conduct production testing with A/B deployments, automated rollback, and guardrails to catch regressions. Device-specific validation is critical because performance can vary dramatically between hardware targets. Only thorough testing ensures that quantized models are production-ready. Several pitfalls frequently challenge practitioners. A big accuracy drop often signals the need for QAT instead of PTQ, a more diverse calibration dataset, or excluding sensitive layers from quantization. Layer mismatches after export typically stem from outdated offset versions in ONNX or Fusion incompatibilities, solvable by aligning versions and updating runtimes. Out-of-memory errors on edge devices can be mitigated by quantizing activations in addition to weights, reducing batch sizes, or adopting INT8 input-output types. Finally, jittery latency can be stabilized by pinning CPU threads, using static input shapes, and including proper warm-up before benchmarking. These fixes transform frustrating roadblocks into manageable engineering tasks, while int8 quantization delivers the best balance of efficiency and accuracy. Sometimes more aggressive approaches are required. FP16 and BF16 are quick wins, offering broad framework support and minimal accuracy loss, ideal for GPUs and NPUs. Int4 quantization compresses models even further, but typically requires QAT, per-channel quantization, and activation clipping to maintain usability. For large language models, weight-only quantization schemes like W8A16, coupled with specialized methods such as AWQ or GPT-2, are gaining traction. These techniques target KV cache and matrix multiplication efficiency, balancing compression with accuracy. Choosing precision levels must always align with hardware capability and workload sensitivity. Pushing below int8 can yield incredible efficiency, but only with careful validation and tuning. Quantization is the single most impactful optimization for deploying AI at the edge. It reduces latency, memory footprint, and power consumption, making sophisticated AI models viable on resource-constrained devices. Two approaches dominate. PTQ offers speed and simplicity, while QAT restores accuracy on sensitive or aggressively quantized models. Integration with hardware-specific runtimes. TensorRT, TF-Lite, CoreML, and NAPI ensures models are not only smaller, but also faster in real deployments. Finally, continuous validation is essential. Automation of performance and accuracy checks in CI pipelines guarantees models remain reliable across updates. The broader lesson is clear. Quantization is not just a technique, but a discipline, one that transforms cloud-scale AI into practical, deployable intelligence at the edge. Artificial intelligence models have grown enormously in size, with billions of parameters powering breakthroughs in vision, language, and multimodal reasoning. But when these models leave the data center and attempt to run on edge devices, a harsh reality emerges. Edge devices have limited compute, memory, and power budgets. Large AI models translate into slow inference, high latency, and heavy energy consumption. This mismatch demands a solution, and that solution is compression. By slimming down models, we reduce their storage footprint, shrink RAM usage, and cut computational cost, all while striving to preserve accuracy. The ultimate goal is not just smaller models, but leaner, faster, and more efficient AI that performs well in real-world environments. Compression techniques like pruning, quantization, and distillation form the toolkit that transforms massive models into practical, deployable systems. The case for compression is built on three pillars: efficiency, accessibility, and scalability. First, compression reduces model size, lowering the disk and RAM footprint. This enables deployment on devices with limited memory, from drones to wearables to IoT gateways. Second, compression reduces compute cost, as fewer floating point operations, flops, are required per inference. This means models respond faster and use less energy, which is vital for battery-powered devices. Third, compression reduces power consumption, prolonging device lifespan and cutting operating expenses. The overarching goal is clear: make AI not only smarter, but also faster and more affordable, ensuring advanced intelligence can run everywhere, not just in the cloud. Pruning is the most fundamental compression technique. At its core, pruning removes unnecessary weights, neurons, or filters from a neural network, slimming it down without significantly harming performance. The simplest approach is magnitude pruning, where small weights close to zero are dropped, as they contribute little to predictions. Structured pruning goes further, removing entire channels, neurons, or layers, creating a cleaner architecture that hardware can accelerate efficiently. Unstructured pruning is more irregular, randomly removing connections to induce sparsity, but this is harder to accelerate on current hardware. After pruning, models are retrained or fine-tuned to recover lost accuracy, yielding a leaner but still capable network. In short, pruning is the art of cutting fat while preserving muscle in neural networks. Pruning comes in several flavors. Unstructured pruning works at the finest level, removing individual weights. It induces irregular sparsity, which saves parameters but doesn't always lead to real hardware speedups. Structured pruning removes entire filters, channels, or even attention heads in transformers. Its regularity makes it friendly to CPUs, GPUs, and accelerators, translating directly into faster inference. Dynamic pruning adds adaptability, dropping computations on the fly depending on input context, a form of conditional execution. Each type balances flexibility and performance differently. Structured pruning is generally preferred for edge deployment because it aligns best with hardware capabilities, while dynamic pruning is an emerging frontier offering adaptive efficiency. The pruning journey follows a repeatable workflow. First, train a baseline model to establish a performance benchmark. Second, apply pruning, whether structured or unstructured, guided by target hardware constraints. Third, fine-tune or retrain the pruned model to recover accuracy lost during pruning. Fourth, export the compressed model into formats optimized for deployment, such as ONX or TensorRT engines. Finally, deploy with sparsity-aware runtimes like TensorRT, PyTorch Sparse, or ONX runtime, which know how to exploit the pruned structure for real-world gains. Without this vital step, pruning may reduce parameters, but fail to deliver actual speedups. The workflow ensures that pruning is not just theoretical, but results in practical, measurable improvements. To see pruning in action, let's explore unstructured pruning in PyTorch. Using torch.nnutils.prune, we can prune 30% of the connections in the first convolutional layer of a ResNet 18 model. After pruning, the model contains fewer active parameters, but accuracy typically drops. That's why fine-tuning is required, retraining the pruned model on the dataset to recover performance. Importantly, PyTorch pruning is non-destructive by default. It creates masks rather than permanently deleting weights. Developers can make pruning permanent using the remove method. This workflow demonstrates the flexibility of pruning, but also its limitations. Unstructured sparsity reduces parameter count, but may not translate into real hardware acceleration without specialized runtimes. Structured pruning, by contrast, removes entire filters or neurons. In PyTorch, this can be done with prune.lnstructured, where 20% of convolutional filters are dropped based on their L2 norm. The benefits are immediate: fewer flops and faster inference. Unlike unstructured pruning, structured pruning aligns with hardware expectations, creating physically smaller layers that run faster on CPUs and GPUs. This approach is widely used in vision applications like ResNet, where redundant filters can be pruned without major accuracy loss. Structured pruning demonstrates the core principle of compression. Simplicity translates into real-world efficiency. Pruning is just one tool in the compression toolbox. Quantization reduces precision, FP32 to int8, shrinking memory footprint and compute cost with minimal accuracy loss. Knowledge distillation trains a smaller student model to mimic the outputs of a large teacher, capturing generalization in a lightweight form. Weight sharing uses clustering or Huffman coding to reuse similar parameters, reducing the number of unique weights. Low-rank factorization approximates large weight matrices with products of smaller ones, cutting both parameter count and flops. Each method offers a different trade-off, and in practice, they are often combined. Compression, therefore, is not a single trick, but a synergy of methods that together make AI leaner and more efficient. One caveat of pruning is that reducing parameters doesn't always equal faster inference. Hardware accelerators often ignore irregular sparsity, focusing instead on dense matrix operations. As a result, memory access patterns become more important than flop count. This is why structured pruning delivers better speedups. Its regularity matches hardware expectations. To unlock real gains, we need sparsity-aware runtimes, NVIDIA's TensorRT, OnX runtime, TensorFlow Lite, and ARM Compute Library all provide specialized support for compressed models, exploiting structured sparsity for actual latency reductions. Without such runtimes, pruning may save storage but fail to improve throughput. Hardware acceleration ensures that compression is not only theoretical, but also practically beneficial. Compression is never free. It involves balancing competing goals. Aggressive pruning can lead to significant accuracy loss, undermining the model's utility. Implementation complexity rises as sparse models require specialized runtimes and careful tuning. Structured pruning provides real-world acceleration, but offers less flexibility than unstructured pruning. The art of compression lies in finding the sweet spot. Enough compression to fit models on edge hardware while retaining the accuracy needed for the application. Trade-offs must be evaluated in context. A 2% drop in accuracy may be acceptable for a mobile recommendation app, but catastrophic for a medical imaging system. Thoughtful engineering ensures compression enhances rather than undermines AI deployment. The impact of compression is best illustrated through examples. On the Judson Nano, pruning YOLO v5 by 40% doubled inference speed with only a 2.5% drop in mean average precision. On mobile NLP models, pruning 30% of transformer heads and layers allowed them to fit within 2 gigabytes of RAM, enabling responsive on-device language understanding. In ResNet-based vision applications, combining filter pruning with quantization made models 4 times smaller while keeping accuracy within 1% of baseline. These examples show that compression is not theoretical, but a practical enabler of AI at the edge, bridging the gap between research models and real-world constraints. Years of experience in model compression have revealed best practices. Start conservatively, pruning just 10 to 30% initially to minimize accuracy loss. Always fine-tune after pruning to recover performance. Combine methods, pairing pruning with quantization or distillation for multiplicative gains. Favor structure, since structured pruning translates into tangible hardware speedups. And finally, measure what matters. Benchmark not just parameter count, but actual latency and energy consumption on target devices. These practices ensure that compression achieves its true goal: practical, efficient, deployable AI. The lessons of pruning and compression can be summarized simply. Pruning fundamentals involve removing weights or filters to streamline networks. Triple benefits: smaller models, fewer flops, and lower power consumption make compression indispensable for edge AI. Structure matters, since structured pruning aligns best with hardware for real acceleration. Combination is key, as pairing pruning with quantization or distillation yields the best trade-offs. Above all, compression transforms AI from a cloud-centric luxury into an edge-ready reality. It is the essential discipline that enables AI to thrive in the real world, where devices are constrained, but intelligence is demanded everywhere. Artificial intelligence is now being deployed everywhere in cameras, autonomous vehicles, robots, healthcare devices, and smart city infrastructure. Yet running AI at the edge presents unique challenges: limited compute resources, power constraints, and strict latency requirements. This is where NVIDIA TensorRT comes in. TensorRT is NVIDIA's inference optimizer and runtime environment, designed to transform trained models into highly efficient execution engines tailored for deployment. Whether on the Jetson Nano, Xavier, Orin, or full-scale NVIDIA GPUs, TensorRT ensures that models trained in PyTorch or TensorFlow can run at lightning speed in real-world edge environments. Its core mission is simple but transformative. Take heavy cloud-scale AI models and make them lightweight, fast, and efficient enough to thrive in resource-constrained devices without sacrificing the intelligence that makes them valuable. TensorRT is more than just a runtime. It is an inference optimization framework. Once a neural network is trained, deploying it in the real world requires adjustments. Operations must be fused, precision reduced, and memory carefully managed. TensorRT automates these tasks, converting models into .engine files that are hardware-specific and performance-optimized. It supports the entire NVIDIA stack, from consumer GPUs to enterprise accelerators to Jetson devices. Importantly, TensorRT is framework agnostic. It works with models from PyTorch, TensorFlow, or the standardized ONNX format. This flexibility makes it an essential bridge between the research phase of AI and the deployment phase, ensuring models don't just work in theory, but operate efficiently in the environments that matter most. The benefits of TensorRT for edge deployment are tangible and measurable. First, reduced latency. Optimized FP16 and INT8 kernels enable sub-100 millisecond responses, vital for real-time decision-making. Second, a smaller memory footprint allows compressed models to fit within the tight constraints of Jetson devices. Third, increased throughput enables systems to handle multiple inputs simultaneously, making multi-camera or multi-sensor systems viable at the edge. Fourth, extended battery life. Energy-efficient execution means devices like drones, autonomous robots, or IoT sensors can operate longer without recharge. Together, these benefits make TensorRT indispensable for any organization that needs AI to run reliably and efficiently outside the comfort of the cloud. TensorRT accelerates inference through a series of carefully engineered optimizations. Layer fusion merges operations into fewer, more efficient kernels, reducing redundant memory transfers. Precision calibration converts operations from FP32 down to FP16 or INT8, balancing efficiency with accuracy. Kernel auto-tuning dynamically selects the best implementation for each operation, tailored to the target hardware. Dynamic memory allocation reuses tensor memory intelligently across the execution graph, minimizing waste. Collectively, these techniques transform computational graphs into hardware-optimized execution pipelines. Instead of treating a model as a generic workload, TensorRT reshapes it to align perfectly with the underlying GPU or Jetson accelerator. Deploying with TensorRT follows a straightforward 5-step pipeline. First, train your model using PyTorch or TensorFlow. Second, export to ONNX, the intermediate representation that ensures interoperability. Third, build the TensorRT engine, creating a hardware-specific .engine file optimized for the device. Fourth, run inference using the TensorRT runtime, deploying the engine into your application. And finally, benchmark and validate, confirming that latency, throughput, and accuracy meet production requirements. This workflow is simple yet powerful, enabling developers to bridge the gap between cloud training and edge deployment without reinventing their entire pipeline. The first key step in using TensorRT is exporting models to ONNX. For example, in PyTorch, we can load a pre-trained ResNet 18 model, set it to evaluation mode, create a dummy input tensor, and then export to ONNX with torch.onnx.export. The resulting .onnx file captures both the architecture and weights of the model while remaining framework independent. ONNX acts as a universal bridge, allowing TensorRT to ingest the model and apply its optimizations. This step is critical because it standardizes workflows. Once in ONNX, a model can flow seamlessly into TensorRT, regardless of its original training framework. Once a model is in ONNX format, the next step is to generate a TensorRT engine. Using the TritExec command line tool, developers can quickly build engines with different precision levels. For example, FP16 optimization delivers faster inference with minimal accuracy trade-off, while INT8 optimization requires calibration but can achieve dramatic performance gains. The TritExec tool not only converts models, but also benchmarks them, providing latency and throughput metrics immediately. The output is a .engine file, a hardware-specific package containing all the optimizations needed for deployment. With this, your model is no longer a generic ONNX file. It becomes a finely tuned execution engine tailored to your device. Deploying an engine in Python requires only a few steps. First, load the .engine file using TensorRT's runtime API. Then, create an execution context, prepare your input data as a NumPy array, and allocate buffers for input and output. With PyCUDA integration, data can be efficiently transferred between CPU and GPU memory. Finally, call the execution context to run inference, retrieving results almost instantly. While this workflow requires boilerplate code, helper libraries like Torch TensorRT simplify the process, allowing PyTorch users to run models directly with minimal changes. This demonstrates TensorRT's accessibility. Whether you want low-level control or high-level integration, the tools are there to make deployment seamless. The performance improvements with TensorRT are striking. On Jetson Nano, models optimized to FP16 or INT8 can run 3 to 4 times faster than baseline FP32 models. On Xavier and Orin platforms, the gains are even greater, often hitting 30 to 100 frames per second or more for complex vision models. The trade-off comes in accuracy. INTA quantization may introduce a 1 to 2% drop compared to FP32. However, this can be mitigated with proper calibration datasets, quantization-aware training, and per-layer precision control. The takeaway is clear. TensorRT enables edge devices to achieve near-cloud levels of performance, unlocking use cases that were previously impractical. TensorRT powers a wide spectrum of edge AI applications. In computer vision, it accelerates YOLO, SSD, and ResNet models for real-time analytics in surveillance, retail, or manufacturing. In robotics, it supports SLAM, navigation, and perception workloads, where low-latency decision-making is critical for safety and autonomy. In healthcare, TensorRT enables portable diagnostic devices and patient monitoring systems to process data locally, ensuring both speed and privacy. In retail and smart cities, TensorRT allows multi-camera systems to perform people counting, behavior analytics, and surveillance with minimal latency. These examples highlight TensorRT's adaptability. It is not limited to one domain, but serves as a general-purpose accelerator wherever AI meets the edge. Maximizing TensorRT's potential requires following best practices. First, use representative calibration data for INT8 to ensure accuracy across diverse inputs. Second, always profile before production, benchmarking latency and throughput with TRT-exec under different conditions. Third, maintain multiple engines, keeping both FP16 and INT8 versions for flexibility as accuracy requirements shift. Fourth, for multi-device scaling, use NVIDIA Triton Inference Server with Kubernetes, enabling orchestration across clusters. And finally, always validate accuracy versus speed for your specific application, especially under real-world conditions like thermal constraints. These practices ensure that TensorRT delivers not just speed, but sustainable production-grade performance. TensorRT is NVIDIA's edge inference accelerator designed specifically to maximize AI performance on constrained devices. By combining FP16 and INT8 precision optimizations, it routinely delivers 3 to 4 times speedups while reducing memory and power consumption. Its workflow, train, export to ONNX, convert to TensorRT engine, run inference, validate is straightforward and integrates seamlessly into existing AI development pipelines. Most importantly, TensorRT makes real-time AI at the edge a reality, enabling applications that once seemed impossible outside the cloud. For engineers and developers, adopting TensorRT means embracing the future of AI deployment, efficient, portable, and ready for the edge. Artificial intelligence is often associated with expensive servers and specialized GPUs, yet the Raspberry Pi has emerged as one of the most important gateways into edge AI development. Priced affordably between $35 and $75, the Pi has democratized access to computing power that only a decade ago would have required hundreds of dollars in equipment. For students, hobbyists, and educators, it represents the perfect blend of capability and accessibility. Powerful enough to handle lightweight AI tasks, but simple enough to set up in a classroom or garage lab. What makes it particularly compelling for vision applications is the native camera interface with a CSI connector built directly into the board, as well as support for standard USB webcams. Combined with an active global community producing endless tutorials, libraries, and forum discussions, the Raspberry Pi has become an unparalleled platform for learning, prototyping, and experimenting with vision AI at the edge. To run vision AI models effectively, the choice of hardware matters. A Raspberry Pi 4 with 4 gigabytes or ideally 8 gigabytes of RAM is recommended, since memory is often the limiting factor for inference workloads. The ARM Cortex-A72 CPU provides the baseline computational horsepower, while a 32 gigabytes Class 10 micro SD card, preferably a high-quality model like SanDisk Extreme or Samsung Evo, ensures reliability and smooth data access. For capturing images, developers can choose between the Pi Camera Module V2 with 8 megapixels, a standard USB webcam, or the HQ Camera Module with 12.3 megapixels for high-resolution tasks. For those requiring real-time performance on more complex models, an optional Coral TPU USB accelerator delivers 10 times to 50 times speedups by offloading matrix multiplications onto a dedicated neural processor. This combination of affordable, modular hardware makes Raspberry Pi a remarkably versatile entry point into the world of edge AI vision. The true power of Raspberry Pi comes alive with its software ecosystem. At the base is the operating system, typically Raspberry Pi OS in 64-bit mode or Ubuntu 20.04 LTS, both of which unlock the Pi's full RAM capacity. On top of this, frameworks provide the intelligence. TensorFlow Lite and PyTorch Lite bring popular ML libraries in edge-optimized form, while OpenCV enables image capture, pre-processing, and augmentation. Performance can be further boosted with ONX runtime ARM builds, the Coral Edge TPU runtime, or ARM Neon acceleration. Developers usually work in Python 3, the Pi's lingua franca, though C++ can be used for performance-critical applications and shell scripts for automation. This stack ensures that the Pi is not just a toy computer, but a fully functional AI development platform capable of running optimized inference pipelines for real-world applications. TensorFlow Lite, or TF Lite, provides the most common pathway for deploying models on the Raspberry Pi. The journey begins by training or exporting a lightweight model, such as MobileNet, YOLO Lite, or EfficientNet Lite, on a more powerful machine. Once trained, the model is converted into .tf Lite format using the TensorFlow Lite converter, often with quantization applied to shrink model size and improve speed. Deployment then involves transferring the .tf Lite file to the Pi, setting up the camera pipeline, and running inference through the TF Lite interpreter. With only a few lines of Python, developers can load the model, allocate tensors, and invoke predictions. The efficiency of this workflow makes it ideal for hobbyists and educators. Training is done in the cloud or on a workstation, but inference happens locally, fast enough to power doorbells, monitoring systems, or small robots. Beyond TensorFlow Lite, the Pi can also leverage the ONX runtime, which brings interoperability across frameworks. ONX, the Open Neural Network Exchange format, allows models trained in PyTorch, TensorFlow, or other frameworks to be exported into a unified standard. With a simple pip install ONX runtime, developers can run these models on Raspberry Pi using ARM-optimized builds. This brings two main benefits. First, it enables memory-efficient inference, critical given the Pi's RAM limitations. Second, it broadens the choice of models, since ONX supports popular vision networks like ResNet and MobileNet. In effect, ONX runtime makes the Pi a cross-framework inference engine, allowing developers to pull from a wide ecosystem without being tied to a single tool. For those needing true real-time inference, the Coral Edge TPU USB accelerator is a game-changer. Capable of delivering 30+ frames per second on MobileNet SSD running on a Pi 4, it transforms the board into a legitimate edge AI device. The TPU works by offloading the most computationally expensive operations, the dense matrix multiplications at the heart of neural networks, onto dedicated hardware. The workflow involves compiling .tflight models with the Edge TPU compiler, then loading them with the specialized Edge TPU runtime. The results are dramatic. Tasks that would otherwise run at a few frames per second on the CPU suddenly achieve real-time performance, enabling responsive doorbells, retail analytics systems, and wildlife monitoring cameras. In essence, the Coral TPU unlocks production-grade applications on a $75 device, bridging the gap between prototyping and deployment. The versatility of Raspberry Pi in AI vision is best understood through examples. A smart doorbell can detect and recognize visitors, sending instant notifications with images to homeowners' smartphones. In wildlife monitoring, battery-powered Pi units equipped with cameras can detect motion and classify animal species in remote forests. Retail analytics solutions can track shelf occupancy and product availability, producing real-time inventory reports at minimal cost. In education, Raspberry Pi empowers students to build robotics projects, experiment with object recognition, and learn the fundamentals of computer vision. These use cases highlight the Pi's unique balance. It is affordable and accessible enough for classrooms, yet powerful and flexible enough for lightweight production deployments. Despite its promise, running AI on Raspberry Pi comes with notable challenges. Resource constraints are the most obvious. With only 4 to 8 gigabytes of RAM, the Pi cannot handle very large models or batch processing. CPU-bound performance means that without accelerators like the Edge TPU, inference speed is limited. Thermal constraints also matter. Heavy workloads cause heat buildup, requiring heat sinks or fans to prevent throttling. Power limitations affect portable applications. With 5 to 15 watts of consumption, battery-powered systems require careful management. Finally, processing bottlenecks restrict real-time inference to lightweight models. These challenges remind us that while Raspberry Pi is powerful for its size and cost, it is not a replacement for industrial-grade servers. Instead, it is a complementary tool for prototyping, education, and targeted lightweight deployments. To overcome these challenges, developers follow proven best practices. First, use lightweight architectures like MobileNet, V2, V3, EfficientNet Lite, YOLO Nano, or MobileVeet, all designed for constrained environments. Second, apply quantization, converting FP32 models into INT8 to shrink them by 3-4 times and speed inference 2-3 times with minimal accuracy loss. Third, optimize the I/O pipeline by preprocessing images with OpenCV, resizing before inference, and using threading or frame skipping to manage camera input. Fourth, consider hardware accelerators, Coral TPU, Intel's Neural Compute Stick 2, or custom NPU hats dramatically boost performance. The overarching principle is this: optimizing for the edge requires a different mindset than cloud AI. Success comes from designing with constraints in mind, squeezing every bit of efficiency from hardware and software alike. The Raspberry Pi stands as a gateway to edge-efficient AI, accessible, affordable, and backed by a vibrant community. It is ideally suited for prototyping, education, and lightweight production deployments, where cost and accessibility matter more than raw performance. Success requires aggressive optimization. TensorFlow Lite or OnX runtime, combined with quantization, ensures models run within hardware limits. For production use cases demanding real-time performance, HTPU or similar NPUs are essential accelerators. Ultimately, the Raspberry Pi proves that AI is no longer reserved for expensive clusters or cloud servers. It can live on a $75 device, teaching students, enabling researchers, and powering small-scale deployments worldwide. The message is simple but powerful. AI is for everyone, and Raspberry Pi is the bridge that makes it possible. TinyML represents one of the most exciting frontiers in artificial intelligence. Unlike massive AI models that run on cloud servers or GPUs with terabytes of memory, TinyML focuses on bringing intelligence to microcontrollers, devices with as little as a few kilobytes of RAM. This enables always-on, ultra-low-power AI running directly on sensors, wearables, and small IoT devices. The magic of TinyML lies in its ability to specialize. Keyword spotting, anomaly detection, and gesture recognition are tasks that don't require billion-parameter models, but rather lean, efficient neural networks optimized for constrained environments. The promise is enormous, with billions of microcontrollers already embedded in appliances, industrial systems, and consumer electronics. TinyML has the potential to transform ordinary objects into smart companions capable of perception, adaptation, and autonomy, all without depending on the cloud. TinyML is not just a technical curiosity, it is transformative because of its benefits. First, ultra-low power. These systems can operate on batteries for months or years, making them perfect for remote or portable deployments where constant recharging is impractical. Second, privacy-first design. Since data is processed locally, sensitive information like health metrics or voice commands never needs to leave the device, addressing both compliance and trust concerns. Third, real-time inference. By cutting out round trips to the cloud, TinyML delivers millisecond-level latency, enabling responsive interactions in time-critical applications. Finally, massive scalability. Billions of microcontrollers already exist in the world, and with TinyML, they can all be upgraded into intelligent devices. This is not just about creating smarter gadgets, it is about weaving intelligence into the very fabric of everyday life at scale. The hardware ecosystem for TinyML is diverse, catering to both prototyping and industrial-grade deployment. The Arduino Nano 33 BLE Sense is perhaps the most accessible, integrating a 9-axis IMU, microphone, and environmental sensors, making it ideal for beginners and rapid prototyping. The STM32 family of microcontrollers powers industrial automation worldwide, valued for reliability and performance. The ESP32 stands out with Wi-Fi and Bluetooth support, perfect for IoT applications that require connectivity. And for those demanding more intensive inference, Edge TPUs or NPUs serve as neural coprocessors, accelerating workloads while keeping energy usage low. This variety demonstrates the adaptability of TinyML, from $5 hobby boards to industrial MCUs. The hardware landscape makes it possible to embed AI almost anywhere. Hardware alone cannot deliver TinyML. It requires a carefully crafted software stack. At the heart is TensorFlow Lite for microcontrollers, TFLM, Google's framework that can run models with as little as 16 kilobytes of memory. Platforms like Edge Impulse simplify the entire pipeline, from data collection and labeling to training and deployment, making TinyML accessible to non-experts. CMSIS-NN, developed by ARM, provides optimized kernels that maximize performance on Cortex-M processors, ensuring every cycle counts. Finally, OnNX Runtime Mobile offers a lightweight inference engine supporting multiple model formats, increasing interoperability. Together, these tools empower developers to train models on powerful systems and then deploy them seamlessly onto microcontrollers, bridging the gap between research and real-world deployment. A classic TinyML use case is keyword spotting, the foundation of wake word systems like Hey Siri or OK Google. The workflow begins with collecting 1-second audio clips of keywords and background noise. These are then converted into spectrograms, visual representations of sound, which are fed into a small convolutional neural network. Once trained, the model is converted into TFLM format and flashed onto an Arduino Nano BLE Sense. The result is astonishing. An LED lights up when the keyword is detected, all without cloud connectivity. This example highlights the strengths of TinyML: real-time responsiveness, complete privacy, and ultra-low power consumption. It demonstrates that even constrained devices can deliver meaningful AI experiences when tasks are carefully scoped and models are efficiently optimized. Industrial IoT presents another compelling TinyML application: anomaly detection. Consider a factory motor that must be monitored continuously to detect early signs of failure. Streaming vibration data to the cloud 24/7 would be expensive, power-hungry, and bandwidth-intensive. With TinyML, an MCU connected to a vibration sensor can run an autoencoder model locally, learning what normal operation looks like and detecting deviations in real time. Alerts are sent only when anomalies appear, drastically reducing data transfer and power consumption. The result? Battery life extends from days to months, costs plummet, and predictive maintenance becomes feasible, even in remote, low-connectivity environments. TinyML makes industrial intelligence not only possible, but practical at scale. The challenge of running AI on kilobytes of memory requires aggressive optimization. Quantization converts 32-bit floating point weights to INT8 or even INT4, reducing model size by up to 8 times with minimal accuracy loss. Pruning and distillation remove unnecessary connections and compress knowledge from larger models into smaller ones. Feature engineering reduces input complexity by leveraging domain-specific features like MFCCs for audio or statistical descriptors for sensor data. Finally, microarchitectures, networks explicitly designed for MCUs, such as micro CNNs or lightweight RNNs, replace bulky architectures with leaner designs. These techniques, used in combination, transform unwieldy models into efficient deployable ones, proving that the art of TinyML is as much about compression as it is about innovation. Despite its promise, TinyML faces serious challenges. Memory constraints are the most obvious, with many MCUs offering only 32 kilobytes to 512 kilobytes of RAM, forcing extreme optimization. Power management is another hurdle. Devices must often sleep between inferences, requiring careful duty cycling to balance responsiveness and longevity. Bare metal programming complicates development since many MCUs lack operating systems, demanding low-level expertise. Debugging is limited, as restricted logging capabilities make troubleshooting harder than in cloud environments. Finally, the gap between simulation and deployment means models that perform well on laptops may fail under real-world constraints. These obstacles underscore that TinyML is not trivial. It is engineering at the frontier, where every byte and milliwatt matters. TinyML's potential spans industries. In wearables, it enables heart rate anomaly detection, activity classification, and sleep monitoring without draining batteries or compromising privacy. In smart homes, it powers wake word detection, gesture recognition, and presence sensing, making environments more responsive and energy efficient. In agriculture, TinyML assists with crop monitoring, irrigation optimization, and pest detection, often in remote fields without reliable connectivity. In industrial IoT, it delivers predictive maintenance by analyzing vibration and sound patterns locally. These use cases prove a central point. TinyML is not a niche, but a horizontal enabler, capable of embedding intelligence wherever microcontrollers already exist, which is virtually everywhere. To succeed with TinyML, certain best practices must be followed. First, design for extreme constraints. Aim for models under 10 kilobytes, aggressively quantized and optimized. Second, use specialized tools like Edge Impulse to streamline the pipeline from data to deployment, lowering entry barriers. Third, benchmark on real hardware. Simulators cannot capture true performance, so always test latency, accuracy, and memory use on target NCUs. Fourth, optimize for power. Design inference cycles with sleep-wake patterns to extend battery life. Finally, focus on narrow, task-specific applications rather than general-purpose intelligence, which is far beyond MCU capacity. By adhering to these practices, developers can turn constrained devices into reliable, intelligent agents operating at scale. TinyML embodies the vision of AI everywhere, even on $5 microcontrollers. Its transformative benefits include real-time, on-device inference, enhanced privacy, ultra-low power consumption, and massive scalability. The technical recipe is clear: optimized, quantized models running on MCU-friendly runtimes, supported by microarchitectures and specialized tools. The practical path to entry is equally simple. Start with hardware like the Arduino Nano 33 BLE Sense. Experiment with Edge Impulse and begin with small focus classification tasks. From there, the community and ecosystem provide the support to grow. The overarching message is that the future of AI is not confined to the cloud. It will live in billions of tiny, intelligent devices all around us, invisibly making life smarter, safer, and more efficient. With deploying machine learning to edge devices, one truth quickly becomes apparent: constraints define reality. Edge devices, whether microcontrollers, Raspberry Pis, or Jetson modules, operate with limited compute, memory, and power. What works in the cloud often collapses under these restrictions. Benchmarking is the disciplined process of testing models directly on target hardware to uncover these realities. It answers critical questions. Will the model meet latency requirements? Can it sustain throughput under load? Does it fit within RAM limits? Benchmarking also addresses performance variability. Models behave differently when compressed, quantized, or executed under varying conditions. Empirical testing provides the evidence needed for confident deployment. Most importantly, benchmarking builds deployment confidence. It allows teams to strike the right balance between efficiency and accuracy, ensuring service-level agreements are met without sacrificing the user experience. Effective benchmarking is guided by metrics across three dimensions: performance, quality, and efficiency. Performance involves latency, measured in milliseconds per inference, often at P50 or P95 percentiles, and throughput recorded as inferences per second or frames per second for vision tasks. Quality measures include accuracy, F1 score, or precision recall, ensuring compression or optimization hasn't degraded results beyond acceptable thresholds. Memory footprint, both RAM usage and model size on disk, is another key factor, particularly for microcontrollers. Efficiency metrics focus on power draw, watt consumption, thermal impact, and battery drain. By triangulating across these metrics, developers gain a holistic view of how a model behaves under real-world constraints. Optimization is no longer guesswork. It is data-driven decision-making. Benchmarking follows a structured workflow designed to reveal actionable insights. Step 1 is model selection, where candidates like MobileNet, ResNet, or YOLO variants are chosen for evaluation. Step 2 involves conversion to edge-optimized formats such as TF-Lite, TensorRT, or Onyx to ensure compatibility with hardware accelerators. Step 3 is deployment to the target device, whether a Jetson, Raspberry Pi, or MCU. Step 4 executes standardized benchmarks on datasets that reflect real-world conditions. Step 5 involves collecting comprehensive metrics: latency, memory, accuracy, and energy usage. Finally, results are compared against baselines to evaluate trade-offs. This iterative loop enables systematic improvement, ensuring models are not just accurate, but deployable within edge constraints. Benchmarking requires specialized tools. TensorFlow Lite offers the benchmark model utility, which provides standardized performance metrics. Onyx Runtime includes cross-platform profiling features for measuring latency and throughput. MLPerf Tiny and MLPerf Inference deliver industry-standard benchmarks, enabling consistent cross-model comparisons. PyTorch Mobile supports profiling for PyTorch-based edge deployments, capturing per-layer timing. For advanced customization, developers rely on custom profiling tools like Python's time.perfcounter or GKU synchronization functions such as torch.cuda.synchronize. These tools provide granular visibility, empowering engineers to understand not just whether a model is slow, but why it is slow, and where optimization should be focused. A practical example illustrates the workflow. Using TensorFlow Lite's benchmark tool on Raspberry Pi, a developer runs /benchmark model bar.graph mobilenet v2.tflite input layer input layer shape 1 24 24 3 star num threads 4. The output delivers detailed metrics: inference latency in milliseconds, memory usage in megabytes, CPU utilization percentage, and initialization time. It even provides per-layer breakdowns, showing which operations dominate compute. This transparency empowers optimization, perhaps resizing inputs, fusing operations, or quantizing bottleneck layers. The result is actionable insight. Developers know precisely where improvements can be made to squeeze maximum performance from limited hardware. On NVIDIA Jetson devices, benchmarking often leverages TensorRT's TerdexEC utility. Running a ResNet 18 model with FP16 precision might look like this: TerdexEC-ONX equals ResNet 18.ONX FP16 shapes input 1 3 224 224. The results are illuminating. FP32 inference might take 3.2 milliseconds, while FP16 cuts that to 1.8 milliseconds, and int8 quantization drives it further down to 0.9 milliseconds. These improvements are not theoretical. They are measured, benchmarked outcomes that demonstrate how precision reduction and kernel fusion can unlock real-time performance. TensorRT showcases the power of hardware-specific optimization, where the same model behaves very differently depending on deployment precision. Benchmarking strategies differ by device class. Microcontrollers, TinyML, handle ultra-low power tasks like keyword spotting or anomaly detection, using models such as micronets or proxyless NAS. Raspberry Pi class devices, single-board computers, target lightweight networks like Mobile Net v2 or Efficient Det Lite, suitable for small NLP or vision tasks. Jetson and Edge GPUs support more demanding workloads, including YOLO 5, ResNet 18, or even lightweight transformer models like Distilbert. Each category imposes unique constraints, memory limits on MCUs, fervor throttling on Pi-class devices, or power draw on Jetson. Benchmarking must therefore align not just with the model, but also with the device class and task-level service agreements to be meaningful. Benchmarking reveals the quantitative trade-offs between models. For instance, MobileNet v2 delivers blazing speed with low memory use, but at a slight cost to accuracy. ResNet 50 achieves higher accuracy but demands heavier compute. YOLO Nano offers speed and compactness, whereas YOLO v5 delivers superior detection precision at the expense of latency. A trade-off chart comparing latency, accuracy, and model size provides decision makers with clarity. Should they prioritize speed, precision, or efficiency? Benchmarking provides the empirical data to make these decisions rationally, aligning technical compromises with business and application requirements. Benchmarking is incomplete without power and thermal profiling, especially for battery-powered or remote deployments. Tools include USB inline power meters for measuring watt draw, Jetson's Tequastats utility for GPU utilization and thermals, and even thermal imaging cameras for hotspot detection. Key metrics include watts under various workloads, thermal throttling thresholds, and accuracy per watt efficiency. These measurements enable battery life estimation and system reliability analysis. Without this data, a model might pass latency tests, but fail in the field due to overheating or power exhaustion. Power and thermal testing thus closes the loop, ensuring edge deployments are viable, sustainable, and field-ready. Experience has shaped best practices that every team should follow. Benchmark on real hardware. Simulators cannot capture real-world performance. Use representative datasets that reflect real edge conditions, from poor lighting to noisy audio. Measure complete latency, including both cold start initialization and steady state inference, since users experience both. Vary batch sizes and quantization levels to uncover optimal configurations. And most importantly, automate benchmarking in CI/CD pipelines, ensuring performance regressions are caught early. These practices turn benchmarking from a one-off exercise into a continuous discipline embedded into the lifecycle of edge AI systems. The lesson is clear. What you can't measure, you can't optimize. Edge benchmarking is not optional, it is essential. It ensures that models are matched appropriately to device constraints, balancing accuracy, speed, memory, and power. Comprehensive benchmarking requires metrics across all dimensions, the right tools for each platform, and real-world testing to validate results. Ultimately, benchmarking is what transforms an AI model from a research artifact into a deployable, reliable product. Without it, deployment is guesswork. With it, deployment is a science, producing systems that perform as promised under the very constraints that make edge AI so powerful and so challenging. Artificial intelligence is no longer confined to distant data centers or cloud-only infrastructures. Increasingly, it is moving directly onto the devices we carry every day: smartphones, tablets, and wearables. Modern smartphones are not just communication tools, they are edge computers in our pockets, equipped with powerful CPUs, GPUs, and dedicated NPUs designed for AI workloads. This shift has been driven by rising user expectations. People want experiences that are instant, private, and resilient, even when connectivity is poor or absent. Cloud-only approaches often struggle to deliver this. On-device AI, by contrast, provides immediacy, autonomy, and privacy, making it the natural evolution of the AI landscape. The model has shifted to hybrid and on-device inference, where the heavy lifting of training may still happen in the cloud, but execution, the intelligence users interact with daily, increasingly runs locally, closer to the user and the data. The surge in mobile AI adoption can be traced to five powerful drivers. Latency is the first. Sub 100 millisecond response times are non-negotiable for real-time features such as camera filters, AR experiences, and voice assistants. Second is privacy. With sensitive data like photos, health metrics, and voice samples staying on device, users gain confidence that personal information is not constantly streamed to external servers. Third is cost efficiency. Reducing dependency on cloud inference APIs lowers infrastructure costs, making scaling more predictable for businesses. Fourth, reliability. Features continue to work in offline or low bandwidth scenarios, which is essential for users in global markets where connectivity is inconsistent. Finally, personalization. On-device AI can leverage local context and sensor data to deliver hyper-customized experiences, adaptive UIs, predictive typing, or health insights unique to each user. These drivers explain why mobile AI has become a defining trend in the evolution of intelligent applications. The hardware landscape has matured to fully support mobile AI. Today, neural processing units, NPUs, or neural engines are standard on flagship SoCs, providing dedicated acceleration for AI workloads. Efficient GPU and DSP pipelines, accessed through APIs like Metal and Vulkan, further improve throughput for vision, speech, and NAP tasks. Mixed precision computing, using FP16 and INT8, reduces memory footprint and boosts efficiency, making larger models viable within device constraints. Meanwhile, devices now ship with larger RAM capacities and faster storage, ensuring smooth execution of increasingly complex models. Together, these hardware tailwinds eliminate many of the traditional barriers to on-device AI, making it not just possible, but practical to deploy sophisticated neural networks locally on everyday mobile devices. Hardware alone cannot deliver intelligence. It must be paired with the right software ecosystem. Apple's Core ML provides a native framework for deploying models on iOS, optimized with tools like BNNS and Metal Performance shaders. TensorFlow Lite, Google's mobile-first ML framework, integrates with GPU NNAPI and Metal delegates for efficient inference. Android's NNAPI provides a standardized way to route AI operations to available accelerators across the Android ecosystem. And ONX Runtime Mobile offers cross-platform portability, ensuring models trained in PyTorch or TensorFlow can run seamlessly on both iOS and Android devices. Each of these frameworks abstracts away much of the hardware complexity, giving developers optimized pathways to high-performance, energy-efficient on-device inference. The result is a mature, interconnected ecosystem that makes mobile AI deployment not only feasible, but increasingly streamlined. The success of mobile AI is best illustrated through its use cases. In vision, it powers real-time photo enhancement, video stabilization, OCR for document scanning, and instant object recognition. In speech and NLP, on-device AI drives wake word detection, dictation, translation, summarization, and even sentiment analysis. In safety and accessibility, it underpins crash and fall detection, live captioning, and screen readers, ensuring devices are inclusive and responsive. In AR and VR, it enables spatial tracking, scene understanding, real time effects, and gesture recognition. Finally, in personalization, mobile AI delivers smart keyboard predictions, adaptive user interfaces, and context aware content recommendations. These use cases highlight that mobile AI is not limited to one vertical. It is a horizontal enabler, reshaping user experiences across industries and applications. The business implications of mobile AI adoption are profound. By reducing reliance on cloud inference, companies cut costs significantly, lowering their cost of goods sold, COGS, and making scaling more predictable. At the same time, user retention and engagement improve thanks to features that are faster, snappier, and more responsive. Regulatory compliance becomes easier. On device processing helps organizations satisfy data residency and consent requirements, aligning with global privacy standards. Finally, companies gain a competitive edge by delivering experiences that feel more private, battery efficient, and reliable than cloud dependent competitors. Mobile AI is therefore not just a technical trend, it is a business strategy, creating a moat around products through superior user experiences. Of course, deploying AI on mobile devices introduces its own set of challenges. Memory and compute limitations restrict the size and complexity of models that can be executed locally. Thermals and battery drain are concerns, as sustained workloads may cause overheating or degrade battery life. Hardware fragmentation complicates development, particularly in the Android ecosystem, where devices vary widely in capability. Model lifecycle management also grows complex, as organizations must manage the logistics of deploying, updating, and rolling back models across millions of devices. These constraints require thoughtful architecture, rigorous optimization, and disciplined engineering to ensure that on device AI remains efficient, sustainable, and user friendly. Optimizing AI models for mobile requires a deliberate toolkit. Quantization reduces precision to INT8 or FP16, shrinking models and boosting efficiency with frameworks like TensorFlow Lite, Core ML, and Onyx Runtime Mobile. Pruning and distillation slim down architectures while retaining most of their predictive power. Operator coverage must be carefully considered, ensuring that models use only operations supported by accelerators like NNAPI or Metal. Streaming and chunking strategies prevent out of memory errors by processing long inputs, such as audio or text, in smaller segments. Finally, on device caching of tokens or embeddings speeds up repeated inferences. Collectively, these techniques transform heavyweight cloud models into lean, mobile optimized systems capable of running reliably on smartphones and tablets. Certain model architectures are particularly suited to mobile deployment. Envision networks like MobileNet, EfficientNet Lite, and YOLO Nano provide efficient performance for image classification and detection. In speech, models like Conformer and QuartzNet are optimized for low latency on device audio processing. In NLP, distilled transformer variants such as TinyBert and MobileBur strike a balance between size and accuracy. Even in LLMs, innovations like LoRa, low rank adaptation, and weight only quantization make it possible to run pared down language models on high end smartphones. These architectures demonstrate that mobile AI is not about compromise, but about careful design, where efficiency and accuracy are balanced to deliver high-quality experiences within device constraints. The most successful applications combine the strengths of both on-device and cloud AI through hybrid patterns. On-device first strategies prioritize local inference, falling back to the cloud only when tasks exceed device capabilities. Progressive enhancement delivers instant, lower quality results locally, refining them later with cloud resources for improved accuracy. Privacy gates ensure that sensitive personal data remains on device, while only anonymized signals are sent to the cloud for learning and analytics. These patterns illustrate the pragmatic middle ground, blending the immediacy and privacy of mobile AI with the scale and power of cloud backends to achieve the best overall user experience. To deploy mobile AI successfully, organizations should follow a structured checklist. First, define clear SLAs. Set latency and battery budgets up front to guide optimization. Second, ensure framework compatibility, selecting models whose operators are supported by Core ML, NN API, or similar runtimes. Third, optimize aggressively, applying quantization, pruning, and distillation early in development rather than as an afterthought. Fourth, test across a device matrix, validating performance on low, mid, and high-tier devices to ensure broad accessibility. Fifth, implement telemetry to gather privacy-preserving performance data in the field, enabling continual tuning and improvement. Following this checklist ensures that mobile AI projects are robust, scalable, and user-centric. The rise of mobile AI signals a profound shift in how intelligence is delivered. On-device inference offers faster, cheaper, and more private experiences than cloud-only approaches. Hardware is ready. Today's smartphones are equipped with specialized silicon and mature runtime frameworks. Hybrid strategies win in practice, blending local speed with cloud breadth. Optimization must begin early, focusing on precision, power efficiency, and operator compatibility from the start. The companies that master mobile AI will not just improve apps, they will define the next generation of user experiences, setting new standards for performance, privacy, and personalization in the mobile-first era. When we talk about bringing machine learning directly to Apple's ecosystem, we're really talking about Core ML. Core ML is Apple's native framework designed to run machine learning models across iOS, iPadOS, macOS, and even watchOS. It provides a unified way for developers to deploy models that handle vision tasks, natural language processing, sound analysis, recommendation systems, and structured tabular data. The genius of Core ML lies in how it is deeply integrated with Apple hardware. It takes advantage of the Apple Neural Engine, the GPU, and the CPU, ensuring that inference is not only fast, but also optimized for the constraints of mobile power and memory. Models are packaged as .ml model files, bundled neatly into the application, making deployment simple and reliable. Core ML turns Apple devices into self-contained AI engines, enabling developers to embed intelligence directly inside everyday apps without depending on the cloud. There are 4 big reasons why developers choose Core ML for production-grade iOS apps. First is performance. By leveraging the Apple Neural Engine, Core ML achieves real-time inference with sub-100 millisecond latency, crucial for vision and AR applications. Second is privacy. Because inference runs entirely on-device, sensitive user data never leaves the phone or tablet, aligning perfectly with Apple's privacy-first philosophy. Third is battery efficiency. Core ML uses kernels and optimizations purpose-built for mobile power constraints, ensuring that AI-enhanced apps don't drain the device in minutes. Finally, there is ecosystem integration. Core ML doesn't exist in isolation. It plugs seamlessly into vision for computer vision, Create ML for model training, ARKit for immersive experiences, and Siri for intelligent assistance. Together, these advantages make Core ML not just a framework, but the default choice for building AI-powered apps in the Apple ecosystem. Developing with Core ML follows a streamlined 5-step workflow. It begins with training the model, which can be done in PyTorch, TensorFlow, or even scikit-learn. Next, the trained model is converted into .ml model format using tools like Core ML tools or via the ONNX conversion pipeline. Then, developers integrate the model into an Xcode project by simply dragging and dropping the .ml model file. The fourth step is to implement Core ML APIs in Swift or Objective-C, enabling the app to call the model for predictions. Finally, inference runs directly on the device's hardware, delivering real-time results to the user. This workflow exemplifies Apple's philosophy of simplicity, abstracting away low-level complexity so that developers can focus on designing intelligent experiences rather than wrangling deployment pipelines. To see Core ML in action, let's consider converting a PyTorch model. Suppose we have a mobile NetV2 model pre-trained on ImageNet. We begin by tracing the model using TorchScript and creating a dummy input tensor. With CoreMLTools.convert, we then specify the input type, in this case, an image with defined dimensions, and generate an ML model file. The output, MobileNet ML model, is now ready to be dropped into an iOS project. This process highlights 3 key principles. First, Core ML Tools is the bridge between training frameworks and Apple's runtime. Second, tracing ensures optimization, making the model efficient for deployment. And third, input specification matters, since Core ML requires precise definitions of shape and type. In just a few steps, a research-grade PyTorch model is transformed into a deployable Apple native asset. Once the NL model file is inside the project, developers can access it with just a few lines of Swift. By wrapping the model with Apple's Vision framework, developers gain high-level abstractions for handling image inputs and classification tasks. For example, you load the model, create a VN Core ML request, and run it on a CG image. The results come back as an array of classification observations, ready to be displayed in the app. This integration showcases the beauty of Core ML's design. Developers write minimal code, while the framework handles pre-processing, model execution, and post-processing. The synergy with Vision is particularly powerful for image-based tasks, ensuring optimized throughput and Swift-friendly data structures. For developers, this means productivity. For users, it means AI-powered features that feel natural, responsive, and deeply integrated into the app experience. Core ML supports a wide range of model categories, each optimized for its domain. Image models enable classification, detection, segmentation, and even style transfer or super resolution. Text models power sentiment analysis, autocomplete suggestions, and real-time translation. Audio models handle wake word detection, sound classification, and speech recognition. Tabular models support recommendation engines, regressions, and decision trees, useful for personalization and structured data analysis. Each category ties directly into specialized Apple frameworks: Vision for images, natural language for text, sound analysis for audio, and ARKit for augmented reality. This ecosystem integration ensures that no matter the type of model, Core ML delivers optimized, domain-specific performance. The diversity of supported models makes Core ML not just a vision tool, but a comprehensive AI deployment framework for all kinds of mobile intelligence. The deployment story with Core ML is one of simplicity and robustness. Models are bundled directly into the app, enabling offline operation. critical for scenarios where connectivity is unreliable. Apple also supports over-the-air model updates, allowing developers to dynamically download newer models from servers as applications evolve. Integration with Apple's frameworks ensures that features like vision, natural language, sound analysis, and ARKit work seamlessly with Core ML models. This ecosystem-first design makes Core ML apps highly portable, efficient, and secure. Developers don't need to reinvent the wheel. They can tap into proven, Apple-optimized building blocks that deliver consistent performance across devices. Despite its strengths, Core ML introduces certain challenges. Model size constraints are a practical limitation, with Apple recommending models stay under 100 megabytes for smooth App Store distribution. Anything larger can trigger download restrictions on cellular networks. Operator support gaps present another hurdle. Not every operation in PyTorch or TensorFlow maps neatly to Core ML, requiring developers to adjust architectures or simplify layers. Optimization requirements are non-trivial. Quantization and pruning are often essential to achieve acceptable latency and memory performance. Finally, debugging complexity is greater on-device than in the cloud, since Apple devices provide less granular logging and profiling. These limitations underscore that while Core ML is powerful, deploying effectively still requires thoughtful design and careful engineering. Core ML is Apple's premier framework for on-device intelligence, and it represents the company's philosophy of combining performance, privacy, and simplicity. Its workflow is straightforward: train, convert, integrate, deploy, but its impact is profound. By leveraging the Apple Neural Engine and GPU, it delivers inference that is fast, private, and energy efficient. Its integration with vision, natural language, sound analysis, and ARKit makes it ideal for building applications that span vision, text, audio, and augmented reality. Developers who adopt Core ML gain the ability to create iOS apps that feel more intelligent, responsive, and personalized than ever before. The message is simple. Core ML isn't just a tool, it is the gateway to building the next generation of mobile AI experiences within Apple's ecosystem. TensorFlow Lite, often abbreviated as TF Lite, is Google's lightweight runtime built specifically for deploying machine learning models on mobile and embedded devices. Unlike its full TensorFlow counterpart, which is designed for training and heavy computation, TF Lite's purpose is singular: efficient inference at the edge. This efficiency comes from three design principles. First, conversion into .tflite format compresses and streamlines models originally trained in TensorFlow, PyTorch, or OnNX, shrinking them for mobile-friendly deployment. Second, it is hardware optimized, fine-tuned to run on ARM CPUs, mobile GPUs, NPUs, and DSPs commonly found in smartphones. Third, it emphasizes on-device processing, meaning inference happens directly on the phone without sending data to remote servers. This ensures applications remain fast, private, and always available, even without connectivity. In a world where billions of people depend on mobile experiences daily, TensorFlow Lite is the backbone that makes AI practical on resource-constrained devices. TF Lite has become the industry standard for Android ML deployment because it aligns perfectly with both developer needs and user expectations. Its performance advantage comes from kernels tuned to ARM hardware, enabling sub-100 millisecond inference for lightweight models. Its battery efficiency is rooted in quantization. Reducing precision to INT8 or FP16 cuts energy usage while preserving most of the model's accuracy. It also boasts broad compatibility, supporting phones, tablets, wearables, and even IoT devices across the fragmented Android ecosystem. Finally, developer integration is smooth. Android Studio offers first-class support while Kotlin and Java APIs make model loading and inference straightforward. These four pillars, speed, efficiency, compatibility, and integration, explain why TF Lite dominates mobile AI. It is not just a runtime, it is the enabler of scalable, real-world ML on Android devices. The development workflow with TF Lite is simple yet powerful, built around 5 steps. Step 1. Train or export your model, whether in TensorFlow, PyTorch, or another framework. Step 2. Convert to .tflite format, shrinking and optimizing it for edge inference. Step 3. Add the .tflite file into your Android Studio project assets, where it becomes part of the application bundle. Step 4. Use the interpreter API in Kotlin or Java to run inference directly inside your app. And Step 5. Optimize with delegates, hardware accelerators like NN API, GPU, or DSP can be invoked to boost performance further. This workflow embodies Google's philosophy of lowering barriers. Developers can go from a trained model to a deployable app with just a few tools and minimal boilerplate code. The cornerstone of TensorFlow Lite is conversion. A typical workflow begins by loading a pre-trained model, such as MobileNet v2 in TensorFlow. Using the TF-Lite Converter API, the model is transformed into .tflite format, with optional optimizations like quantization for efficiency, pruning for size reduction, or operator compatibility selection for targeting specific hardware. Developers can even specify input and output shapes to tailor models for their use case. The output, a compact .tflite file, is vastly smaller and lighter than the original. This step is where models trained on high-end workstations become practical for Android deployment. Without conversion, even the simplest neural networks would be too bulky or slow for mobile devices. With it, they become responsive and efficient, ready to run in the palm of a user's hand. Once converted, running inference on Android requires just a few lines of Kotlin. Developers load the .tflite model from assets into the interpreter, prepare the input, often a pre-processed image tensor, and allocate an output buffer. A single tf-like run call executes inference, delivering probabilities, classifications, or other predictions in real time. For example, a MobileNet model can classify images into 1001 categories with minimal latency. The workflow showcases TF-Lite's beauty. Simplicity on the surface, optimization under the hood. Developers don't need to manually manage pre-processing pipelines or GPU kernels. The framework abstracts complexity, letting them focus on building experiences that delight users while still delivering the speed expected from modern apps. The real magic of TF-Lite comes alive through delegates, plugins that offload computation to specialized hardware. The NN API delegate routes workloads to Android's Neural Networks API, tapping into device-specific accelerators automatically. The GKU delegate harnesses OpenGL or Vulkan for parallelized processing, ideal for vision tasks. The Hexagon DSP delegate targets Qualcomm's DSPs, delivering power-efficient inference on Snapdragon chips. Finally, the Edge TPU delegate integrates seamlessly with Google Coral hardware, offering massive speedups for INT8 models. These delegates enable developers to extract the maximum performance from whatever hardware is available, ensuring that the same model can run efficiently across a fragmented ecosystem. Delegates are what make TF-Lite future-proof. As hardware evolves, apps can tap into new accelerators with minimal code changes. TF-Lite powers an astonishing range of real-world applications. In vision, it drives image classification, face recognition, object detection, OCR, and even pose estimation. In speech and natural language, it enables wake word detection, offline translation, smart replies, and real-time transcription. In IoT and edge environments, it supports predictive maintenance, anomaly detection, and sensor fusion, enabling intelligence in factories and field devices. For mobile UX, it fuels smart keyboards, AR effects, and personalized recommendations. These examples highlight TF-Lite's versatility. It is not limited to one domain, but instead acts as a universal engine for edge intelligence, enabling experiences that cloud-only solutions could never achieve due to latency, privacy, or connectivity constraints. Despite its strengths, deploying with TF Lite introduces challenges. Model size constraints matter because app stores like Google Play impose 100 megabyte limits, forcing developers to compress models aggressively. Operator compatibility issues arise when unsupported TensorFlow operations prevent smooth conversion, requiring architecture adjustments. Device fragmentation across Android means performance must be tested across a wide variety of phones, tablets, and SoCs. Finally, there are performance trade-offs. Smaller quantized models may run faster, but lose some accuracy, requiring developers to balance efficiency with predictive quality. These hurdles are real, but they are not deal breakers. With planning and iteration, developers can overcome them, delivering robust mobile AI experiences at scale. The story of TensorFlow Lite for Android boils down to four truths. First, TF Lite has become the industry standard for mobile AI deployment, trusted by developers worldwide. Second, it offers a streamlined workflow: train, convert, integrate, optimize. Third, hardware acceleration via delegates dramatically boosts performance and efficiency. And fourth, on-device inference delivers benefits no cloud-only solution can match: privacy, speed, and resilience. For developers, TF Lite is more than a tool. It is a gateway to building applications that feel smarter, faster, and more personal, transforming the smartphone into a true AI-powered companion. The case for deploying natural language processing directly on mobile devices is compelling and increasingly urgent. On-device NLP brings 5 major advantages. Privacy is paramount. By keeping text data on the device, user conversations, messages, and queries never leave the phone, reducing risk and building trust. Latency improves dramatically. Instead of waiting for a network round trip, users receive instant responses, making interfaces feel natural and seamless. Cost is reduced because fewer server calls translate into lower infrastructure expenses, making large-scale deployment more affordable. Personalization becomes richer since models adapt to user context locally, learning patterns of typing, vocabulary, and preferences without exposing that data externally. And finally, reliability is enhanced because systems continue to work offline, whether it's for translation, messaging, or voice commands. Together, these drivers explain why the AI industry is pivoting toward on-device NLP as the standard for next-generation mobile experiences. On-device NLP is not limited to a single capability. It spans a spectrum of tasks that make everyday interactions smarter. Text classification powers spam filters, sentiment analysis in messaging apps, and topic labeling for content feeds. Sequence labeling drives named entity recognition, intent detection in voice assistants, and part-of-speech tagging for grammar tools. Generation tasks like autocomplete and predictive text bring fluidity to typing, while suggested replies accelerate communication. Lightweight speech-to-text and translation models enable offline dictation and multilingual conversations, while conversational AI harnesses distilled transformers for basic dialogue, providing instant responses without connectivity. These tasks, though computationally complex in the cloud, become approachable at the edge through optimization, enabling phones to act as intelligent assistants in the user's hand, not just portals to remote servers. The challenge with NLP is that models like BERT are notoriously large, often hundreds of megabytes. For edge deployment, specialized architectures make efficiency possible. Compressed transformers, such as DistalBERT, shrink models by 40%, while retaining 97% of BERT's performance. TinyBERT is even more radical, delivering up to 9.4 times faster inference. MobileBERT is engineered specifically for mobile hardware. Another approach is parameter sharing, exemplified by Albert, which reduces parameters by 18 times by reusing weights across layers. Beyond transformers, lightweight models like fast text or bag of embeddings still serve well for classification tasks. And in ultra-low resource environments, RNN Lite or GRU variants fit within microcontrollers. These architectures reflect the spectrum of trade-offs available, from compressed transformers for smartphones to lean RNNs for IoT. The message is clear. With the right architecture, NLP at the edge is not just possible, it is practical. Deploying on-device NLP follows a disciplined workflow. It begins with training or fine-tuning a model in PyTorch or TensorFlow on domain-specific data. Next comes optimization, pruning redundant parameters, quantizing weights to INT8, or distilling knowledge into smaller student models. Once optimized, the model is exported into a deployment format such as OnNX, TF-Lite, or Core ML. From there, the model is integrated into mobile apps, using TF-Lite on Android or Core ML on iOS. Finally, inference runs with hardware delegates, NN API for Android, Apple Neural Engine for iOS, or GPUs where available. The emphasis is on optimization at every stage. Without pruning, quantization, and distillation, deployment would be infeasible. With then, Edge NLP becomes lightweight, efficient, and ready for production-scale apps. Let's walk through a concrete example. Using Hugging Face transformers, we load a Distilbert model pre-trained on text classification. With TensorFlow Lite's converter, we transform it into .tflite format. During conversion, we apply quantization, shrinking model size from 240 megabytes to 60 megabytes. This compact .tflite file can now be embedded in an Android application. The workflow illustrates 3 lessons. First, Hugging Face provides accessible pre-trained models. Second, quantization is essential for making the mobile ready. And third, tflite integrates seamlessly with Android. The end result is a powerful transformer running entirely on-device, providing instant predictions without ever touching a server. On the iOS side, Core ML plays the same role. Here, a Distilbert model is traced using TorchScript, then converted with Core ML tools into .ml model format. This file integrates directly into Xcode, packaged with the app, and runs on Apple's Neural Engine. The advantages are twofold. Hardware optimization ensures that inference is fast and battery efficient, while ecosystem integration means the model works seamlessly with Siri, ARKit, or the natural language framework. For developers, the message is simple. PyTorch and Hugging Face models can make the leap to iOS with minimal friction. For users, it means their iPhones and iPads gain responsive, private, and reliable NLP experiences. Efficiency is achieved not just through architecture, but through aggressive optimization. Quantization shrinks models by converting FP32 to int8, making them 4 times smaller and up to 4 times faster, with only 1 to 2% accuracy loss. Pruning cuts away low-importance attention heads and layers, reducing parameters by 30 to 50%. Distillation trains smaller student models from larger teachers, sometimes achieving 90% size reduction while retaining key knowledge. Operator fusion speeds up attention kernels by combining operations, reducing memory overhead and kernel launches. These optimizations are not optional extras. They are the backbone of Edge NLP, transforming impractical research models into deployable mobile assets. On-device NLP is already reshaping mobile experiences across industries. In keyboard apps, it enables predictive text, grammar correction, and personalized suggestions. In messaging, it powers spam detection, auto-reply suggestions, and sentiment analysis without sending messages to the cloud. In healthcare, it drives offline symptom checker chatbots and medical term recognition tools that protect sensitive patient data. In finance, it enables transaction categorization and on-device fraud detection, catching anomalies in real time. These use cases prove that on-device NLP is not an abstract concept. It is a tangible enabler of applications that are smarter, faster, and more private than ever before. Despite its promise, on-device NLP is not without hurdles. Model size remains a challenge. Standard transformers of 300 megabytes plus must be compressed aggressively. Framework limitations exist, as TF-Lite and Core ML have incomplete operator coverage for advanced NLP layers. Battery and thermal constraints can cause devices to overheat or drain quickly during sustained inference. Finally, there are trade-offs. Every optimization risks reducing accuracy and balancing speed, efficiency, and user experience is a delicate art. These challenges require thoughtful engineering, extensive testing, and realistic expectations. Success in on-device NLP comes not from eliminating trade-offs, but from managing them wisely. Experience has yielded best practices for deploying NLP at the edge. Always start with mobile-optimized models such as DistilBERT or MobileBERT rather than attempting to compress full BERT. Apply quantization-aware training, QAT, during fine-tuning to preserve accuracy under INT8 deployment. Test across device tiers, from flagship phones to mid-range Android devices, to ensure broad compatibility. Finally, build hybrid pipelines where lightweight models handle fast. Local inference and cloud services provide fallback for heavier tasks. A common pitfall is ignoring Android hardware diversity, leading to models that shine on flagships but fail on budget devices. Best practices prevent such failures, ensuring robustness across the full device spectrum. The lessons of on-device NLP can be condensed into 4 key insights. First, the benefits are clear: fast, private, cost-effective language understanding directly on mobile devices. Second, the right models matter. Tiny and distilled transformers combined with quantization unlock mobile readiness. Third, frameworks define success. TF-like for Android and Core ML for iOS are the paths to efficient deployment. Fourth, hybrid architectures win in practice, balancing speed, privacy, and scalability. The call to action is straightforward. Start small, optimize aggressively, and validate across devices. On-device NLP is not the future, it is the present, already shaping how billions of users experience intelligent language interfaces every day. When deploying artificial intelligence on mobile devices, one factor quickly rises to the top: power consumption. Unlike cloud servers, smartphones and wearables operate under strict battery limits. Users expect features that are fast and intelligent, but they also demand all-day battery life. If an app drains power too quickly, users will abandon it, and adoption metrics will plummet. AI workloads, especially vision, natural language, and augmented reality, are compute-intensive, often consuming 2 to 5 times more power than standard operations. Sustained inference generates heat, which not only shortens battery life, but also triggers thermal throttling, degrading performance and user experience. The lesson is clear: optimizing power is not an afterthought. It is central to user retention, device reliability, and successful adoption of mobile AI features. Where does all this power go? The biggest culprit is compute operations. Convolutions in vision models and attention mechanisms in transformers consume enormous energy. Next comes sensor usage. Keeping the camera or microphone active or frequently polling accelerometers and gyroscopes quickly depletes batteries. Third is inefficient code. Busy wait loops, failure to leverage hardware accelerators, or reliance on CPUs instead of NPUs waste energy unnecessarily. Engineers can even use thermal imaging to identify hotspots, revealing which components consume the most power during AI workloads. Understanding these sources of drain is the first step toward reclaiming efficiency and extending device life. Hardware provides powerful levers for energy savings. Neural processing units, NPUs, are game changers, delivering up to 100 times energy efficiency compared to CPUs for AI workloads. GPUs, when used via delegates, exploit parallelism to achieve 4 to 8 times better efficiency than CPUs. Digital signal processors, DSPs, excel at audio and sensor workloads, running 20 times more efficiently than CPU-based inference. The key is to choose the right delegate. On Android, that means using NNAPI. On iOS, Core ML with the Apple Neural Engine ensures optimized performance. By routing workloads to the right hardware, developers unlock dramatic power savings without sacrificing accuracy or user experience. Software design choices are just as important. Quantization reduces model weights from FP32 to INT8, cutting compute and memory needs by up to 75% with minimal accuracy loss. Tuning and distillation slim models by 30 to 90%, making inference lighter and faster. Runtime optimizations like batching and caching reduce redundant computations by grouping API calls and reusing results. Finally, lazy loading ensures that large models are loaded only when needed, not at application startup, saving memory and preventing background drain. These techniques transform heavyweight AI models into lean, battery-conscious assets suitable for daily mobile use. One of the smartest ways to conserve power is through duty cycling. Instead of running sensors continuously, systems can activate them strategically. Motion triggers use accelerometer data to wake AI models only when movement is detected. Keyword spotting relies on lightweight audio models to activate full NLP pipelines only on command. Camera activation can be limited to essential moments with efficient use of preview callbacks. Even pre-processing tasks like FFT can be offloaded to low-power microcontrollers, reducing load on the main device. With careful duty cycling, sensor power consumption can drop by 40 to 80%, while responsiveness remains intact. Sustained AI workloads inevitably generate heat, and heat leads to throttling, reducing device performance. To manage this, developers must monitor device thermal states using platform APIs. They can limit inference frame rates, for example, running vision models at 15 FPS instead of 30 under high thermal load. Lightweight models can run continuously, while heavier models activate only on demand. Adaptive quality settings ensure that user experience is maintained even as the system scales back performance to protect hardware. Thermal management is not just about efficiency, it is about preserving reliability and user trust. Another effective approach is hybrid inference. On-device processing handles quick predictions under 100 milliseconds, privacy-sensitive data, offline functionality, and continuous monitoring tasks. The cloud handles computationally intensive workloads, rare queries, or tasks requiring vast datasets. Consider a keyboard. The edge runs autocomplete and next word prediction, while the cloud performs grammar checks and style suggestions. Or a camera. The device detects objects and faces locally, while the cloud applies enhancement and scene interpretation. This division of labor balances power, performance, and scalability, while keeping users satisfied. Developers cannot optimize what they cannot measure. Android engineers use tools like Android Studio Profiler for CPU, GPU memory tracking, Battery Historian for energy consumption analysis, and command line tools like ADB Shell Dumpsys Battery Stats. On iOS, Xcode Instruments Energy Log, Energy Gauge, and Metric Kit provide real-time profiling and reporting. For embedded devices, tools like Jetson Tegrastats or external power monitors offer precise measurements. These tools provide visibility into the battery impact of each feature, enabling data-driven optimization. Several best practices consistently deliver results. Use smaller models like MobileNet or Distilbert, designed for mobile environments. Quantize aggressively with INT8 or mixed precision, wherever accuracy allows. Profile per feature, measuring energy costs before shipping. Provide user controls, such as a low-power mode toggle. Conduct A/B testing to balance user experience improvements against power trade-offs. Always include thermal testing, simulating extended use in various environments. Remember, once an app crosses 1% battery drain per minute, users notice, and many will uninstall. Real-world companies illustrate these practices. Messaging apps like WhatsApp and Signal run on-device NLP for typing suggestions using quantized transformers and context-aware caching to save power. Social media platforms like Snapchat and Instagram run AR filters at lower frame rates and optimize pre-processing to conserve energy. Wearables like Fitbit and Apple Watch rely heavily on duty cycling and hierarchical model cascades, ensuring all-day ML performance on tiny batteries. These examples prove that power-aware AI is not theoretical. It is a competitive necessity. The story of power management in mobile AI boils down to 4 truths. First, battery life is critical. Without it, users abandon apps. Second, optimization must be multi-level. Hardware accelerators and software compression together deliver real savings. Third, strategic trade-offs like duty cycling and hybrid inference balance efficiency with user satisfaction. And fourth, real device testing is essential. Only profiling on target devices validates whether optimizations work. The big picture is clear. Successful mobile AI is not just about building smarter models. It is about designing holistic systems that balance intelligence with efficiency, ensuring AI enhances devices without draining the very power that keeps them alive. When we think about the future of artificial intelligence, one of the most pressing questions is not simply what can AI do, but rather how can AI do it responsibly? The title of this presentation, Privacy Considerations for On-Device AI, captures this tension perfectly. Artificial intelligence is no longer a technology reserved for the cloud, for massive centralized servers, or for research labs. Increasingly, AI is moving closer to the user, into our smartphones, wearables, personal computers, and even home appliances. This shift, known as on-device AI, unlocks tremendous potential for speed, personalization, and autonomy. Yet, it also raises an equally important issue: privacy. Building AI that respects user trust and complies with data protection laws is not just a technical necessity, but a moral and business imperative. As we move through this document, we'll explore why privacy matters, the unique advantages and risks of on-device AI, the principles and techniques that developers should adopt, and practical examples that illustrate the right way forward. Privacy is not an abstract concern. At its core, it is about protecting people's most sensitive information, their health metrics, their biometric identifiers, their personal communications. When individuals use an AI-enabled device, they are, whether knowingly or not, exposing parts of their lives that are deeply private. If this information is mishandled or leaked, the consequences can be devastating, ranging from identity theft to reputational harm, from financial fraud to state surveillance. This is why trust becomes the foundation of adoption. Every time there is a data breach, public trust in technology takes a blow and adoption slows. We've seen this in industries ranging from healthcare to finance, where confidence is directly linked to responsible data handling. On top of that, regulations such as GDPR in Europe, CCPA in California, and HIPAA in healthcare settings create strict boundaries for how data can be used, stored, and shared. Violations are not only reputational disasters, but also carry heavy financial penalties. Finally, privacy matters because it is a human right. Data minimization, processing only what is essential and doing so locally on device, gives users peace of mind while simultaneously serving as a crucial safeguard in today's interconnected world. The beauty of on-device AI lies in its natural alignment with privacy-first principles. By processing data directly on the user's device, raw data never needs to leave the safety of personal hardware. This eliminates transmission risks and reduces exposure to third parties. Imagine a smart keyboard predicting the next word you'll type. It can analyze your text locally without ever uploading your private messages to a server. Fewer network connections mean fewer potential attack surfaces. Hackers can't steal what was never transmitted. Moreover, on-device AI supports offline-first operation. A health monitoring app, for example, can continue to analyze heart rate or sleep patterns without requiring constant internet connectivity, shielding users from network-based vulnerabilities. Finally, the personalization offered by local processing is both powerful and private. Systems can adapt to an individual's behavior while avoiding the centralization of sensitive data. In this sense, on-device AI doesn't just compete with cloud-based AI on convenience. It surpasses it in terms of privacy by design. Yet, no system is without risks. On-device AI must contend with its own set of privacy vulnerabilities. One concern is model leakage. Adversaries with enough technical skill may reverse engineer model weights to infer details about the training data. Imagine if a model trained on personal conversations accidentally retained and revealed fragments of them. A second risk lies in side-channel leaps. Even without direct data access, subtle patterns such as power consumption, processing time, or hardware noise can inadvertently expose what a user is doing. Then there is the problem of unintended storage. Sensitive inputs, if cached or logged improperly, may remain on a device longer than intended, creating long-term exposure. Finally, developers must guard against overcollection. requesting permissions far beyond what is necessary. For instance, a photo editing app has no legitimate reason to access your contact list. Each of these risks reminds us that simply moving AI to the device is not enough. Rigorous safeguards must be built in from the start. The antidote to these risks lies in the philosophy of privacy by design. This principle insists that privacy is not an afterthought. It must be embedded from the very first design decision. Data minimization should be the guiding star. Only collect and process what is absolutely necessary. On-device preprocessing further strengthens privacy, ensuring that any data destined for the cloud is anonymized or sanitized before leaving the device. Transparency is another pillar. Users must clearly understand what permissions they are granting and how their data contributes to AI functionality. Beyond transparency comes control. Intuitive opt-in and opt-out mechanisms empower users to decide whether or not they wish to share sensitive information. Finally, privacy by design demands secure defaults. Encryption, sandboxing, and strict process isolation should not be optional extras. They should be baked into the system, relieving the user of complex configuration tasks. By following these principles, developers create systems that both respect users and satisfy regulators. To operationalize privacy, developers can rely on advanced technical strategies. Secure enclaves and encrypted storage provide a hardened outer shell, isolating sensitive computations from the rest of the device. Within this layer, federated learning emerges as a revolutionary technique. Rather than uploading raw data, devices share only model updates, an approach that allows collective intelligence without compromising individual privacy. At the very core lies differential privacy, which injects carefully calibrated noise into datasets to prevent the re-identification of any single individual. Together, these methods form a multi-layered defense, much like concentric circles of armor around a valuable core. By combining them, developers can preserve the utility of AI while dramatically reducing privacy risks. Laws around the world increasingly shape how AI must treat personal data. Under the GDPR, individuals have the right to an explanation for algorithmic decisions. Explicit consent must be obtained before processing data, and users can demand erasure of their personal information. The California Consumer Privacy Act emphasizes opt-outs, requiring businesses to give users the ability to prevent the sale or sharing of their data. It also mandates clear disclosure of data practices. In healthcare, HIPAA sets some of the strictest rules. Only minimal necessary disclosures are allowed, and any breach must be promptly reported. Beyond these legal requirements, developers are expected to maintain thorough documentation of data flows and model behaviors. This is not mere paperwork. It is evidence of accountability. By proactively aligning on-device AI with these regulations, organizations protect themselves from liability and, more importantly, signal to users that their privacy is taken seriously. Consider a real-world scenario, a smart keyboard designed for text prediction. This is one of the most privacy-sensitive use cases imaginable because it interacts directly with the user's personal writing. With on-device processing, the keyboard can learn from the user's typing without transmitting raw text to a server. Federated learning ensures that only anonymous gradient updates are sent back to improve the central model, never the text itself. To strengthen this further, differential privacy can add statistical noise, ensuring no individual typing patterns are ever revealed. This layered approach allows the keyboard to get smarter over time, while maintaining the confidentiality of each user's words. It is a powerful example of how advanced privacy techniques and on-device AI work hand in hand to protect sensitive personal interactions. Another compelling illustration is face unlock on smartphones. At first glance, storing facial data might seem like a serious privacy risk, yet modern systems mitigate this through secure enclaves where mathematical representations of the face are stored exclusively in trusted hardware. Authentication happens entirely on-device, meaning your biometric data never leaves your phone. Over time, the system can adapt to changes in your appearance, such as growing a beard or wearing glasses, by retraining locally with new samples. This balance, highly secure, privacy preserving, yet user friendly, is what makes edge AI not just acceptable, but desirable. It provides a glimpse into how convenience and privacy need not be at odds when the architecture is carefully designed. For developers, protecting privacy requires disciplined habits. Encryption must be universal, covering both model files and data, whether stored or transmitted. Logging should be minimal, temporary, and accompanied by clear retention rules. Sandboxing ensures that AI processes are walled off from the rest of the app environment, reducing the risk of leaks. Consent dialogues should not be buried in legal jargon, but presented in plain language that users understand. Finally, privacy audits should become a routine part of development, identifying hidden leaks before they reach the public. When these best practices are integrated into everyday workflows, privacy becomes not an obstacle, but a natural extension of responsible design. Even well meaning teams can fall into traps that undermine privacy. One common pitfall is unnecessary reliance on the cloud. If on device inference is sufficient, why expose users to extra risks by sending their data to external servers? Another error is excessive data retention. Keeping raw images, audio, or text longer than needed creates a ticking time bomb for breaches. Third-party libraries also present hidden dangers. Many silently harvest additional data beyond the needs of your app. And finally, inference opacity. The failure to clearly show users when and how their data is being processed breeds distrust. Avoiding these pitfalls is as much about discipline as it is about design. As we conclude, let's step back and distill the essence of this discussion. First, privacy is not a burden. It is a natural fit for on-device AI. By keeping data local, on-device AI is inherently aligned with privacy-first principles. Second, layered protections, federated learning, secure enclaves, differential privacy can be combined to form a robust shield around users. Third, regulatory compliance is not optional. It is a minimum standard, one that must be met with foresight and diligence. And finally, privacy itself can be a differentiator. In a world where users are increasingly wary of surveillance, companies that prioritize trust gain a clear competitive edge. By building AI systems that respect privacy from the ground up, we do more than obey the law. We create experiences that are both powerful and humane. That is the future of responsible AI. When we talk about artificial intelligence at scale, the conversation often focuses on the models, the neural networks, the algorithms, the hardware accelerators. But the true foundation of AI lies deeper. It is in the data pipelines that feed these systems. This page sets the stage by reminding us that modern AI systems require robust data infrastructure. Without a solid foundation, no model, no matter how advanced, can perform effectively. ETL, extract, transform, load, and its newer counterpart, ELT, extract, load, transform, are two architectural approaches that form the backbone of scalable workflows. These workflows take raw, messy, unstructured information from countless sources and convert it into the structured, reliable, and usable form that AI depends on. Think of ETL and ELT as the circulatory system of AI infrastructure. They carry the lifeblood of data from where it originates to where it can be harnessed for intelligence. Throughout this discussion, we'll explore why pipelines matter, how ETL and ELT differ, the tools and best practices that support them, and how they directly enable advanced AI applications. Why do pipelines matter so much? The answer is threefold: foundation, automation, and scalability. First, pipelines are the foundation of AI because models are only as good as the data they ingest. High volumes of clean, structured data are not optional. They are the precondition for reliable predictions. Second, pipelines automate the process of moving from raw data to usable insights. Imagine trying to manually clean millions of rows of log files or normalize petabytes of sensor readings. It would be impossible without automation. Pipelines reduce human error and accelerate workflows, ensuring that data scientists spend time on analysis, not cleaning. Finally, scalability is crucial. A well-designed pipeline is not a one-off script. It is a reproducible system that grows with your data needs. Whether you start with 100,000 rows or expand to billions of entries streaming in real time, a robust pipeline ensures consistency. In short, pipelines are not just plumbing, they are the essential architecture that allows AI to operate with speed, accuracy, and reliability. ETL stands for Extract, Transform, Load, a sequence that has defined data engineering for decades. Extraction comes first, gathering data from multiple sources, databases, APIs, flat files, logs, each with its own formats and quirks. Next comes transformation, where the raw information is cleaned, normalized, and shaped. This is where business rules are applied, duplicates removed, formats standardized, and aggregations created. Finally, loading takes place. The processed, structured data is deposited into a target system, such as a warehouse or database, optimized for downstream consumption. ETL has historically been the standard approach for business intelligence and batch processing workflows. It assumes a world where data volumes, though large, are still manageable, and where most insights can be produced through scheduled, periodic jobs. In this sense, ETL reflects the legacy of on-premises systems, where careful pre-processing was essential to ensure that downstream systems could handle the workload efficiently. The evolution of cloud-native infrastructure brought a new paradigm, ELT, or Extract, Load, Transform. Here, the order is reversed. Data is first extracted, then immediately loaded in its raw form into a data lake or warehouse. Only afterward does transformation take place, leveraging the immense compute power of modern storage systems. This approach recognizes that today's workloads often involve unstructured or semi-structured data arriving in massive volumes. ELT allows organizations to preserve raw data, transforming it only when specific use cases demand it. For AI, this flexibility is vital. Different teams may require different transformations from the same dataset, and ELT architecture ensures the raw data is always available for new purposes. This approach is optimized for large-scale, cloud-based workflows where scalability and adaptability take precedence. It is not that ETL is obsolete, but that ELT represents the natural adaptation to a new technological landscape. Although ETL and ELT share the same ultimate goal, integrating data for analysis, their philosophies diverge in execution. ETL transforms data before it is loaded, while ELT transforms data after it is stored. ETL is typically best for smaller, more structured datasets, often in legacy environments. It separates the transformation process from the storage environment, requiring additional processing layers. ELT, on the other hand, thrives on scale. It is designed for raw, large datasets and leverages the computational strength of cloud warehouses like Snowflake or BigQuery. In practice, ETL suits organizations that need tightly controlled, structured workflows, while ELT appeals to those embracing flexible, cloud-native design. Neither is inherently superior. Both have their place depending on workload, infrastructure, and scale requirements. The key is understanding when each is the right tool. Pipelines are not abstract concepts, they enable concrete AI use cases. First, they support data pre-processing at scale, preparing text, images, and audio for model training. Without pipelines, preparing multimodal datasets would be a nightmare. Second, pipelines fuel real-time analytics. Imagine IoT sensors streaming environmental data. Pipelines allow AI to act immediately, detecting anomalies or predicting failures. Third, pipelines drive feature engineering, automatically creating and transforming variables that models use for prediction. This step is often the difference between mediocre and high-performing AI. Finally, pipelines underpin knowledge bases for large language models, ensuring structured, high-quality information flows into training and retrieval systems. In each case, Pipelines are the invisible machinery that enables AI to function in practice. A thriving ecosystem of tools supports ETL and ELT workflows. For ETL, long-standing enterprise tools like Talend, Informatica Power Center, Apache NiFi, and Microsoft SSIS dominate. For ELT, newer cloud-native platforms like dbt, Snowflake, BigQuery, and Databricks lead the way. Orchestration tools like Apache Airflow, Prefect, Dagster, and Luigi ensure that pipelines run smoothly and reliably. On the streaming side, Apache Kafka, Flink, Spark Streaming, and AWS Kinesis handle real-time flows. Each tool has its role. Some excel at transformation logic, others at orchestration, still others at handling velocity. Together, they form a comprehensive toolkit for building pipelines that meet diverse needs, from batch analytics to real-time AI decision-making. Designing effective pipelines requires discipline. Error handling must be robust, with automated retries and transparent logging to ensure resilience. Data quality must be continuously monitored. Automated tests and alerts should flag anomalies before they poison downstream models. Modularity is another essential practice. Pipelines should be built as reusable components that scale gracefully with growing data volumes. Finally, alignment with downstream AI needs is crucial. A pipeline that fails to deliver the right features or the right freshness of data undermines the models it serves. By embedding these best practices, teams create pipelines that are not just functional, but dependable and future-proof. As we wrap up, let's return to the big picture. ETL represents the traditional approach, structured, preload transformations with a mature ecosystem behind it. ELT represents the modern approach, flexible, post-load transformations optimized for cloud-native AI. Both have value, and the choice depends on workload characteristics, infrastructure, and scale. The ultimate takeaway is this: robust pipelines are non-negotiable for AI. They are the quiet enablers of every predictive model, every intelligent application, every breakthrough in AI deployment. Without them, AI remains theory. With them, AI becomes reality. Artificial intelligence today is no longer just about building clever models. It is about managing an entire ecosystem of moving parts. Training, testing, deployment, and monitoring all rely on complex workflows that span across different systems, data sources, and environments. The opening page of this document sets the stage by introducing Apache Airflow as a modern solution for these challenges. Airflow is more than just a scheduling tool. It is a full orchestration platform that ensures automation and reliability across the entire machine learning lifecycle. The reason this matters is that AI is not static. Models need retraining, data needs refreshing, and workflows must adapt to new requirements. Without orchestration, teams risk relying on manual processes that cannot scale. Airflow provides a programmable, reproducible framework where workflows are treated as code, enabling consistency, transparency, and automation. As we move deeper into this presentation, we will see why Airflow has become the backbone of production-grade AI infrastructure. Modern AI systems are inherently multi-step. You don't simply feed data into a model once and call it done. Instead, you might first extract data from multiple sources, pre-process and clean it, engineer features, train models, run evaluations, and finally deploy them into production environments. Each of these steps depends on the success of the previous one. Without orchestration, these dependencies quickly spiral into chaos. Manual processes inevitably break down as scale increases, creating errors and missed steps. Dependency management becomes fragile. One late running job can cascade into delays across the system. Reliability suffers most. Without automation, recovering from failures or ensuring consistent execution across environments becomes nearly impossible. Orchestration solves these problems by treating workflows as structured, repeatable, and automated processes. In the same way that an air traffic controller coordinates dozens of flights in and out of an airport, Airflow coordinates hundreds or even thousands of interdependent tasks, ensuring that everything runs on time and in the right order. Apache Airflow is an open source platform built for programmatically authoring, scheduling, and monitoring workflows. At its core, it introduces the concept of directed acyclic graphs, or DAGs, as the framework for defining task dependencies and execution order. What sets Airflow apart is that these DAGs are defined as Python code. This makes workflows both expressive and maintainable, unlike legacy approaches that relied on verbose XML or rigid configuration files. Airflow comes with a built-in scheduler that can handle both time-based and event-driven triggers. This means a workflow can run every night at midnight, or it can run whenever a file lands in a directory or data arrives in a streaming pipeline. The platform also provides a rich monitoring and visualization interface, so data engineers and ML practitioners can see at a glance whether their workflows are succeeding, failing, or waiting on dependencies. With its extensible architecture, Airflow integrates seamlessly with external systems, from databases to cloud services, making it a powerful hub for AI operations. Airflow shines through a set of key features that make it especially suitable for AI workflows. First, its advanced scheduling capabilities allow teams to define highly complex dependencies between tasks. Conditional branching, dynamic task generation, and context-based scheduling all become possible. Second, its robust error handling ensures that workflows can recover from inevitable failures. Configurable retries, failure recovery paths, and service-level agreement monitoring mean that pipelines continue running even when things go wrong. Third, the ecosystem surrounding Airflow is vast. More than 700 pre-built operators exist for interacting with common systems such as BigQuery, Snowflake, Databricks, Kubernetes, and major cloud providers. This makes integration frictionless. Finally, Airflow scales gracefully. Whether running on a single laptop for a lone data scientist or across Kubernetes clusters executing thousands of concurrent tasks, Airflow adapts to your scale. These capabilities make it particularly well-suited for ML workflows where tasks often span data preparation, training, and deployment pipelines with intricate interdependencies. Airflow is not theoretical. It powers some of the most advanced AI systems in the world. In data pipeline orchestration, it ensures that ETL jobs feed feature stores consistently, keeping training and inference aligned with fresh data. In training pipeline automation, Airflow can schedule hyperparameter tuning jobs, periodic retraining, or controlled A/B testing for model deployment. For modern generative AI, Airflow orchestrates retrieval-augmented generation workflows, managing embedding updates, refreshing vector databases, and ingesting new content to keep systems accurate. Netflix is a prime real-world example. They rely on Airflow to orchestrate feature generation, model training, and deployment for their recommendation systems. With billions of events processed daily, Netflix demonstrates Airflow's ability to operate at staggering scale while maintaining precision and reliability. These use cases highlight why orchestration is not just a convenience. It is the operational backbone that enables AI to function in dynamic, data-rich environments. Airflow's architecture is designed to separate concerns while maintaining coordination. The web server UI provides visibility into DAGs, pipeline runs, and overall system health. The metadata database stores everything about DAG definitions, task runs, and execution states. The scheduler orchestrates when tasks should run, based on both time triggers and dependency completion. Executors, whether local, Celery-based, or Kubernetes-powered, determine how tasks are distributed and executed. Workers are the engines that actually run task instances and return results. At the logical level, DAGs define workflow structures and dependencies, while operators serve as reusable templates for specific task types such as Python functions, Bash commands, or SQL queries. Together, these components create a modular yet cohesive system. This modularity is what enables Airflow to scale from small teams running a handful of workflows to global enterprises orchestrating thousands of tasks daily. Airflow is powerful, but like any tool, it must be used with discipline. First, tasks should be idempotent, meaning they produce the same result no matter how many times they are run. This ensures retries and backfills do not create inconsistencies. Second, everything should be under version control. DAGs should live in Git repositories alongside model code, enabling traceability and supporting CI/CD practices. Third, comprehensive monitoring is essential. Airflow metrics should be integrated with observability systems to provide real-time alerts on pipeline health. Fourth, dynamic DAGs can unlock scalability, such as generating separate workflows for each customer or automating hyperparameter sweeps. At the same time, developers must avoid the pitfall of creating overly complex DAGs that become impossible to maintain. The best approach is to break large workflows into smaller, manageable sub-DAGs. Following these practices ensures that Airflow deployments remain both reliable and sustainable as systems grow. As we conclude, it becomes clear why Airflow is widely regarded as the backbone of AI infrastructure. By providing a coordination layer for machine learning systems, it ensures reliability, reproducibility, and transparency. DAGs as code serve as self-documenting workflows, creating a level of clarity and consistency that manual processes simply cannot achieve. Airflow scalability allows it to serve both small experiments and enterprise-scale ML platforms with equal effectiveness. The lesson here is to start small, iterate, and grow. By embedding orchestration early, teams prepare themselves for future scale while avoiding chaos. Ultimately, Airflow is not just a tool. It is the foundation for building AI systems that can be trusted in production. When we think of modern AI systems, one of the biggest shifts is the movement from static, batch-driven processes to dynamic, real-time intelligence. This first page introduces Apache Kafka as a cornerstone technology for building responsive AI systems powered by fresh, actionable data. Traditional workflows relied heavily on batch processing, where data was collected, stored, and analyzed hours or even days after it was generated. In today's world, that lag is unacceptable. Real-time systems are no longer a luxury, they are a necessity. From fraud detection in finance to monitoring industrial IoT sensors, from recommendation engines on streaming platforms to adaptive natural language models, the demand for instantaneous insight is universal. Apache Kafka, born at LinkedIn and now nurtured by the Apache Software Foundation, offers the infrastructure to make this possible. It is not just a message broker. It is the foundation for real-time, event-driven AI. This page sets the stage for a deeper journey into why streaming data matters, how Kafka works, and how it integrates into the broader AI ecosystem. Batch processing once dominated the analytics world. Data would be collected perhaps overnight and processed the next morning to generate reports. But in a competitive landscape where milliseconds matter, that delay creates blind spots. Streaming data solves this by reducing the gap between generation and action to near zero. AI applications thrive on real-time requirements because stale data produces poor predictions. Imagine an autonomous car relying on yesterday's road conditions. It would be useless. Instantaneous decision-making is equally important. Low latency processing allows businesses to detect credit card fraud as it happens, or recommend a video while a user is still browsing. Beyond responsiveness, streaming enables continuous learning. Models can adapt to evolving conditions, whether that's a change in consumer behavior, a new cyber threat, or fluctuating demand in supply chains. In this sense, streaming is not just about speed, it is about survival. It ensures that AI remains contextual, relevant, and accurate in an ever-changing environment. Apache Kafka is best understood as a distributed streaming platform built for scale, durability, and performance. At its heart, Kafka enables applications to publish and subscribe to streams of records in real time. This publish-subscribe model ensures that data flows seamlessly from producers, applications or services generating events, to consumers that act on them. Kafka's durability sets it apart. Rather than being ephemeral, data streams are stored in a fault-tolerant, persistent way ensuring no data loss. This makes Kafka not only a pipeline, but also a reliable storage layer. Its real-time processing capabilities allow applications to respond instantly as data arrives, which is critical for AI workloads. And perhaps most importantly, Kafka scales horizontally. Clusters of Kafka brokers can handle hundreds of megabytes per second, serving thousands of clients simultaneously. What began as an internal project at LinkedIn has since become the global standard for real-time pipelines, powering everything from banking systems to global e-commerce platforms to AI-driven personalization engines. To understand Kafka's power, we must first grasp its fundamental building blocks. Producers are applications that publish data to Kafka, sending events into specific topics, which act as named feeds or categories. Topics organize streams of information, much like folders organize files. Consumers are applications that subscribe to these topics, processing or storing the data as needed. Behind the scenes, Kafka is composed of brokers, individual server instances that store and distribute topic data. A group of brokers working together forms a cluster, ensuring high availability and resilience. These concepts are deceptively simple, yet they unlock massive scalability. For example, one topic might handle log streams from thousands of web servers, while another manages video analytics data for real-time computer vision tasks. By decoupling producers from consumers, Kafka creates a flexible architecture where data can be used by multiple applications simultaneously, fueling diverse AI pipelines without duplication or delays. Kafka's sweet spot is in AI applications that require constant access to fresh insights. For log streaming, Kafka serves as the backbone for monitoring systems that power dashboards and alerting mechanisms. In knowledge streaming, Kafka feeds large language models with real-time, contextual information, helping them avoid staleness and hallucinations. In media streaming, Kafka delivers images, videos, and audio to computer vision and natural language systems, ensuring models process the latest content. Most critically, Kafka powers feature engineering pipelines, delivering real-time features for training and inference. Imagine a fraud detection model. Kafka ensures that the most recent transaction features are available instantly, so the model can catch anomalies in flight rather than after the fact. By extracting, transforming, and serving features on the fly, Kafka allows AI models to remain sharp and adaptive, no matter how fast conditions evolve. Kafka does not exist in isolation, it integrates seamlessly into the broader AI ecosystem. Combined with distributed processing frameworks like Apache Spark and Apache Flink, Kafka streams can be transformed, aggregated, and analyzed in real time. When paired with Airflow, workflows can be orchestrated around streaming events. Imagine retraining a model whenever new batches of data arrive. Kafka also connects directly to feature stores such as Feast, ensuring that standardized, low-latency features are available for both training and inference. Even model serving platforms like TensorFlow Serving can consume Kafka streams directly, enabling continuous inference pipelines. This web of integrations transforms Kafka into more than just a messaging system. It becomes the nervous system of AI infrastructure, connecting every organ, data sources, pre-processing layers, training frameworks, and inference engines into a living, adaptive whole. Deploying Kafka in AI systems requires strategic planning. First, partitioning is crucial. By partitioning topics based on usage patterns, teams enable parallel processing and reduce latency. Without thoughtful partitioning, workloads risk hotspots where performance bottlenecks arise. Second, fault tolerance is non-negotiable. Configuring replication factors, ideally 3 or more, ensures no data loss even if brokers fail. Third, performance monitoring is essential. Metrics like consumer lag, broker throughput, and cluster health must be tracked continuously to prevent silent failures that could cripple AI models. Fourth, security cannot be overlooked. Implementing access control lists, encryption, and authentication safeguards sensitive training data and inference results. Common pitfalls include underestimating storage requirements for model features, poor partition strategies, inadequate monitoring, and insufficient security. Each of these can compromise the reliability of AI pipelines. Best practices are not just guidelines, they are survival strategies for ensuring Kafka systems remain robust, efficient, and trustworthy. As we wrap up, this final page distills the essence of Kafka's role in AI. At its core, Kafka provides the real-time foundation that modern AI systems require, shrinking the gap between data generation and insight delivery from hours to milliseconds. Its ability to integrate with feature stores, orchestration frameworks, and model-serving platforms makes it indispensable for end-to-end AI pipelines. And with its enterprise-grade reliability, scalability, and fault tolerance, Kafka has earned its place as a production standard technology. For organizations beginning their journey, the next steps are clear. Evaluate current data latency requirements. Identify high-value use cases where streaming adds competitive advantage, and pilot a Kafka-based feature pipeline. In doing so, they lay the groundwork for AI systems that are not only intelligent, but also adaptive, timely, and deeply responsive to the world around them. Let's begin by setting the stage. In modern machine learning, models are often celebrated as the heroes of the story. We talk about architectures, algorithms, and accuracy scores. But beneath all that lies the true workhorse of AI systems, data features. Features are the variables that models learn from, the carefully engineered representations of reality that allow predictions to make sense. Yet as organizations scale their AI efforts, managing these features becomes a formidable challenge. This introductory page introduces feature stores, specialized systems designed to manage features at scale. By bringing order, consistency, and reusability to feature engineering, feature stores act as the central nervous system of machine learning infrastructure. In this discussion, we'll explore why feature stores matter, what they are, and how open source and enterprise solutions like Feast and Tekton tackle these problems. Along the way, we'll examine real-world use cases, best practices, and the key lessons ML teams must adopt to succeed in production. Machine learning projects often stumble not because of poor model design, but because of inconsistent data pipelines. One of the most pervasive issues is feature duplication. Without a centralized approach, teams reinvent the same features repeatedly. One group codes a user activity score, another codes a similar metric slightly differently. This redundancy wastes engineering time and introduces subtle inconsistencies that degrade model performance. Then there's training serving skew. A feature might be calculated one way during training, but a slightly different way in production, leading to unpredictable outcomes and reduced accuracy. Finally, the lack of standardized feature management slows iteration. Manual processes force data scientists to spend weeks building and validating features rather than focusing on experimentation. These challenges highlight why feature stores are not a luxury, but a necessity. They ensure consistency, reduce duplication, and accelerate the path from idea to deployment. In short, they transform messy, fragmented pipelines into reliable, scalable workflows that empower machine learning at scale. At its core, a feature store is a centralized repository, a single source of truth for all machine learning features. Instead of scattering feature definitions across notebooks, scripts, and databases, a feature store standardizes access and definitions so teams can reuse features with confidence. Beyond storage, it serves as the bridge between offline and online environments. In the offline setting, features are prepared for training, often using batch jobs across historical data. In the online setting, those same features must be served with sub-second latency to support real-time inference. A feature store makes this possible seamlessly. Governance and metadata add yet another layer of value. By tracking lineage, versions, and documentation, feature stores provide transparency across a feature's entire lifecycle. This means teams can reproduce experiments, audit data flows, and ensure compliance with regulations. If models are the engines of AI, then feature stores are the fuel systems, making sure the right input reaches the engine at the right quality and at the right time. Feast represents the community-driven approach to feature stores. As an open-source project, It integrates with existing infrastructure rather than forcing organizations to rebuild their pipelines. Developers interact with Feast through a Python SDK and command line interface, keeping workflows simple and accessible. Feast supports offline stores like BigQuery, Redshift, and Snowflake, as well as online stores such as Redis, DynamoDB, and Google Data Store. It even integrates with streaming systems like Kafka and Kinesis, enabling real-time feature ingestion. This flexibility makes Feast attractive to research teams, startups, and organizations with strong engineering talent that want to maintain control of their infrastructure. Another major advantage is its vibrant community, with thousands of GitHub stars and active contributions from practitioners across industries. Feast evolves rapidly and benefits from shared innovation. In essence, Feast lowers the barrier to entry for feature store adoption, offering a practical, cost-effective solution for teams willing to invest some engineering effort to tailor the system to their needs. On the other end of the spectrum lies Tekton, an enterprise-grade, fully managed feature platform. Unlike open-source solutions, Tekton is designed to provide production-ready reliability out of the box. It offers managed infrastructure, complete with service-level agreements and expert support. Tekton integrates seamlessly with enterprise systems such as Spark, Snowflake, Databricks, and cloud services across AWS, Azure, and Google Cloud. For regulated industries like finance and healthcare, governance features are paramount. Tekton includes role-based access control, audit logs, approval workflows, and lineage tracking to satisfy compliance requirements. Performance is another key differentiator. Optimized for high throughput, low latency serving, Tekton employs advanced caching strategies to deliver features in milliseconds. For organizations with large-scale production ML systems, Tekton provides not only the infrastructure, but also the governance and security required to operate responsibly. If Feast represents flexibility and experimentation, Tekton represents reliability and enterprise scale. The choice often comes down to the maturity of the ML program and the regulatory environment in which it operates. The importance of feature stores becomes most apparent in real-world applications. In fraud detection, models rely on both real-time signals, like device fingerprints or user behavior, and hysterical patterns. A feature store ensures these diverse signals are consistently available for scoring transactions on the fly. In recommendation systems, low latency access to embeddings, historical interactions, and contextual signals allows platforms to deliver personalized content in under 10 milliseconds, keeping users engaged. For large language models, feature stores enrich retrieval-augmented generation pipelines with structured metadata, enabling more context-aware and less error-prone responses. Predictive maintenance provides yet another example. By combining time series sensor data with metadata about equipment, models can forecast failures before they occur, saving enormous costs. In all these cases, the common thread is consistency, speed, and reliability. Feature stores make it possible to combine real-time signals with historical context, giving models the best of both worlds. Adopting a feature store is only the first step. Success depends on following disciplined best practices. First, teams must standardize feature definitions. Clear naming conventions and metadata documentation prevent confusion and enable discovery across teams. Second, versioning and lineage tracking are essential. By maintaining versions of features and documenting data sources through transformations, teams ensure reproducibility and accountability. Third, quality and freshness must be monitored continuously. Alerts for staleness or anomalies prevent degraded model performance from creeping in unnoticed. Fourth, access controls must be implemented with rigor. Role-based permissions, audit logging, and usage tracking prevent unauthorized access while ensuring responsible data sharing. Organizations that succeed at scale are those that approach feature management systematically. By reducing technical debt and enabling reuse, best practices not only maintain quality, but also accelerate innovation. In this sense, feature stores are not just tools, They are cultural enablers of disciplined, high-impact machine learning. As we conclude, let's distill the essential lessons. Feature stores are the foundation of production machine learning systems, ensuring that features remain consistent, reusable, and high quality across environments. Without them, duplication, skew, and inefficiency undermine the value of even the best models. Organizations have a choice of paths. Feast offers open source flexibility, ideal for teams with strong engineering capacity and a desire for community driven innovation. Tekton provides enterprise grade reliability and governance, essential for regulated industries and production scale ML. Regardless of the choice, the principle remains the same. Start small but think big. Begin with core features for a single use case. Establish best practices and gradually expand to an organization-wide implementation. By doing so, companies create the infrastructure that will support machine learning not just for today's experiments, but for tomorrow's mission-critical systems. Feature stores, in short, are not an optional add-on. They are the backbone of ML success. In the rapidly evolving world of artificial intelligence, data is not just an input, it is the fuel that powers the entire machine. But raw data, arriving at scale and in real time, is messy, noisy, and often unusable in its natural state. This first page introduces the concept of real-time data preprocessing as the bedrock of high-performance AI and machine learning pipelines. The goal is simple: transform raw signals into actionable insights quickly enough to keep pace with the speed of modern applications. Whether it's fraud detection in financial transactions, sensor analysis in the Internet of Things, or recommendation systems that react instantly to user clicks, milliseconds matter. This guide presents practical strategies for engineers who build pipelines that don't just handle big data, they handle fast data. As we move through this presentation, we will uncover why preprocessing is vital, the specific tasks it entails, the tools and frameworks available, and the best practices that keep systems reliable at scale. To understand why real-time preprocessing is critical, we must examine the requirements of modern AI. First, data must be fresh, because stale inputs lead to stale predictions. In critical systems like autonomous vehicles or fraud detection, even a delay of seconds can cause catastrophic errors. Second, data must be clean. Streaming data often arrives incomplete, duplicated, or corrupted. If left untreated, this pollutes the downstream models. Third, data must be formatted consistently. Machine learning models expect structured inputs. Without preprocessing, the variability of raw data can cause instability and errors. Finally, data must be actionable. Preprocessing extracts meaning from signals, turning chaotic inputs into features a model can actually use. The importance of this becomes obvious when we look at real-world use cases. Fraud detection requires immediate scoring of transactions. IoT applications need live interpretation of sensor feeds. Recommendation engines must update user preferences instantly. And autonomous systems demand real-time situational awareness. Without robust preprocessing, even the most advanced AI becomes unreliable, inaccurate, or even dangerous. Preprocessing in real time is not a single step, but a sequence of critical tasks. Cleaning comes first. This involves handling missing values, removing duplicates, and filtering anomalies. In streaming systems, deduplication ensures that repeated events don't distort outcomes, while imputing missing values prevents models from breaking on incomplete data. Transformation follows, where raw data is converted into machine learning-ready formats. This includes feature scaling, normalization, and encoding of categorical variables, all of which ensure that models interpret data correctly. For high-dimensional streams, dimensionality reduction may be applied on the fly. Aggregation is the next pillar. Streaming data often needs to be grouped across time windows. Rolling statistics like mean or variance provide richer signals than raw inputs alone. Tumbling, sliding, and session-based windows allow engineers to capture different temporal dynamics. Finally, enrichment combines streaming data with external sources. For instance, Joining sensor readings with device metadata or linking user activity with demographic information creates more powerful features. Together, these tasks form the backbone of real-time feature engineering, turning raw streams into actionable intelligence. Choosing the right technology stack for pre-processing is one of the most important architectural decisions. Apache Kafka, combined with Kafka Streams, is often the first choice for event sourcing and log aggregation. It provides high-throughput message handling and built-in processing capabilities. Apache Flink is designed for low-latency, stateful stream processing, offering exactly once semantics, making it ideal for complex event processing and time series analysis. Spark structured streaming brings the advantage of unifying batch and stream processing under one API, making it excellent for machine learning feature engineering at scale. For cloud-native environments, Apache Beam and Google Dataflow provide a unified programming model across batch and streaming workloads, with auto-scaling built in. Each of these frameworks has strengths. Kafka for durability and throughput, Flink for real-time analytics, Spark for large-scale ML integration, and Beam for cloud-native flexibility. The key is aligning the tool with the specific workload, latency requirements, and organizational expertise of the team. Real-time preprocessing finds application across nearly every domain of AI. In robotics and reinforcement learning, sensor streams must be pre-processed into compact state representations and reward signals in milliseconds to enable agents to interact with their environment. In recommendation engines, embeddings of user interactions and content features are generated on the fly, ensuring that recommendations reflect the most recent behavior. Anomaly detection systems depend on pre-processing log data, normalizing values, and extracting statistical signals to flag suspicious events before they escalate. In conversational AI, pre-processing plays an equally important role. Speech transcripts, chat messages, and contextual metadata must be cleaned, tokenized, and structured in real time before large language models can generate coherent responses. Each use case has unique requirements, but the common theme is the same. Without fast, accurate preprocessing, models cannot respond effectively to real-world complexity. Scaling real-time preprocessing pipelines requires both architectural foresight and engineering discipline. Windowing techniques are critical to balancing computational load with insight. Tumbling windows group events into fixed intervals. Sliding windows provide overlapping analysis for continuous updates, and session windows capture user activity-based behaviors. Parallelization further enhances scalability. Partitioning streams by keys allows related events to be processed together while distributing load across nodes. Consistent hashing ensures that stateful processing remains coherent across partitions. Optimization techniques reduce resource demands without compromising throughput. Efficient serialization formats like Avro, Protobuf, or Parquet minimize overhead, while compression strategies shrink storage and transmission costs. Edge preprocessing adds another dimension. By performing basic cleaning close to the data source, say on an IoT device, systems reduce cloud processing requirements and latency. For example, in an IoT deployment, sensors might handle simple filtering locally, while aggregating insights flow to the cloud for advanced analysis. These scaling strategies enable pipelines to handle millions of events per second while maintaining accuracy and responsiveness. Building resilient, real-time pre-processing pipelines is as much about best practices as it is about technology. Continuous data quality validation is non-negotiable. Automated checks for schema compliance, valid ranges, and statistical consistency must run continuously, with alerts triggered for anomalies or distribution shifts. Lightweight processing design is equally important. Engineers should profile pre-processing steps and optimize the critical path for low latency. Complexity must be minimized so that speed is never sacrificed unnecessarily. Schema evolution planning ensures pipelines can adapt as data sources evolve. Adding or removing fields should not break downstream consumers. Versioning and backward compatibility are key. Finally, comprehensive monitoring is essential. By integrating with tools like Prometheus and Grafana, teams gain real-time visibility into throughput, latency, and resource utilization. Together, these practices create pipelines that are not just fast, but also stable, reliable, and maintainable. Without them, even the most sophisticated frameworks will crumble under the pressures of production. As we conclude, the lessons of real-time preprocessing become clear. First, it is the foundation of reliable AI at scale. Models cannot perform well without clean, fresh, and well-structured inputs. Second, speed matters. For most real-time applications, sub-second latency is the target, and reaching it requires both the right tools and disciplined design. Third, the majority of engineering effort in ML, often as much as 80%, goes into data preparation. Investing in preprocessing is not wasted effort. It is the most impactful way to improve model performance. Fourth, optimized preprocessing can yield performance gains of 4 times or more compared to raw, unprocessed inputs. Finally, the roadmap for adoption is straightforward. Evaluate your latency requirements, select frameworks that align with your workloads, and implement monitoring to ensure ongoing reliability. Looking forward, as AI models become more complex and data streams grow richer, efficient real-time preprocessing will only increase in importance. It is not just an engineering challenge, it is a competitive advantage. Artificial intelligence is only as strong as the data it consumes. This first page introduces us to one of the most underappreciated truths in AI. Without reliable, high-quality data, even the most sophisticated models will fail. The phrase garbage in, garbage out is not just a cliche. It is a fundamental principle. Poor quality inputs don't just create noisy predictions. They can cause systemic drift, unexpected failures, and the erosion of user trust. What's more, hidden biases within data propagate silently through entire machine learning life cycles, embedding inequality or unfairness into automated decisions. On the flip side, systematic monitoring of data quality creates transparency, fairness, and long-term stability. This introduction frames data quality not as an optional extra, but as the very foundation of responsible AI engineering. It reminds us that models may capture headlines, but without dependable inputs, their value quickly deteriorates. As we proceed, we will see how quality can be measured, monitored, and scaled to production environments. Why does data quality matter so profoundly in AI systems? At its core, poor quality data leads to degraded model performance. Imagine a fraud detection model being trained on transaction data riddled with missing values or mislabeled entries. The model may appear accurate in testing, but collapse when deployed in production. Over time, this leads to model drift, where predictions diverge from reality. Failures then occur in critical applications. Credit approvals, medical diagnoses, supply chain forecasts, each with serious consequences. Data quality issues also amplify hidden biases. If an e-commerce recommendation model is trained on incomplete data for certain demographics, it may unintentionally exclude or misrepresent those groups. Finally, the absence of monitoring undermines trust. Engineers, regulators, and users alike need assurance that AI decisions rest on reliable foundations. By embedding quality monitoring, organizations can detect errors early, ensure fairness, and maintain the consistent performance that production-grade AI demands. To effectively monitor quality, organizations must think across 5 dimensions. Completeness asks whether data is missing. A model trained on incomplete records is like a student studying from half a textbook. Its understanding will always be limited. Accuracy measures how well data reflects reality. Incorrect labels or measurement errors distort models, creating faulty predictions. Consistency examines whether data remains uniform across systems and over time. A date field formatted differently in training versus serving environments can break pipelines. Timeliness assesses freshness. In fast-moving environments like stock trading or cybersecurity, stale data produces outdated, irrelevant predictions. Finally, validity checks whether data adheres to domain-specific rules. For example, an age value of -5 is invalid and should be flagged immediately. Together, these 5 dimensions form a holistic framework. They remind us that quality is not just about correctness, it is about relevance, structure, and reliability across the entire life cycle of data. Fortunately, a rich ecosystem of tools exists to support data quality monitoring. Evidently AI is an open source Python library tailored for ML practitioners, offering visualization and monitoring capabilities for both model and data behavior. Great Expectations provides a framework for data validation, allowing teams to create expectations or unit tests for data that automatically profile and verify quality. Y Labs brings observability at scale, with features like drift detection and explainable monitoring, ensuring production systems remain transparent and reliable. For enterprises, platforms like Monte Carlo and Soda extend monitoring with lineage tracking and deep integration into corporate ecosystems. These tools serve a shared mission to provide comprehensive visibility into data health. They automate the detection of issues, reduce reliance on manual inspection, and empower engineers to focus on fixing root causes rather than constantly firefighting. Selecting the right tool depends on scale, budget, and organizational maturity, but the message is clear. Robust monitoring is both possible and necessary. The importance of monitoring data quality becomes clearest when we examine practical use cases. In feature validation, ensuring data is accurate and complete before training prevents models from learning the wrong patterns and degrading over time. In schema monitoring, pipelines must be checked for changes. If a source system suddenly introduces a new column or alters a field format, models depending on that data may fail silently. Anomaly detection plays a different but equally critical role. Monitoring real-time data streams for unusual patterns allows teams to catch issues before they spread, such as unexpected spikes in missing values. Finally, fairness checks ensure that models perform consistently across demographic groups, identifying hidden biases before they become embedded in production. These use cases highlight that monitoring is not abstract. It directly affects the trustworthiness of models in the real world, from fraud scoring to recommendation engines to healthcare diagnostics. Monitoring data quality for small projects is straightforward, but scaling across enterprise systems requires strategy. The first step is to automate validation by embedding quality checks directly into ETL and ELT pipelines. This ensures problems are caught early, not after deployment. Visual monitoring with dashboards provides teams with real-time insight into anomalies, making it easier to detect trends or sudden shifts. Thresholds should be set for key metrics, with clear alerting channels so that issues are surfaced immediately. Finally, integrating quality gates into CI/CD pipelines ensures that poor data never reaches production, just as failing tests prevent faulty code from shipping. These strategies transform quality monitoring from a reactive task into a proactive discipline. They allow organizations to manage data health at the same scale as they manage their infrastructure and code, ensuring AI systems remain robust even as complexity grows. Scaling strategies succeed only when paired with best practices. The first principle is to treat data as first-class infrastructure. Just as code undergoes rigorous testing and review, so too must data. Second, monitoring must extend across both training and inference data. Catching drift requires observing not only the offline datasets used for training, but also the live data feeding models in production. Third, versioning datasets and tracking schema changes is essential for reproducibility and debugging. When something goes wrong, engineers need to trace exactly which version of the data caused the issue. Fourth, collaboration with domain experts cannot be overlooked. They understand what good data looks like within a specific context, whether that's financial transactions, medical records, or IoT telemetry. Together, these practices ensure that data quality monitoring is not just a technical checklist, but a cultural shift, embedding responsibility for data health into every stage of AI development. The final page brings all these lessons together. Data quality monitoring is not a side activity, it is the foundation of trustworthy AI systems. Yet it is too often ignored until problems arise, by which point the costs of failure are high. By focusing on the five dimensions of quality: completeness, accuracy, consistency, timeliness, and validity, organizations create a comprehensive framework for monitoring. By leveraging tools like Evidently AI, Great Expectations, and Y Labs, they can automate oversight and respond quickly to emerging issues. By embedding monitoring into every stage of the ML pipeline, from ETL to model serving, they prevent drift, bias, and catastrophic failures. The next steps are clear. Start with a quality assessment of your most critical AI systems. Establish baseline monitoring and expand coverage gradually. In doing so, teams not only safeguard their models, but also build systems that are fairer, more reliable, and more trustworthy. Ultimately, good data quality is not just about performance, it's about creating AI that people can depend on. The journey of large language models, or LLMs, is one of scale, ambition, and complexity. In research labs, these models begin as experiments trained on subsets of data, designed to test new architectures or benchmark emerging techniques. But when we transition from controlled experiments to planet scale production, where billions of requests are served daily, the infrastructure challenges multiply dramatically. This first page introduces us to that very shift. LLMs are no longer academic curiosities. They are foundational technologies underpinning search engines, chatbots, translation services, and enterprise applications. Scaling them from prototype to production demands more than raw computing power. It requires orchestration of memory, storage, networking, cost, reliability, and governance at levels never before attempted in AI. In this discussion, we will explore why LLM infrastructure is uniquely hard, the core constraints, and what good looks like when organizations succeed in building mature, production-grade systems. Why is the infrastructure for large language models so difficult to manage? First, there is massive model scale. With billions or even trillions of parameters, the memory and compute requirements stretch beyond what even the best GPUs can handle individually. Second, the data pipeline complexity is immense. Training datasets range from terabytes to petabytes, creating storage demands and bandwidth bottlenecks across the entire pipeline. Third, there are extended training windows. Multi-node training can last weeks, and without strong fault tolerance and recovery systems, even a minor failure can derail the process. Finally, inference demands conflict. In production, users expect millisecond response times, while businesses demand high throughput. Balancing these two, often competing requirements is one of the greatest technical puzzles. These challenges highlight that scaling LLMs isn't just about more hardware. It's about engineering new systems that manage unprecedented demands. At the heart of LLM training lies the problem of compute. GPU scarcity creates fierce competition across organizations, with scheduling and allocation becoming as important as raw horsepower. Then there are parallelism trade-offs. Engineers must balance data parallelism, model parallelism, and pipeline parallelism, optimizing across model architecture and hardware topology. Each choice has implications for speed, efficiency, and scalability. Interconnect bottlenecks are another major barrier. Even with technologies like NVLink and InfiniBand, gradient synchronization across thousands of GPUs pushes network links to their limits. Recovery adds further complexity. Checkpointing mechanisms must scale across thousands of compute ranks without creating storms of I/O traffic. Efficient GPU utilization, then, requires orchestration across multiple dimensions, where every decision impacts cost, performance, and feasibility. Memory and storage present challenges just as daunting as compute. Consider that a single 175 billion parameter model requires over 520 gigabytes of memory just to store parameters in half-precision format. An optimizer overhead, typically 3 to 5 times that amount, and memory requirements explode further. Checkpoints for models at this scale can easily exceed 60 terabytes, making storage and recovery a monumental task. Training datasets add another layer, with modern foundation models demanding 2 to 8 petabytes of high quality, filtered data. Managing such volume requires tiered storage strategies, sharding, and in some cases, quantization, all while balancing the trade offs between accuracy, latency, and accessibility. The challenge is not just storing this information, but ensuring it can be accessed quickly enough to keep GPUs fully utilized. Without careful design, storage becomes a choke point that slows the entire system. If compute and memory are the muscles of LLM infrastructure, networking is the circulatory system, and it too faces stress under scale. All reduce operations, used for synchronizing gradients across GPUs, can saturate network links. Straggler nodes, caused by uneven sharding or heterogeneous hardware, drag down overall performance. Even vector databases, which support retrieval augmented generation, can suffer hotspotting during high-volume queries, creating bottlenecks. Mitigating these issues requires creative strategies. Locality-aware data placement reduces cross-rack traffic, intelligent prefetching anticipates access patterns, and hierarchical synchronization reduces the burden on global communication. Without these optimizations, network congestion can erase the benefits of even the most powerful hardware. The financial and environmental realities of LLMs cannot be ignored. Training a GPT-3 scale model can cost $1 to $4 million in compute resources alone, before even accounting for engineering or infrastructure overhead. Idle GPU hours are extraordinarily expensive, so efficiency is paramount. Organizations adopt cost optimization strategies such as using spot or preemptible instances with checkpoint recovery, mixed precision training and inference, kernel fusions, and sparse attention mechanisms. Beyond cost, sustainability must be considered. Energy consumption, cooling efficiency, and carbon-aware scheduling all matter when running data centers at this scale. Teams must justify not only the financial outlay, but also the environmental footprint. Optimizing cost and energy is not an optional exercise. It is a prerequisite for sustainable AI operations. Reliability is the silent pillar of successful LLM infrastructure. Long training runs require elastic recovery mechanisms and automatic requeue capabilities, ensuring that progress continues despite hardware failures or preemptions. Post-deployment, drift detection becomes critical. Changes in data distribution, prompt patterns, or embedding spaces can degrade performance subtly over time. End-to-end tracing provides observability from ingestion through training, serving, and feedback loops, enabling root cause analysis when issues arise. Finally, safety monitoring must be integrated into the system itself. Rate limiting, guardrails, and abuse detection protect both users and infrastructure from harmful outputs or misuse. Without reliability and observability, scaling LLMs is like flying blind at supersonic speeds. No discussion of LLM infrastructure is complete without addressing governance. Data quality at scale requires filtering pipelines that can process petabytes of raw text efficiently, deduplicating content and ensuring high fidelity. Privacy workflows must detect, redact, and delete personally identifiable or protected information. Compliance and lineage tracking are essential for licensing, auditing, and legal protection. At the same time, safety evaluation through red teaming, bias analysis, and jailbreak resistance testing demands its own infrastructure. Governance, then, is not an afterthought. It must be designed into the system from the ground up. In the absence of strong governance, organizations face not only technical risks, but also ethical, legal, and reputational risks that can outweigh any technological advantage. Training is only half the battle. Once deployed, LLMs must serve billions of requests with speed and reliability. Performance balancing involves optimizing token throughput while maintaining low latency, often using intelligent batching and KV cache reuse. Multi-tenant operations demand that different workloads run side by side without interference, with auto-scaling and hot model loading to handle spikes. Caching architectures, layered for prompts, embeddings, and retrievals reduce compute costs while boosting responsiveness. Finally, deployment control ensures reliability through canary testing, gradual rollouts, and automated rollback mechanisms. Production systems must deliver not only intelligence, but also operational stability at internet scale. What does best-in-class LLM infrastructure look like? First, it provides a unified platform where training, fine-tuning, and inference share consistent abstractions and interfaces. Second, it embraces composable optimization, offering modular toolkits for parallelism and memory management that adapt across architectures and scenarios. Third, it runs on a robust CI/CD pipeline where data, models, and prompts are continuously integrated, tested, and deployed with automation. Fourth, it enables cost-aware experimentation, tying telemetry directly to product metrics, so decisions are based on ROI, not just technical feasibility. Organizations that achieve this maturity reap measurable rewards. They can deploy new models 5 to 10 times faster, reduce infrastructure costs by 30 to 50%, and achieve uptime exceeding 99.9% with automated recovery. In short, good infrastructure is not invisible. It is transformative, creating compounding advantages in speed, efficiency, and capability. The final section reminds us that large language model infrastructure is not just machine learning, but bigger. It introduces fundamentally new constraints that cut across every layer of the stack. Compute parallelism, memory constraints, I/O bottlenecks, reliability gaps, and spiraling costs all demand systemic solutions. Governance, too, is central, ensuring data quality, privacy protection, compliance tracking, and safety guardrails. The winning teams will be those who optimize not just the model, but the entire system. By breaking down silos between research, infrastructure, and product teams, they create compounding advantages that accelerate deployment, reduce costs, and unlock capabilities competitors cannot match. Scaling LLMs to production is not easy, but for those who get it right, it is a foundation for the future of AI. As we step deeper into the world of large language models, one truth becomes abundantly clear. Memory and storage are not afterthoughts. They are the lifeblood of scaling. This first page sets the stage by highlighting the unprecedented demands that modern models place on infrastructure. Models containing billions or even trillions of parameters require staggering memory capacity just to exist. During training, the situation grows more complex. It isn't just parameters being stored, but optimizer states and activations as well, each demanding its own slice of precious GPU memory. Inference brings its own challenges with the need for rapid weight loading and efficient context caching. On top of that, checkpointing, essential for resilience and reproducibility, explodes in cost as models scale, easily reaching terabytes per run. This introduction reminds us that without a carefully engineered memory and storage strategy, no amount of model sophistication can survive the transition from theory to practice. Why exactly are memory and storage such critical factors for LLMs? The answer lies in the way these models consume resources. Parameters alone demand enormous memory footprints, but during training, we must also store optimizer states and activations simultaneously. Activations, which are the temporary results produced as inputs pass forward and backward through the model, often exceed the size of the parameters themselves. This means that memory is not only large, but also dynamic, changing with every iteration of training. For inference, the challenge shifts to speed. Model weights must be loaded into GPU memory quickly, and context must be cached efficiently to deliver low latency predictions. Storage adds another layer of complexity. Checkpoints are necessary for recovery and experimentation, but their size grows exponentially with model scale. What once was gigabytes of storage is now terabytes, and soon petabytes. These realities underscore why memory and storage are no longer secondary considerations. They are defining constraints of modern AI. Training a large language model is a memory balancing act. Let's consider the numbers. 1 billion parameters requires about 4 gigabytes of memory in standard FP32 precision. but optimizer states, particularly when using Atom, add a fourfold overhead, bringing the total to 16 gigabytes per billion parameters. This means that a 100 billion parameter model already pushes memory into the terabyte range. Then come activations. During forward and backward passes, activations can consume as much as 40% of total memory, often exceeding the weight storage itself. To cope, engineers use techniques like gradient checkpointing, which trades compute for memory by recomputing activations instead of storing them all. Precision trade-offs also help. Switching to FP16 or BF16 nearly halves the memory footprint while maintaining numerical stability. When we break it down, parameters might consume about a quarter of memory, optimizer states another third, and activations nearly half. This delicate distribution illustrates why memory is the most immediate bottleneck in LLM training. If memory is the short-term challenge, storage is the long-term burden. Training LLMs requires datasets at petabyte scale, demanding distributed file systems that can deliver high throughput without I/O bottlenecks. Checkpointing is another massive consumer. Frequent checkpoints are essential for recovery and for tracking experiments, but each run can generate between 1 and 3 terabytes of data. Over time, this accumulates into tens or hundreds of terabytes, creating storage challenges that dwarf many enterprise systems. To manage this, teams employ tiered architectures, NVMe drives for hot data that needs rapid access, object stores for checkpoints, and cold storage for archives and long-term retention. This hierarchical approach balances speed, cost, and accessibility. Without it, storage would quickly spiral out of control, stalling even the most well-funded projects. Once training is complete, models face a different set of memory pressures in production. The first is weight loading. Serving a model requires loading its massive weights from storage into GPU memory, and any delays here translate directly into user-facing latency. For models deployed at internet scale, even seconds of delay are unacceptable. Then there's the KV cache, or key value cache, used by the attention mechanism. As context length grows, say, beyond 4,000 tokens, the KV cache can actually exceed the size of the parameters themselves. Without optimization, this creates a runaway memory problem. Solutions include batching requests to amortize memory usage and applying quantization techniques, which shrink weights to INT8 or even 4-bit formats, reducing memory footprint by factors of 2 to 8. These optimizations are not luxuries. They are the difference between a system that is usable and one that is prohibitively expensive. The lifecycle of a model introduces diverse storage needs. During training, full precision weights and optimizer states must be stored, often in multiple variants, for experimentation. In fine-tuning, domain-specific adaptations produce additional checkpoints that must be versioned and managed. Once deployed, models shift into optimized serving formats, with versioning ensuring reproducibility and rollback capabilities. Finally, archiving becomes necessary, with cold storage and retention policies managing long-term costs while preserving artifacts for compliance and future use. Model registries, such as MLflow or weights and biases, support this lifecycle by tracking artifacts systematically, ensuring teams can retrieve the right version at the right time. This structured approach turns storage from a liability into an asset, providing transparency, reproducibility, and governance across the model's entire lifespan. The good news is that memory and storage challenges, while immense, are not insurmountable. Distributed training optimizations provide some of the most powerful solutions. Parameter sharding techniques like Zero, fully sharded data parallel, or Megatron LM distribute the model across GPUs, breaking the memory wall. Activation offloading moves tensors temporarily to CPU or NVMe storage when not needed, while gradient accumulation reduces optimizer state memory pressure. On the storage side, compression and deduplication shrink dataset footprints, while differential checkpoints store only parameter changes rather than entire models. Systematic checkpoint pruning removes intermediate saves, retaining only what is necessary for reproducibility. Together, these strategies allow teams to train models that would otherwise be impossible with today's hardware. They represent the cutting edge of infrastructure engineering, pushing the boundaries of what AI systems can achieve. As we conclude, the key lessons of memory and storage management come into sharp focus. First, memory is the real-time bottleneck. During training, parameters, optimizer states, and activations must all fit into available VRAM. During inference, the speed of weight loading and the growth of the KV cache determine system throughput. Second, storage is the long-term burden. Datasets and checkpoints scale into petabytes, and versioning requirements compound the challenge. Third, success requires a clear implementation strategy. Build tiered storage that balances performance and cost. Manage the model lifecycle systematically with registries and retention policies. And employ distributed training techniques to scale beyond single node limitations. The story of LLMs is not just one of clever algorithms. It is one of infrastructure mastery. By solving memory and storage challenges, we unlock the true potential of models at unprecedented scale. When we think of large language models, we often focus on their parameters, their training data, and the impressive outputs they generate. But beneath the surface lies another critical enabler: vector databases. This introduction reminds us that traditional databases built for rows, columns, and exact matches simply cannot handle the way modern AI understands content. Large language models interpret text, images, and other modalities by transforming them into high-dimensional embeddings, mathematical vectors that capture meaning rather than surface form. To store and search these embeddings efficiently, we need specialized infrastructure. Vector databases are that infrastructure. They allow semantic search where queries return results based on meaning rather than keywords. They enable operations on vectors, such as comparing similarity across millions or billions of items. And they provide the foundation for retrieval-augmented generation, or RAG, pipelines that ground LLM outputs in factual knowledge. In short, vector databases are the hidden engine that makes modern AI applications scalable, searchable, and reliable. Why do we need vector databases at all? The answer lies in the shift from syntax to semantics. Traditional databases excel at exact matching, finding a product by SKU or a record by ID, but they falter when asked to find items similar in meaning. Imagine searching for running shoes and missing results labeled sneakers. Vector databases solve this problem by storing embeddings, numeric representations of meaning, and retrieving items based on similarity metrics, like cosine distance or dot product. This enables semantic search at scale. Vector operations also become efficient, allowing systems to compare high-dimensional vectors across billions of records without grinding to a halt. Furthermore, vector databases support hybrid queries, combining similarity with metadata filters, like date ranges or categories. For modern applications, from chatbots to recommendation systems, this capability is transformative. It's the difference between search that finds keywords and search that understands intent. That's why vector databases have become the backbone of intelligent retrieval systems. Vector databases stand out because of their specialized features. The first is approximate nearest neighbor indexing, or ANN. Instead of attempting perfect matches, which would be computationally prohibitive, ANN algorithms trade a fraction of accuracy for dramatic speed improvements, making billion-scale vector search practical. The second feature is massive scale. Distributed architectures let these databases handle billions of embeddings while still delivering sub-second responses, a feat impossible for traditional relational systems. Third, metadata filtering blends semantic search with structured filters, enabling precise hybrid queries like find documents about climate change published in the last 5 years. Fourth, framework integration accelerates adoption. Seamless connectivity with libraries like LangChain, Llama Index, and other LLM tools means developers can plug vector search directly into their AI applications. Together, these features make vector databases not just fast and scalable, but also developer-friendly and versatile. Deis, or Facebook AI Similarity Search, is one of the most widely used open-source libraries for vector search. Written in C++ with Python bindings, Theus is highly optimized for both CPU and GPU operations. Its key strength is flexibility. It supports multiple index types, from flat brute force to advanced structures like IVF, HNSW, and product quantization. This makes it an excellent choice for research and prototyping, where experimentation and customization are paramount. One benchmark illustrates its power. Theus can deliver searches up to 100 times faster than brute force methods. With 16 gigabytes of GPU memory, it can index millions of vectors efficiently. The trade-off, however, is that Theus requires more engineering effort to scale in production. There is no built-in infrastructure management. Deploying at enterprise scale demands custom work. Still, for teams seeking maximum control and flexibility, Theus remains a gold standard in vector similarity search. For organizations that value speed to production over engineering control, Pinecone offers a fully managed cloud service. With Pinecone, teams don't have to provision, maintain, or scale infrastructure. It is handled automatically. Its enterprise-grade features make it especially attractive for production environments. Low-latency APIs, multi-tenant support, and advanced security features allow reliable deployment in mission-critical systems. Pinecone also shines in its support for hybrid search, where vector similarity can be combined with metadata filtering for results that are both relevant and precise. For RAG pipelines, Pinecone reduces friction dramatically, enabling teams to move from prototype to production without worrying about operational scaling. It is particularly well suited for companies that need enterprise reliability but lack the resources or desire to manage infrastructure in-house. The trade-off is reduced flexibility compared to open-source solutions, but the benefit is rapid, reliable deployment. Weaviate takes a different approach by combining vector search with graph-like data structures. This makes it uniquely capable of handling complex queries that go beyond simple similarity. For example, one could search for documents related not just by content, but also by relationships across entities. Weaviate includes built-in machine learning modules, such as pre-integrated transformers and classifiers, which accelerate development. Its flexible APIs, GraphQL, and REST make it accessible to developers across ecosystems. Importantly, Weaviate offers hybrid deployment options. It can be self-hosted for organizations that want control, or run as a managed cloud service for those who prefer convenience. This duality makes it versatile, appealing to startups experimenting with prototypes as well as enterprises scaling production. By blending vector search with graph capabilities, Weaviate opens possibilities for richer, more contextual AI applications that go beyond simple embedding retrieval. Vector databases enable a wide array of applications across industries. In retrieval augmented generation, chatbots use vector search to ground their responses in factual content, reducing hallucinations and improving accuracy. In multimodal search, embeddings from models like Clip allow users to search images using text queries or find images similar to a given one. Recommendation systems benefit by embedding both users and items into a shared vector space, enabling precise matches based on behavior and preference rather than just categorical labels. In anomaly detection, vector representations of time series sequences reveal unusual patterns that may indicate fraud, system failures, or security breaches. These use cases underscore that vector databases are not niche, they are foundational. They transform how AI systems access, interpret, and apply information, making them essential for next-generation applications. Implementing vector databases effectively requires discipline. First, teams must choose the right index. Flat indexes guarantee accuracy but are slow. HNSW indexes balance accuracy and speed but consume more memory. IVF scales efficiently for huge datasets with moderate accuracy. Second, it's critical to version embeddings. Different embedding models produce vectors that are not interchangeable, so tracking versions alongside data prevents silent errors. Third, teams should monitor quality metrics, such as recall at K and query latency, to ensure both relevance and performance are maintained over time. Finally, normalize vectors during indexing when using cosine similarity, ensuring comparisons are consistent and efficient. These best practices turn vector databases from promising experiments into production-grade systems. They ensure that the search results are not only fast, but also trustworthy and reproducible. As we conclude, the essential lessons become clear. Vector databases are the backbone of modern search and RAG pipelines, enabling semantic retrieval at scale. Choosing the right solution depends on the use case, team resources, and scale requirements. FAIS offers flexibility and control for research and custom deployments. Pinecone delivers enterprise reliability with minimal maintenance overhead, ideal for production environments. Weaviate provides unique capabilities for complex graph-like queries with both open source and managed options. The overarching principle is simple. Start with your use case. Define your requirements in terms of speed, accuracy, scale, and governance, and then choose the database that best aligns. By doing so, you'll build systems that not only store embeddings, but transform them into powerful engines of meaning, context, and insight for AI applications. Large language models are remarkable in their ability to generate fluent, coherent text, yet even the most advanced models face inherent limitations. Their knowledge is frozen at the time of training, and their context windows limit how much information they can process at once. This opening page introduces the concept of retrieval augmented generation, or RAG, a powerful solution to these challenges. RAG pipelines extend the capabilities of LLMs by injecting external knowledge directly into the generation process. Instead of relying solely on what the model remembers, RAG allows it to consult external sources in real time. This means models can answer questions about proprietary documents, provide up-to-date information, and reduce the risk of hallucinations by grounding responses in factual context. The introduction frames RAG not just as a feature, but as a foundational technique for making AI systems more accurate, trustworthy, and useful in enterprise and research applications alike. Why do we need RAG pipelines at all? The answer begins with the limited context windows of LLMs. No matter how large a model is, it can only attend to a fixed number of tokens in a single prompt. If we try to stuff too much information in, the model loses track. Second, models suffer from a knowledge cutoff. Because they are trained on static datasets, their world knowledge stops at a particular date, often years before deployment, in fast-changing fields like law, medicine, or finance. This makes them outdated. Third, RAG enables the injection of fresh, domain-specific information right when it's needed. Instead of retraining a model every time new documents are added, RAG lets us update the retrieval layer and immediately improve responses. Finally, RAG helps reduce hallucinations, the tendency of LLMs to produce convincing but incorrect answers. By grounding outputs in retrieved documents, the pipeline ensures greater factual accuracy. In short, RAG addresses the core weaknesses of LLMs, turning static systems into adaptive, knowledge-rich assistants. The workflow of a RAG pipeline unfolds in 4 distinct stages. First comes the user query. A natural language question is transformed into an embedding vector, a dense numeric representation of meaning. Next, the vector database search begins. Using similarity metrics, the system finds document chunks that are semantically aligned with the query. The third stage is context assembly. The system selects the top results and organizes them into a form that fits within the model's context window, ensuring the LLM receives the most relevant material. Finally, the LLM generation step combines this retrieved context with prompt engineering to produce a coherent, accurate answer. This flow may seem simple, but it represents a profound shift in how AI systems operate. Instead of being closed boxes, LLMs become open systems, querying, retrieving, and reasoning over external data in real time. For a RAG pipeline to succeed, each component must work in harmony. The embedding model is the first piece. It transforms text or other modalities into dense vector representations that capture semantic meaning. Examples include OpenAI embeddings, BERT, or CLIP. Next is the vector database, which stores and indexes these embeddings for fast similarity search. Popular choices include Face, Pinecone, and Weaviate. Then comes the retriever, which manages the search process itself, filtering, re-ranking, and ensuring only the most relevant results are passed along. Finally, the LLM is the generative engine, synthesizing retrieved context into fluent responses. Together, these components form a pipeline where each step enhances the next. Embeddings enable semantic search, vector databases scale it, retrievers refine it, and LLMs deliver answers enriched with context. The elegance of RAG lies in this modularity. Each component can be improved independently, leading to continuous performance gains. The versatility of RAG pipelines is evident in their use cases. Enterprise knowledge assistants help HR, IT, and legal departments by providing employees with accurate answers grounded in company documentation and policies. Proprietary document chatbots allow organizations to converse with their internal reports, research, or compliance documents as easily as with a human expert. In scientific research, RAG systems perform live literature searches, synthesizing findings across thousands of academic papers, a task impossible for a single researcher. Moving further, multimodal RAG expands beyond text, retrieving and processing images, audio, and video alongside documents. This allows applications like medical systems that cross-reference X-rays with patient histories, or customer service agents that analyze call transcripts with support manuals. Each use case highlights a simple truth. When LLMs are connected to domain-specific knowledge, they evolve from general-purpose engines into specialized expert systems. Building RAG pipelines at scale is not trivial. Scale is the first challenge. Efficiently retrieving from billions of documents requires advanced indexing and sharding strategies to distribute the workload. Latency is another. The end-to-end pipeline includes embedding computation, vector search, and LLM generation. Even a few hundred milliseconds of delay can feel sluggish in a live application. Relevance poses a subtler problem. Retrieval must deliver not just superficially similar chunks, but truly relevant ones, as irrelevant material can dilute or confuse the LLM's output. Finally, there's freshness. Indexes must be updated regularly, sometimes continuously, to incorporate new information. Outdated retrieval pipelines risk negating the very benefits of RAG. These challenges show that retrieval is not a bolt-on feature. It requires careful engineering across the entire stack to achieve reliability, speed, and accuracy at scale. Success with RAG pipelines depends on disciplined best practices. First is the chunking strategy. Documents should be split into semantically meaningful chunks of about 500 to 1,000 tokens, with overlaps to preserve context. Poor chunking leads to fragmented or incoherent retrieval. Second, hybrid retrieval is recommended. Combining semantic search with keyword-based methods like BM25 improves coverage, while re-rankers enhance precision. Third, teams must implement metrics monitoring, tracking relevance scores, recall rates, and hallucination frequencies, combined with human feedback, enables continuous improvement. Fourth, performance optimization is key. caching frequent queries, and implementing tiered retrieval strategies. Coarse searches, followed by fine-grained re-ranking, reduce latency without sacrificing quality. These best practices transform RAG pipelines from experimental demos into production-grade systems, ensuring both reliability and scalability. The final page distills the lessons of RAG into clear principles. RAG bridges the gap between the raw power of LLMs and the need for fresh, domain-specific knowledge. It offers a complete pipeline: embeddings, vector databases, retrievers, and LLMs that together solve accuracy, relevance, and hallucination challenges. It is the foundation of enterprise-grade generative AI, enabling systems that are not only powerful, but also grounded and trustworthy. The path forward is straightforward. Evaluate your use case, select the right components, and start with a proof of concept. From there, iterate and scale. In doing so, you equip your LLMs not just with memorized knowledge, but with the ability to query, reason, and generate in partnership with external data. RAG, in short, transforms LLMs from impressive but isolated systems into dynamic engines of knowledge that evolve as quickly as the world itself. Large language models are powerful, but they come with a price. Inference is both expensive and slow. This opening page reminds us that scaling LLMs into production environments creates real bottlenecks: latency that frustrates users, and costs that balloon as traffic grows. Many queries, however, are repetitive or partially overlapping. Caching offers a way to exploit this redundancy. By storing and reusing results, we can eliminate redundant computation, deliver answers in milliseconds instead of seconds, and reduce operational expenses by as much as 30 to 70% in high-volume systems. Beyond efficiency, caching improves user experience by providing instant responses, creating the illusion of a model that is not only intelligent but also lightning fast. This introduction frames caching not as an optional optimization, but as a strategic necessity, the key to transforming LLMs from experimental tools into production-ready services that scale gracefully. Caching in the context of LLMs comes in several flavors, each addressing a different bottleneck. The prompt response cache stores entire query answer pairs. As a user asks the same question again, the system can retrieve the full response instantly, bypassing the model entirely. The embedding cache avoids recomputing vector representations for repeated queries or documents, saving resources in retrieval-augmented generation pipelines. The KV cache preserves the key value states of attention layers during autoregressive decoding, drastically speeding up token generation in long contexts. Finally, the retrieval cache stores vector database search results, ensuring frequent queries don't repeatedly trigger costly similarity searches. Each type addresses a specific layer of the stack, and together they form a multi-layered defense against inefficiency. Understanding when and where to apply them determines whether your caching strategy merely helps or truly transforms performance and cost dynamics. Prompt response caching shines in scenarios where queries repeat frequently, such as customer support bots. Imagine thousands of users asking about return policies or warranty coverage. Instead of generating a new response each time, the system can instantly return a cached answer. Implementation is straightforward. Hash the query and model parameters to create a cached key, store the model's response as the value, and retrieve when an identical query appears. Fuzzy matching can catch near duplicates, such as "How do I reset my password?" versus "Can you help me reset my password?" Time to live, or TTL, policies ensure freshness, expiring entries as policies or data change. The benefits are dramatic: full responses with zero inference latency, massive cost savings, and a user experience that feels instantaneous. This strategy turns static FAQs into dynamic, scalable, AI-powered support systems that feel both fast and personalized. Perhaps the most transformative caching technique for LLMs is the KV cache. Transformers generate text one token at a time, with each step depending on all prior tokens. Without caching, this requires quadratic computation as context length grows. The KV cache solves this by storing intermediate key value attention states, so the model does not recompute them for every token. The result is profound. Inference complexity drops from ON squared to ON, cutting per token generation time by 30 to 50%. This makes long context inference feasible, enabling real-time chat systems with 8,000 tokens or more. But challenges remain. Memory footprint grows linearly with context length, requiring careful GPU memory management. Engineers must balance sequence batching with cache size, and pruning strategies are essential for ultra-long contexts. Still, KV caching is indispensable. Without it, large context applications like chat assistants or document summarizers would grind to a halt. Caching is not just about algorithms, it is about infrastructure choices. Cache stores can include Redis for distributed high-throughput caching, Memcached for simple low-latency needs, or even in GPU memory for the fastest access at the cost of limited capacity. Hybrid approaches combine these, creating tiers where hot items reside in GPU memory while less frequent entries sit in Redis. Eviction policies are equally important. Least recently used, LRU, ensures stale entries are cleared first, while least frequently used, LFU, prioritizes popular items. TTL-based policies ensure time-sensitive data is refreshed, while size-based watermarks keep overall memory use under control. Finally, consistency management is critical. Model versioning must be baked into cache keys to prevent mixing responses from different models. Cache flushing and warming strategies ensure smooth rollouts, while monitoring prevents stale responses. Together, these considerations remind us that caching is an ecosystem decision requiring careful tuning to match workloads and infrastructure constraints. Real-world AI systems demonstrate the power of caching. Customer service chatbots benefit enormously, caching answers to high-frequency questions and handling thousands of queries per second with minimal inference cost. In search and retrieval augmented generation pipelines, embedding and retrieval caches cut down redundant computations, ensuring fresh responses without overwhelming vector databases. Multi-turn dialogue systems leverage KV caching to maintain fluid conversation flow, reducing token latency by up to 70% and enabling real-time interactions. In content moderation, caches store classification results for recurring patterns, dramatically accelerating throughput in high-volume environments like social media. These use cases highlight caching's versatility. It doesn't just make systems cheaper, it makes them more usable, responsive, and scalable across industries, from customer engagement to safety-critical applications. Implementing caching effectively requires following best practices. First, cache selectively. Not all queries benefit equally, so focus on high-value, repetitive workloads. Second, monitor hit-miss ratios. A cache hit rate above 40% is often necessary to justify the investment. Third, employ cache warming by pre-populating entries for common queries, ensuring fast responses from the start. Fourth, version cache keys carefully. Embedding the model ID or version prevents inconsistencies when models are updated. On the optimization side, semantic deduplication groups similar queries, adaptive TTLs extend expiry for stable content, and partial result caching stores intermediate steps. Probabilistic caching further prioritizes high-value entries. Ultimately, caching is about balance between memory usage and cost savings, between freshness and reuse. Best practices ensure this balance tilts toward reliability and performance. The final page distills the lessons of caching into clear outcomes. Done well, caching can reduce latency by up to 70% and cut inference costs by as much as 60% in large-scale applications. 4 complementary strategies: prompt, response, embedding, KV, and retrieval caches work together to optimize the stack. The most immediate gains often come from KV caching, which accelerates token generation. From there, teams can layer in other caches based on traffic patterns and budget constraints. The overarching message is simple. Caching is the key to scaling LLMs efficiently. Without it, latency and costs spiral out of control. With it, organizations unlock performance, affordability, and user experiences that feel instantaneous. Caching is not a luxury, it is the foundation of production-grade LLM deployment. Deploying large language models in production is one of the most challenging engineering problems of our time. The models themselves are astonishingly capable, but bringing them from the lab into real-world environments is about more than just clever algorithms. It's about infrastructure. This introduction frames the conversation around scale, reliability, and latency. Enterprises need systems that not only respond in fractions of a second, but also remain resilient under unpredictable traffic and cost pressures. Serving is about ensuring that models run continuously, adapt to spikes in demand, and deliver responses at internet scale. It's also about striking a balance between user experience, operational efficiency, and budgetary constraints. This page sets the stage for a guide aimed at ML engineers and site reliability engineers, those responsible for turning cutting-edge models into reliable, enterprise-grade services. The second page explains why serving LLMs is uniquely difficult. The first obstacle is size constraints. These models are enormous, sometimes requiring hundreds of gigabytes of memory just to load, leading to long initialization times and immense GPU pressure. Next are performance demands. Users interacting with a conversational assistant expect near instant responses, no matter how complex the query. Meeting that bar consistently is tough. Then there's traffic unpredictability. Production workloads often come in spikes, hundreds of thousands of queries one moment, near idle traffic the next. Infrastructure must scale elastically to handle both extremes. Finally, resource efficiency is critical. GPUs are costly resources, and without multi-tenancy and cost-aware scheduling, expenses spiral out of control. Together, these challenges remind us that deploying LLMs is not merely a technical exercise, it's a careful act of engineering trade-offs, where performance, cost, and reliability are always in tension. A robust serving system consists of several tightly integrated components. At the edge is the front-end API, which receives user queries, validates them, and enforces authentication and rate limiting to protect against abuse. The inference engine runs the model on accelerated hardware, such as GPUs or TPUs, managing execution graphs and ensuring maximum throughput. A caching layer sits in between, storing prompt results, key value caches, and embeddings to eliminate redundant computation. The orchestration layer coordinates the system, handling auto-scaling, load balancing, and intelligent routing to ensure requests go to the right resources. Finally, observability tools provide logs, metrics, and distributed traces, enabling engineers to detect performance issues before they affect users. This architecture is not static, it's dynamic, adapting constantly to meet demand. Each layer contributes to a system that transforms LLMs from heavyweight research artifacts into agile production-grade services. How do organizations actually deploy LLMs? There are 3 main approaches. Single-node serving is the simplest. running models on a single GPU or machine. It works well for smaller models, say under 13 billion parameters, and is easy to set up with frameworks like Hugging Face or Fast API. But it quickly hits limits. Distributed serving is the next step, where large models are sharded across multiple GPUs or nodes. Tensor parallelism allows billions of parameters to be split across devices, enabling 70 billion plus parameter models to run, albeit with added operational complexity. Finally, there are serverless APIs, which offer on-demand access with no infrastructure management. They're cost-efficient and convenient, but come with higher latency and cold start penalties. Supporting all of these deployment models are inference runtimes like TensorRT, vLLM, and deep speed inference, which optimize performance for different hardware and workload types. Choosing the right deployment model depends on model size, performance targets, and operational resources. Every millisecond of latency matters. Performance optimization techniques focus on squeezing maximum efficiency from the serving stack. KV cache reuse stores intermediate attention states, reducing token generation latency by as much as 50% for long contexts. Request batching combines similar queries into a single execution, boosting throughput while balancing trade-offs in latency. Quantization and pruning shrink models by reducing precision. FP32 weights can be compressed to INT8 or INT4, dramatically reducing memory footprints with minimal accuracy loss. Finally, memory pinning ensures that frequently used models remain resident in GPU memory, avoiding the costly delays of reloading. Together, these strategies create serving pipelines that feel instantaneous to users, even under heavy loads. They remind us that performance isn't just about hardware, it's about careful engineering choices that multiply efficiency across the system. Reliability and scalability are pillars of production systems. Dynamic scaling, often powered by Kubernetes HPA or Reserve, ensures the GPU pods expand and contract based on demand. Scaling based on queue depth, not just CPU or memory, helps match resources to real workloads. For global applications, multi-region deployments bring inference closer to users, improving latency and complying with data sovereignty rules. Safe deployment practices such as canary rollouts, A/B testing, and shadow traffic ensure new models are validated before full release. Finally, resilient strategies like fallback models, circuit breakers, and graceful degradation protect against cascading failures. These patterns transform LLM serving into something enterprises can trust, a service that remains available and responsive even under duress. Reliability, after all, is not a bonus feature. It is the minimum expectation in production AI. A production system is only as good as its observability. Engineers need visibility into how models perform in real time. Performance metrics, latency percentiles, throughput, and error rates reveal whether systems meet service level objectives. Resource utilization metrics show GPU load, memory fragmentation, and kernel efficiency. Distributed tracing with tools like OpenTelemetry allows end-to-end request tracking, making bottlenecks visible across the pipeline. Finally, proactive alerting ensures teams are notified immediately of drift, anomalies, or degradations. Monitoring is not reactive. It is preventive, enabling teams to catch issues before they affect users. In LLM serving, observability is the safeguard that turns black box systems into transparent, manageable services. It empowers teams to move fast without losing control. Serving LLMs at scale requires strong security and governance. At the API edge, rate limiting and abuse detection prevent denial of service attacks and malicious prompt injection. Token bucket algorithms enforce fair usage, while pattern detection blocks exploit attempts. Data security demands encryption of prompts and responses, both in transit and at rest, alongside automatic PII detection and redaction. Compliance requirements, HIPAA, GDPR, SOC 2 require audit logs and immutable records of model interactions. Governance also means access control, with role-based permissions, ensuring different teams have the right level of visibility and control. Feature flagging supports gradual rollouts, minimizing risk. Together, these measures create a serving environment that is not just fast and reliable, but also trustworthy and compliant. Governance and security are not extras, they are non-negotiables for enterprises deploying AI at scale. The final section distills everything into actionable lessons. Serving LLMs in production is about balancing latency, cost, and reliability. Core optimizations, caching, batching, quantization, and routing directly improve user experience and efficiency. Deployment choices, from Kubernetes clusters to Ray-serve to serverless APIs, determine scaling models and operational overhead. Observability, governance, and security ensure systems are trustworthy, resilient, and compliant. The next step for teams is to assess their current architecture, identify bottlenecks, and adopt patterns from best-in-class systems. The path to enterprise-grade AI is not mysterious. It is systematic. Serving is where brilliant models meet real-world expectations, and it is here that the difference between a demo and a product is made. The rise of large language models has been accompanied by a new set of challenges: how to train models with billions or even trillions of parameters. This introduction highlights the critical role of DeepSpeed and its Zero Redundancy Optimizer, or ZERO, in making this possible. Training at scale is limited not just by algorithms, but by memory ceilings, communication bottlenecks, and exploding storage requirements. DeepSpeed is designed to break through these barriers. It reduces memory consumption, accelerates training throughput, and lowers overall costs. The message here is clear. Without frameworks like DeepSpeed and Zero, today's largest models would remain research fantasies rather than production realities. This page sets the stage for a deeper look into the mechanisms, techniques, and best practices that allow engineers to push beyond the traditional limits of GPU memory and distributed training. This slide outlines the core problems DeepSpeed was created to solve. First are memory constraints. Standard GPU memory cannot hold billion-parameter models, let alone the trillion-parameter giants of today. Second are communication bottlenecks. Training requires synchronizing gradients and parameters across GPUs, but network overhead often throttles throughput. Third is the storage explosion caused by massive checkpoint sizes, which become unmanageable at scale. DeepSpeed addresses each challenge directly. It shards memory across devices to reduce redundancy, overlaps communication with computation to reduce latency, and streamlines checkpointing for efficiency. The result is not just a marginal improvement, but a leap forward, enabling models to be trained on hardware that would otherwise be insufficient. This section underscores the necessity of DeepSpeed. Without it, scaling to modern model sizes would be prohibitively expensive and operationally impossible. At the heart of DeepSpeed lies Zero, the Zero Redundancy Optimizer. Traditional data parallelism replicates an entire model on each GPU, wasting vast amounts of memory. Zero revolutionizes this by partitioning key elements of training. Optimizer states, such as Adams moment estimates and learning rates, are sharded across GPUs. Gradients, the updates generated during backpropagation, are also partitioned rather than fully replicated. Finally, even model parameters themselves are distributed across devices. By eliminating this n-way redundancy, Zero achieves dramatic memory savings while preserving computational efficiency. This innovation allows models that were once impossible to train on a single node to now fit across distributed hardware without sacrificing performance. The elegance of Zero lies in its simplicity. Share the load intelligently, and suddenly the impossible becomes achievable. Zero's approach is incremental, implemented in progressive stages. Stage 0 is the baseline, standard distributed data parallel, where the full model is replicated on each GPU. Stage 1 introduces optimizer state sharding. distributing those tensors across devices and saving nearly 4 times the memory. Stage 2 goes further, sharding gradients during backpropagation, eliminating their redundancy. Stage 3 completes the vision, sharding parameters themselves so that no GPU holds the full model. This enables the training of truly massive networks. The result is the ability to fit significantly larger batches and models on the same hardware, unlocking new performance levels without new GPUs. Each stage represents a step deeper into efficiency, allowing teams to adapt based on their model size, hardware, and tolerance for complexity. Even with sharding, GPU memory eventually reaches its limits. This is where offloading strategies come into play. Zero offload moves optimizer states and gradients to CPU memory, leveraging abundant system RAM while reducing GPU pressure. This comes with a PCIe transfer overhead, but still delivers major gains. Zero Infinity pushes further, offloading not just optimizer states, but also parameters and activations to CPU and NVMe storage. With this approach, model size becomes virtually unlimited. The trade-off, of course, is higher latency. The art of offloading lies in careful tuning, overlapping computation and communication, so that latency penalties are hidden while memory savings are maximized. These variants remind us that memory is not a hard wall, but a flexible resource, provided we use the right combination of GPU, CPU, and storage tiers. Deep speed is not only about memory, it's about speed. Several performance techniques are built into the framework. Communication overlap ensures that reduce scatter and all gather operations run in parallel with computation, hiding network latency. Kernel fusion combines operations like bias plus JALU activation or layer normalization into single kernels, cutting memory transfers and launch overhead. Gradient accumulation allows gradients from multiple microbatches to be accumulated before an optimizer step, emulating larger batch sizes without exceeding memory limits. Activation checkpointing reduces peak memory by discarding activations and recomputing them during backpropagation. Each technique involves a trade-off: more computation for less memory, or more complexity for greater throughput. But together they enable training at scales and speeds previously unattainable. This slide compares deep speed with PyTorch's fully sharded data parallel, or FSDP. Deep speed, particularly 03, offers mature offloading to CPU and NVMe, advanced memory compression, and flexible schedulers. It is a Microsoft-supported project with its own custom communication backend. FSDP, by contrast, is natively integrated into PyTorch, making it easier to adopt within existing PyTorch workflows. Its strength lies in ecosystem compatibility and simpler setup. Driven by a large open-source community, the choice between them depends on context. Deep speed excels when offloading and advanced memory optimization are essential. FSDP may be preferred when simplicity and seamless PyTorch integration matter more. Both frameworks represent the cutting edge of distributed training, and many teams experiment with both before settling on the one that best fits their environment. This slide presents a conceptual example of a deep speed configuration. It includes micro batch sizes, gradient accumulation steps, zero stage selection, offloading parameters, and activation checkpointing. For instance, 03 with CPU offload is enabled. Small per GPU batch sizes are balanced with accumulation, and mixed precision training with BF16 reduces memory footprint. Activation checkpointing is turned on, and communication overlap is activated. Each of these parameters must be tuned to the hardware and model size. The configuration illustrates how deep speed gives engineers granular control, allowing them to squeeze every ounce of performance from their GPUs while extending capacity far beyond native limits. In practice, these configurations evolve iteratively, with careful benchmarking and monitoring guiding adjustments. Training at scale is never smooth, and this page highlights the practical lessons. Progressive implementation is key. Start with 0 stage 1, then 2, then 3, validating stability at each step before enabling offloading. Metrics like throughput and memory headroom must be measured continuously. Communication parameters like bucket sizes often need careful tuning to match network topology. Offloading should use pinned CPU memory and high-performance NVMe drives with proper queue depth. Debugging common failure modes is also critical. Out-of-memory errors may require smaller microbatches, higher zero stages, or activation checkpointing. Slow offloading may point to PCIe bottlenecks or poor disk performance. Communication issues often trace back to NCCL misconfiguration or bandwidth limits. Training instability under mixed precision may require BF16 or FP16 or gradient clipping. These lessons emphasize that deep speed is not plug and play. It is a powerful but intricate tool that demands engineering discipline. The final content slide provides guidance on when to apply specific strategies. For models under 10 billion parameters running on A100 or H100 GPUs, 02 or 03 with BF16 precision is often enough, with minimal offloading required. For models exceeding 20 billion parameters or in constrained GPU environments, 03 with aggressive offloading becomes necessary, sometimes extending into NVMe territory. Long context models, which have substantial activation memory needs, demand aggressive checkpointing and KV cache optimizations. In multi-tenant clusters, elasticity, job recovery, and checkpointing strategies are paramount. The underlying principle is adaptability. The right combination of zero stage, offloading, and optimization depends on the model, hardware, and workload. There's no one-size-fits-all answer. Success lies in tailoring these tools to your specific context. The final section distills the key lessons. Memory optimization lies at the heart of Zero. By sharding optimizer states, gradients, and parameters, larger models can fit on the same hardware. Capacity is extended through offloading, using CPU RAM and NVMe storage with latency trade-offs. Throughput gains are realized through communication overlap, kernel fusion, and gradient accumulation. Above all, success requires iterative tuning. No two workloads are identical, and optimal configurations are highly specific to hardware, network, and model architecture. Deep speed and zero are not magic bullets, but they are powerful frameworks that redefine what is possible. By balancing memory, computation, and communication, they make it feasible to train models that once seemed impossible. For teams pushing the boundaries of AI, mastering these tools is no longer optional, it is essential. Large language models have redefined what artificial intelligence can achieve, but their success has pushed infrastructure to its limits. Training models with billions and now trillions of parameters requires new paradigms in distributed computing. This first page introduces Megatron LM, a framework created to overcome these barriers. Traditional distributed methods, such as simple data parallelism or even zero-based optimization, cannot, on their own, handle the scale demanded by frontier models. Megatron LM pioneered hybrid parallelism, blending tensor parallelism with pipeline parallelism to unlock extreme scalability. It is the engine behind groundbreaking models like GPT-3, MTNLG, and Bloom, enabling researchers and enterprises alike to train networks at unprecedented size. This introduction sets the stage for a deep dive into the techniques, infrastructure, and best practices that make trillion-parameter training feasible. Why was Megatron LM necessary in the first place? The limitations of older approaches became evident as models grew. Standard distributed data parallel DDP, even when combined with zero, cannot efficiently scale to trillion-parameter ranges. Large language models require not just billions, but trillions of parameters, and no single GPU or even a small cluster can handle that. The answer lies in hybrid parallelism, moving beyond GPU per node thinking to strategies that divide both computations and model structure. Megatron LM introduced tensor and pipeline parallelism to address these gaps, unlocking new performance horizons. In effect, Megatron LM was not just a scaling strategy. It was a necessity. the bridge between existing GPU limits and the ambitions of next-generation AI research. Megatron LM builds on three pillars of parallelism. First is data parallelism, the simplest method where the entire model is duplicated across GPUs and each processes a shard of the training data. While conceptually simple, it is limited by the model's ability to fit within a single device. Second is tensor parallelism, which splits individual weight matrices across multiple GPUs. For example, a massive attention matrix can be divided so each GPU computes part of the operation, enabling training of models that exceed single GPU memory. Third is pipeline parallelism, which distributes sequential layers across different devices. By breaking the model into stages, each GPU handles part of the forward and backward pass. The real power comes when these three approaches are combined into 3D parallelism, allowing massive scale through a layered orchestration of data, tensor, and pipeline strategies. Tensor parallelism is central to Megatron LM's design. It allows massive matrix multiplications, the backbone of transformers, to be split across GPUs. For instance, the attention mechanisms Q, K, and V projections can be distributed so no single GPU must handle the full weight matrix. This requires high-speed interconnects like NVLink or InfiniBand, as GPUs must communicate partial results rapidly. The benefit is clear: models with extremely wide hidden dimensions, which would otherwise break GPU limits, can now be trained. Tensor parallelism shines whenever individual weight matrices exceed a device's capacity. By carefully mapping these computations across devices, Megatron LM makes once impossible models not only trainable, but efficient at scale. Pipeline parallelism addresses depth rather than width. Here, the layers of the transformer are divided into sequential pipeline stages, each assigned to a GPU or node. To maximize utilization, the system uses micro-batching, where smaller batches flow through the pipeline in staggered fashion, keeping all GPUs busy. The key challenge is managing pipeline bubbles, the idle time that occurs at the beginning and end of each cycle when some stages wait for others to finish. Effective scheduling reduces these bubbles, ensuring maximum throughput. Pipeline parallelism is indispensable for training extremely deep models where hundreds of layers must be distributed across hardware while maintaining computational efficiency. It complements tensor parallelism by addressing a different dimension of scale. The brilliance of Megatron LM lies in its 3D parallelism, a synthesis of data, tensor, and pipeline parallelism. This allows training at the scale of 100 billion to 1 trillion parameters. Configurations are topology-aware, adapting to the architecture of GPU clusters and their interconnects. Elastic setups let teams adjust parallelism to their available hardware, maximizing efficiency. Importantly, this approach has been proven in industry, powering some of the largest and most influential LLMs to date. 3D parallelism ensures that no single GPU is overwhelmed, workloads are distributed intelligently, and both memory and compute bottlenecks are alleviated. Without this integration, trillion-parameter training would remain theoretical. With it, Megatron LM sets the benchmark for what is possible in large-scale AI. Megatron LM also provides a suite of optimizations to maximize hardware utilization. Optimized CUDA kernels are written specifically for transformer operations, squeezing every drop of performance from NVIDIA GPUs. Fused operations reduce overhead by combining functions like bias plus GELU activation into a single kernel, lowering memory traffic. Activation checkpointing trades computation for memory, discarding intermediate activations during forward passes and recomputing them during backpropagation. This reduces memory load dramatically, making billion-parameter models feasible. Finally, Megatron LM integrates with DeepSpeed for zero-based optimization, CPU and NVMe offloading, and further memory compression. Together, these features make Megatron LM not just a scaling framework, but a finely tuned performance machine. designed to stretch hardware to its limits while enabling unprecedented model size. Scaling to trillion parameter models demands serious infrastructure. On the hardware side, multi-node GPU clusters with InfiniBand are essential, along with high-memory GPUs like A100s or H100s. Storage must handle terabyte-scale checkpoints reliably. On the software side, mixed precision training with FP16 or BF16 is standard to manage memory and speed. NCCL provides efficient communication, while CUDA 11 Plus and CUDNN ensure optimized performance. Orchestration layers vary by environment. Slurm dominates in HPC, Kubernetes enables cloud deployments, and Ray provides flexible workflows for research. The takeaway is simple. Megatron LM is powerful, but it is not lightweight. It requires a well-provisioned stack where each layer, from GPU memory to orchestration scheduler, is tuned for scale. Despite its strengths, Megatron LM introduces new challenges. Communication bottlenecks grow with tensor parallelism, demanding careful topology mapping to minimize latency. Pipeline bubbles reduce efficiency with small batches, requiring balancing across stages. Debugging complexity increases exponentially at scale. Troubleshooting across 1,000 GPUs requires specialized tools. Parameter tuning becomes an art form, with micro batch sizes, scheduling, and memory usage needing precise adjustment. These practical issues remind us that trillion parameter training is not turnkey. It requires expertise, monitoring, and constant iteration. Success comes not from flipping a switch, but from managing complexity at every level of the stack. To overcome these challenges, best practices have emerged. Match parallelism to hardware. Align tensor parallelism with NVLink domains and pipeline parallelism across nodes. Balance pipeline stages so each has roughly equal compute cost, minimizing bubbles. Optimize memory usage with activation checkpointing, carefully choosing where to recompute. Most importantly, focus on the right metrics. Instead of raw flops, measure throughput in tokens per second per GPU. This reflects real training efficiency. Small configuration tweaks often yield 10 to 30% improvements, which at trillion scale equates to millions of dollars saved. In practice, these best practices transform Megatron LM from a powerful framework into a practical tool for real-world training. The final page distills the lessons of Megatron LM. It enables true trillion-scale training, not by incremental improvements, but through transformative parallelism strategies. By combining data, tensor, and pipeline parallelism into 3D parallelism, it achieves scalability across massive GPU clusters. Its performance optimizations, CUDA kernels, fused operations, checkpointing, maximize efficiency. Yet it also demands significant investment in hardware and expertise. The message is clear. Megatron LM is not just bigger machine learning. It is a leap in distributed training design, one that redefines the boundaries of what is computationally possible. For organizations willing to make that investment, Megatron LM unlocks the next frontier of AI, where trillion parameter models are not just dreams, but reality. At the heart of modern, large language models lies the transformer architecture. And at the heart of transformers lies attention. But attention comes at a cost. Standard attention mechanisms scale quadratically with sequence length, both in compute and in memory. As inputs grow longer, resource demands explode, placing enormous strain on GPUs. Activations alone often dominate memory usage during training, leaving engineers scrambling for ways to fit longer contexts into finite hardware. Production deployment introduces another dimension: user expectations of speed, responsiveness, and affordability. This opening page sets the stage for flash attention, a breakthrough in kernel-level optimization that rethinks how attention is computed. Unlike approximation methods, flash attention is mathematically exact, yet vastly more efficient. It fuses operations, leverages GPU memory hierarchy, and processes attention in smaller blocks. Together, these innovations make longer sequence lengths, larger models, and faster inference possible. This introduction reminds us, if attention is the engine of LLMs, then optimizing it is the key to scaling them sustainably. This slide asks a simple question: why do we need to optimize attention at all? The answer lies in its quadratic complexity. for every additional token in a sequence. Both compute and memory grow disproportionately. A jump from 2,000 tokens to 8,000 tokens doesn't quadruple the workload, it multiplies it 16-fold. This scaling challenge makes naive attention untenable for long sequences. Moreover, attention activations dominate GPU memory during training, often leaving insufficient headroom for larger batches or longer contexts. Without optimization, models choke on their own architecture. In production, the story is similar. Deploying LLMs without specialized kernels leads to ballooning latency and costs, undermining their value. Optimizing attention is therefore not an optional refinement, it is a survival strategy. It is what allows researchers to train 32K context models without prohibitive infrastructure and enables engineers to serve billions of users without bankrupting their organizations. Flash attention is a re-engineering of the attention mechanism at the CUDA kernel level. Traditional attention implementations materialize massive O(n) squared attention matrices, consuming extraordinary amounts of memory and bandwidth. Flash attention sidesteps this by never fully materializing those matrices. Instead, it performs fused operations, combining multiple steps into one efficient kernel. It leverages memory hierarchy awareness, carefully managing how data moves between GPU registers, shared memory, and global memory. Through chunk-based computation, it processes attention in small, manageable blocks, dramatically improving GPU efficiency. Importantly, flash attention is mathematically exact. Unlike approximation techniques such as sparse or low-rank attention, it delivers the same results as standard attention while consuming far fewer resources. This makes it an ideal drop-in replacement, already integrated into PyTorch, Hugging Face, Megatron-LN, and other major frameworks. With flash attention, we get the best of both worlds, uncompromised accuracy and unprecedented efficiency. The results of flash attention speak for themselves. Benchmarks show 2 to 4 times faster speed compared to standard implementations. Memory usage shrinks by 50 to 70%, allowing models to fit larger batches, longer sequences, or more parameters into the same hardware. Perhaps most impressively, flash attention enables training with context windows of 8,000 to 32,000 tokens, a leap forward in how LLMs understand and reason over extended information. These improvements have driven rapid adoption. Flash attention is now standard in PyTorch Core, Hugging Face transformers, NVIDIA's Megatron-LM, Google's JAX-Flax, and Meta's FairSeek. It has moved from innovation to infrastructure, becoming the de facto standard for efficient transformer training. In practical terms, this means organizations can train models faster, deploy them more cheaply, and serve users with longer, richer contexts. Flash attention doesn't just optimize performance, it expands what is possible in AI. Beyond flash attention, memory remains a bottleneck for large models, and engineers have developed complementary techniques to address it. Activation checkpointing discards intermediate results during forward passes and recomputes them during backpropagation. This can slow training by 20 to 30%, but it halves memory usage. Gradient accumulation simulates larger batch sizes by accumulating gradients across multiple smaller batches, essential when GPU memory is limited. Mixed precision training using FP16 or BF16 cuts memory needs nearly in half while maintaining numerical stability. Finally, parameter sharding distributes model states across GPUs, leveraging frameworks like Zero, FSDP, or Megatron. Together, these techniques represent a toolbox for scaling. Each comes with trade-offs: more compute for less memory, more complexity for greater throughput. But in combination, they make it possible to train models that otherwise would not fit on current hardware. Memory optimization is not one trick, it is a layered strategy. Training is only half the battle. Inference introduces its own memory challenges. The KV cache is indispensable for autoregressive generation, storing key-value tensors from previous tokens to avoid redundant computation. But it grows linearly with sequence length, quickly overwhelming memory at scale. Enter paged attention, pioneered by frameworks like VLLM. This technique manages attention cache with non-contiguous memory allocation, enabling efficient context switching between requests. Quantization further reduces memory demands, shrinking waits and activations to INT8, 4-bit, or even 2-bit representations using methods like GPTQ or AWQ. This delivers up to 4 times memory reduction with minimal quality loss. Finally, GPU memory pinning keeps frequently used models resident in VRAM, eliminating costly CPU-GPU transfers and reducing latency. These optimizations transform inference from a bottleneck into a strength, enabling real-time chatbots, summarizers, and enterprise applications that are both fast and affordable. The impact of these optimizations is visible across the AI landscape. Advanced training now supports GPT-4 class models with 32K token windows, greatly enhancing reasoning and context awareness. Responsive chatbots deliver answers 2 to 3 times faster, meeting user expectations for real-time interaction. Smaller infrastructure footprints mean organizations can deploy on fewer GPUs, slashing capital expenditures by 30 to 50%. Production cost reductions make LLM-powered APIs more accessible, democratizing AI for startups and enterprises alike. In short, these optimizations are not just technical curiosities. They reshape the economics and usability of AI. They allow innovation to scale beyond elite labs into everyday products, ensuring that efficiency gains translate directly into broader adoption and more powerful applications. This slide offers actionable best practices for practitioners. First, enable flash attention by default. It is now a free performance win in modern transformer stacks. Second, adopt a layered optimization approach. Combine flash attention with activation checkpointing and mix precision for maximum memory savings. Third, profile before scaling. Benchmark your sequence length against memory usage to understand real-world performance trade-offs. Fourth, monitor throughput. The true metric of efficiency is tokens per second, not theoretical flops, because memory bandwidth often proves the limiting factor. Following these best practices transforms theoretical improvements into practical production gains. They ensure that optimizations are not just implemented, but fully realized in terms of speed, scalability, and cost savings. The final section crystallizes the message. Attention is the core bottleneck of large language models, and flash attention provides a breakthrough solution. Faster, leaner, yet mathematically exact. When combined with complementary techniques like caching, quantization, checkpointing, and memory management, it forms a holistic strategy for scaling transformers. These optimizations are not optional. They are essential for competitive, long-context training and serving. The takeaway is simple. The future of AI will not be defined only by larger models, but by smarter infrastructure. Teams that master flash attention and memory optimizations will not just train bigger models, they will train them faster, serve them cheaper, and deliver them more reliably. Efficiency is no longer a luxury, it is the foundation of modern AI. The scale of today's large language models has simply outgrown the limits of single servers. This introduction makes clear that modern LLMs with parameter counts in the hundreds of billions or even trillions cannot be trained on any one machine. The GPU memory ceiling is too low, the compute requirements too vast, and the training timelines impossibly long. The solution is multi-node distributed training. Architectures that coordinate clusters of hundreds or thousands of GPUs running in parallel for weeks at a time. This page reminds us that models like GPT-3, Bloom, and Llama, all exceeding 100 billion parameters, were only possible because of distributed training. It emphasizes that this is not just an optimization, but a foundational necessity. Multi-node strategies cut time to train drastically, and they set the stage for frontier-scale AI. Without them, the dream of trillion-parameter models would remain forever out of reach. This slide asks the crucial question: why do we need to go multi-node at all? The answer lies in scale. Parameter counts have ballooned far beyond what any single GPU can store. Even the most advanced A100 or H100 GPUs cannot contain these models in memory. Training requires not just one GPU, but coordinated arrays of them. Multi-node systems unlock this by combining the compute of hundreds or thousands of GPUs. each processing shards of data or slices of the model in parallel. This reduces time to train from years to weeks. Importantly, multi-node training is not just about speed, it is about feasibility. Without parallel architectures, the model sizes we now take for granted could not exist. This section makes it clear. Multi-node training is the backbone of scaling, and it is the foundation upon which modern AI breakthroughs are built. Distributed training revolves around three fundamental approaches to parallelism. Data parallelism is the simplest. Duplicate the entire model across GPUs and split the training data into batches, synchronizing gradients after each step. It is easy to implement, but constrained by the need to fit the entire model into each GPU's memory. Model parallelism tackles this by splitting the model itself. With tensor parallelism, large weight matrices are partitioned across GPUs. With pipeline parallelism, sequential layers are assigned to different devices. Each spreads the load, enabling models that no single GPU could hold. Finally, 3D parallelism combines data, tensor, and pipeline methods. Enhanced with zero or FSDP sharding, it scales into the trillion parameter regime. This page emphasizes that each strategy brings its own communication patterns and trade-offs, and mastery lies in orchestrating them together for maximum efficiency. At the core of distributed training lies communication. GPUs cannot work in isolation. They must synchronize parameters and gradients constantly. The NCCL library is the backbone, providing optimized collective operations like all reduce and scatter gather across devices. The hardware interconnects matter immensely. InfiniBand, delivering 200 to 400 gigabits per second, and NVLink, capable of 900 gigabytes per second, provide the high bandwidth and low latency necessary for efficient synchronization. For large clusters, hierarchical communication organizes synchronization at multiple levels, reducing cross-rack bottlenecks. Finally, fault tolerance is critical. At the scale of thousands of GPUs, hardware failures are inevitable, and recovery strategies must be baked into the system. This page underscores that distributed training is not just about compute, it is equally about network design. Without the right communication backbone, the whole system collapses under its own weight. Managing hundreds or thousands of GPUs requires orchestration. In traditional HPC environments, Slurm remains the gold standard, designed for fixed allocation jobs with predictable resources. In cloud deployments, Kubernetes combined with Ray offers elasticity, allowing clusters to grow or shrink dynamically with workloads. Critical features include automated checkpointing, so training can resume from the last saved state after failures, gang scheduling, ensuring all GPUs start together, and robust monitoring and reallocation systems to keep jobs balanced. Failure detection and recovery mechanisms are not optional. They are lifelines in multi-week training runs. This section highlights orchestration as the control plane, the layer that transforms a collection of hardware into a cohesive training cluster. Without it, large-scale training would be chaos. This page reminds us that multi-node training is powerful but fraught with challenges. Stragglers, slower nodes, can bottleneck entire clusters. Asynchronous training waits for the slowest GPU. Even a single GPU failure can halt 1,000 GPU job. Network bottlenecks emerge when gradient synchronization produces traffic spikes. Intra-rack bandwidth often far exceeds inter-rack capacity, creating imbalances. Storage demands are equally daunting. Checkpoints often reach terabytes per save, and storing model weights, optimizer states, and data strains even advanced I/O systems. Finally, debugging complexity grows exponentially. Isolating errors across thousands of GPUs or reproducing rare race conditions becomes a major engineering effort. This page makes one thing clear: scaling brings power, but it also multiplies fragility. Success requires engineering solutions at every layer, from networking to storage to debugging. Fortunately, engineers have developed strategies to overcome these obstacles. Mixed precision training with FP16 or BF16 cuts memory and communication volume in half. Gradient compression, through quantization or sparsification reduces bandwidth pressure. Communication overhead is addressed by overlapping gradient synchronization with backpropagation and mapping pipeline stages to match physical network topology. Elastic training allows clusters to adapt dynamically as nodes join or leave, improving resilience. Together, these techniques optimize both computation and communication, turning fragile clusters into efficient systems. This section emphasizes that scaling is not brute force, it is careful optimization. By combining these strategies, multi-node training becomes not just feasible, but performant and cost-effective. Theory becomes reality in this section, which highlights major LLM training projects. GPT-3 was trained with 175 billion parameters on 1024 V100 GPUs using custom implementations of 3D parallelism. Bloom, at 176 billion parameters, relied on 384 A100 GPUs and the Megatron Deep Speed framework, demonstrating the power of open science collaboration. Llama, designed by Meta, showed how careful architecture and optimization could reduce infrastructure needs, training highly efficient models on fewer GPUs. These examples underline a common thread. Success comes from a blend of advanced parallelism, robust fault tolerance, and aggressive memory optimization. They prove that distributed training is not theoretical. It is the practical engine behind today's most influential AI models. The best practices section distills lessons from the field. Focus on the right performance metrics, tokens per second per GPU, rather than theoretical flops. Provide a truer measure of efficiency. Always validate scaling on a single node, then expand incrementally to multi-node and cluster-wide setups, establishing baselines at each step. Monitoring and debugging are continuous requirements. Track NCCL bandwidth, identify stragglers through logs, and profile communication during steady state. Finally, invest in automation. Automatic recovery, checkpoint validation, and custom debugging tools save immense time and resources during multi-week runs. The essence of best practices is discipline. Scaling is not achieved through hardware alone, but through careful measurement, iteration, and systematization. The final page crystallizes the message of the entire document. Multi-node training is the only path forward for trillion-parameter models. Single-node systems cannot meet the compute or memory demands. The foundation of this approach is 3D parallelism, combined with optimized communication, distributing work intelligently across massive GPU clusters. Yet, infrastructure reliability, fault tolerance, orchestration, and monitoring is just as important as architecture design. And finally, efficient infrastructure directly affects cost. The difference between a well-optimized and poorly optimized run can amount to millions of dollars. Multi-node distributed training is not simply a technical choice. It is the deciding factor in whether next-generation models are feasible at all. This page leaves us with the clear conclusion: the future of AI will be built not only on bigger models, but on smarter, more resilient infrastructure. Large language models are extraordinary in their general capabilities, but to be truly useful in real-world applications, they must be adapted. This introduction frames the conversation. Pre-trained models are like general-purpose engines, capable of many things, but not yet optimized for specific tasks. Fine-tuning adapts them, aligning their outputs with domain knowledge, industry jargon, or user intent. Yet full fine-tuning comes at a steep cost: billions of parameters, massive GPU requirements, and terabytes of storage for each variant. This is where parameter-efficient tuning, PEFT, enters the story. By updating only a fraction of parameters, PEFT achieves specialization at a fraction of the cost, making customization feasible for startups, enterprises, and edge deployments alike. This page sets the stage. The question is not whether to adapt LLMs, but how, and whether we can do so without exhausting resources. This page emphasizes why tuning is essential in the first place. General-purpose foundations are powerful but shallow. A base model trained on broad web data knows about law, medicine, and finance in general terms, but lacks the precision that professionals demand. Domain specialization fills this gap. Fine-tuning makes a model a legal assistant, a medical advisor, or a financial analyst. Yet here lies the constraint. Full fine-tuning requires enormous resources. Updating all parameters demands vast GPU clusters, long training times, and terabytes of storage for each model copy. Few organizations can afford this. Enter PEFT, which delivers adaptation with minimal resources. By focusing updates on the most influential parts of the model, PEFT achieves strong results without breaking budgets. This section underscores that tuning is not optional. It is the path to making LLMs practical, trustworthy, and domain-specific. Here we dive into the traditional approach, full fine-tuning. The advantages are clear. By updating every parameter, full fine-tuning offers maximum flexibility and highest performance. It allows absolute control over model behavior, ensuring it adapts precisely to new tasks. The methodology is well established and has delivered proven results for years. Yet the limitations are equally stark. Training costs skyrocket, with hundreds of gigabytes required per model copy. Compute needs are immense, requiring top-tier GPUs or TPUs running for weeks. Data requirements are heavy, demanding carefully curated domain datasets. And deployment becomes cumbersome, as each specialized model consumes vast storage and maintenance overhead. This section reminds us that while full fine-tuning provides gold standard adaptation, it is increasingly impractical for organizations working with today's largest LLMs. PEFT offers a radical alternative. Instead of updating all parameters, it focuses on selective updates, tuning just 0.1 to 3% of the total. These changes are stored as lightweight deltas layered on top of the frozen base model. This makes it possible to adapt one base model into hundreds of domain-specific variants with minimal storage. Even better, PEFT supports multitask efficiency. A single base model can serve multiple applications by swapping in different adapters. The methods vary. LoRa introduces low-rank adaptation matrices into attention layers. Adapters add small bottleneck layers to transformer blocks. Prefix or prompt tuning learns continuous embeddings prepended to inputs, steering the model's outputs. Bitfit tunes only bias terms, the bare minimum of adaptation. Together, these methods prove that small, surgical changes can unlock massive efficiency gains, democratizing model adaptation. This page dives into the technical details. LoRa works by injecting trainable, low-rank matrices into attention layers, approximating full updates without the overhead. It has become the most popular PEFT method due to its balance of efficiency and accuracy. Adapters add bottleneck layers that reroute information through smaller, trainable modules, achieving performance gains while touching only a fraction of parameters. Prefix and prompt tuning learn task-specific embeddings prepended to the input, effectively steering a frozen model toward the right domain. Bitfit goes even further, updating only bias terms, a surprisingly effective method for lightweight personalization. Each technique represents a trade-off. LoRa and adapters tend to offer stronger accuracy, while prefix tuning and Bitfit maximize efficiency. This section highlights how PEFT is not a single technique, but a spectrum offering options for every resource and performance requirement. Here, the savings come into focus. A full fine-tuned copy of a model like Llama 2 70B consumes hundreds of gigabytes. By contrast, LoRa adapters or prompt tuning require just a fraction, sometimes 1,000th of that storage. Training costs fall by 10 to 100 times, while storage demands shrink by 10 to 1,000 times. Training cycles drop from weeks to hours, accelerating iteration. Deployment becomes modular. A single base model can support hundreds of domain-specific adapters, each small enough to store, share, and swap effortlessly. The advantages are not incremental, but transformational. PEFT changes the economics of LLM adaptation, allowing organizations of all sizes to maintain specialized models without drowning in costs. The applications of PEFT are vast. Domain adaptation enables specialized models for law, medicine, finance, or science, where vocabulary and reasoning differ from general language. Multilingual fine-tuning tailors models for specific languages or dialects without retraining the entire system for each one. On-device personalization allows assistants, co-pilots, or chatbots to adapt on edge devices, where compute and memory are limited. Rapid prototyping empowers startups and research labs to experiment quickly, testing ideas without massive infrastructure investments. Each use case shows how PEFT unlocks customization in contexts where full fine-tuning would be impractical. It democratizes model adaptation, opening doors for innovation across industries, languages, and devices. Success with PFT requires disciplined practices. Start with PFT by default. LoRa or adapters should be the first choice unless evidence suggests deeper changes are needed. Track trade-offs carefully, measuring the performance gap between PFT and full fine-tuning, and accepting small degradations for large resource savings. Hybrid approaches add flexibility. PFT can be combined with quantization for edge deployment or with selective layer freezing for stronger performance. The decision framework is clear. Use PFT when compute and storage are limited. Multiple domains must be supported, or rapid iteration is required. Consider full fine-tuning only for critical applications with ample data and resources. This section emphasizes pragmatism, choosing the right tool for the job, rather than blindly pursuing maximal performance. The final slide distills the message. Effective adaptation strategies balance performance and efficiency. Full fine-tuning offers maximum control, but comes with prohibitive resource costs. PEFT provides modular, scalable, and cost-effective adaptation with only minimal trade-offs in accuracy. Techniques like LoRa and adapters have become industry standards for their balance of efficiency and performance, while prompt tuning and BitFit offer extreme efficiency for lightweight scenarios. The strategy is not either or, but both. Smart teams combine full fine-tuning and PEFT depending on the task. The conclusion is simple, yet powerful. LLMs become truly valuable when adapted, and PEFT makes that adaptation accessible to all. For practitioners, the next step is hands-on exploration. Libraries like Hugging Face's PEFT and Microsoft's LoRa provide the tools to begin experimenting. The future belongs to those who can adapt models efficiently, scaling intelligence without scaling costs. Generative AI has become one of the most resource-intensive fields in technology. This introduction highlights the central tension. While models continue to grow larger and more capable, the economic realities of training them grow heavier. Scaling to billions and trillions of parameters requires fleets of GPUs running at near full utilization for weeks, if not months. Storage, bandwidth, energy, and cooling add additional burdens. Costs don't just scale linearly, they explode exponentially. This first page sets the tone for the entire discussion. Success in generative AI is no longer just a question of algorithms and architectures. It is equally a question of economics. Technical teams and product leaders alike must grapple with trade-offs between scale and feasibility, between ambition and sustainability. This presentation frames the challenge not as a purely technical one, but as a holistic balancing act that determines the future of AI itself. Why do costs rise so dramatically in generative AI training? The answer lies in three converging factors. Scale issues come first. Every leap in parameter count requires exponentially more compute, memory, and time. A jump from 10 billion to 100 billion parameters does not simply multiply costs by 10. It raises them by an order of magnitude or more. Second are hardware demands. Training frontier models requires thousands of GPUs or TPUs operating continuously at nearly 100% utilization, sometimes for months at a time. Each of those GPUs costs several dollars per hour, compounding into millions. Third are hidden expenses. Storage systems must handle terabyte-scale checkpoints, bandwidth must support petabyte-scale data movement, and energy plus cooling add massive overhead. This section makes it clear. Training costs balloon not just because models are large, but because the entire ecosystem supporting them must also scale. On this page, the costs are broken down into 5 key drivers: Compute is the most obvious, with GPU and TPU hours dominating budgets. A100s or H100s cost between $2 and $4 per GPU hour, and large runs can involve thousands of them for weeks on end. Data is the second driver. Collecting, cleaning, and storing petabytes of training data requires vast infrastructure, sometimes rivaling the cost of compute. Networking comes next. High bandwidth interconnects like InfiniBand or NVLink are essential for synchronization, and their costs scale dramatically with cluster size. Storage is another heavy burden. Checkpoints for large models can run into multiple terabytes each, and distributed file systems must be maintained. Finally, energy, both power and cooling, can consume megawatts of capacity, with power usage effectiveness ratios determining operational efficiency. Together, these 5 factors typically account for 85 to 90% of total training costs. But the true picture is incomplete without hidden and indirect costs. Experimentation overhead is a major culprit. Failed runs due to unstable hyperparameters or bugs can consume 30 to 50% of total compute. Idle capacity adds another layer, as GPUs often sit reserved but underutilized due to scheduling gaps or pipeline stalls. Engineering time is a hidden cost as well. Designing infrastructure, debugging, and maintaining orchestration requires highly specialized teams. Then there are cloud egress fees. Moving petabytes of data between services or regions can cost thousands per transfer. When these indirect factors are added up, they can increase the bottom line by 40 to 60%. This section emphasizes a sobering reality. Costs are not limited to raw compute or storage. Inefficiencies, experimentation, and operational complexities can add as much as half again to the training bill. Thankfully, there are levers to reduce costs without sacrificing model quality. Mixed precision training using FP16 or BF16 halves compute and memory requirements as long as loss scaling is carefully managed. Zero and FSDP sharding eliminate memory redundancy by distributing optimizer states, gradients, and parameters across devices, enabling larger batch sizes on the same hardware. Flash attention and fused kernels reduce flops and bandwidth consumption by re-engineering attention mechanisms. And gradient accumulation with scheduling ensures efficient GPU utilization through micro-batching and dynamic load balancing. These optimizations, when implemented correctly, can cut training costs by 25 to 40%. This page underscores that optimization is not a single trick, but a suite of techniques that, together, can reshape the economics of training. Beyond technical optimizations, organizations must embrace strategic approaches. Spot and preemptible GPUs offer discounts of 60 to 90% compared to on-demand pricing, but require robust checkpointing to handle interruptions. Elastic training adapts cluster size dynamically, scaling up or down based on availability or workload. Checkpoint optimization reduces storage overhead by pruning and saving only differential updates instead of full checkpoints. Finally, model distillation creates smaller student models that inherit knowledge from larger teacher models, dramatically reducing retraining costs. When these strategies are implemented together, organizations typically achieve 40 to 60% reductions compared to standard approaches. This section illustrates how cost-aware planning transforms the economics of AI training, ensuring resources are used intelligently rather than indiscriminately. This page highlights the business layer of cost decisions. First is size versus efficiency. Bigger is not always better. Diminishing returns often kick in at extreme scales, making smaller, optimized models more practical. ROI calculations must look beyond training to consider inference costs, since long-term serving expenses often eclipse initial training bills. Build versus adapt is another trade-off. Should organizations fine-tune open-source models or train from scratch? The answer depends on task specificity and resources. Finally, total cost of ownership must be considered. Training may cost millions, but deployment and maintenance over a model's lifecycle often add 3 to 5 times more. This section reminds us that cost management is not just about saving money on training, It is about making strategic choices that maximize value and sustainability across the full model lifecycle. The theory comes alive in real-world case studies. GPT-3 cost millions to train on 1024 V100 GPUs for weeks, while GPT-4 class systems cost tens of millions with newer hardware. Bloom, with 176 billion parameters, was trained on 384 A100 GPUs for 3.5 months, relying on 0.3 sharding for efficiency. This open science effort demonstrated how distributed strategies could bring massive multilingual models to life. Meanwhile, domain-specific fine-tuned models, smaller systems in the 7 to 13 billion parameter range, often outperform giant LLMs on niche tasks, and at 1/500th the cost. These examples reinforce the broader lesson. Scale is powerful, but specialization and optimization often provide better returns. The future of AI is not just about bigger models, but about smarter economic design. The final page distills the lessons of cost management in generative AI. First, the complete cost equation includes not just compute, but also storage, energy, and people. Second, while optimization techniques can reduce costs significantly, they cannot eliminate the scaling realities of trillion parameter models. Third, strategic choices matter. Techniques like PEFT, smaller models, and distillation offer superior economics in many cases. And finally, cost efficiency itself is a competitive advantage. Organizations that master the economics of AI development will iterate faster, deploy more sustainably, and outpace competitors. The overarching message is clear. The future of AI will be shaped not only by breakthroughs in algorithms, but by mastery of costs. The teams that balance scale, performance, and economics will define the next generation of innovation. Artificial intelligence is transforming industries, and nowhere is this more evident than in computer vision. But building production-grade vision pipelines is not as simple as plugging in a model. This introduction frames the conversation. Image and video data introduce unique infrastructure challenges that go far beyond what most machine learning workflows encounter. Unlike static datasets, vision data flows continuously at high volume from countless sources like cameras, sensors, and user devices. It arrives in diverse formats, must be stored efficiently, annotated at scale, and delivered back to inference engines with millisecond latency. For engineers and managers, the difficulty is not just training good models. It is orchestrating an end-to-end pipeline that keeps up with both scale and speed. This opening reminds us that infrastructure, not just algorithms, determines whether computer vision succeeds in production. Vision data creates infrastructure stress points that make it uniquely difficult to manage. Scale issues come first. Video streams at 30 frames per second across thousands of cameras create massive data volumes that overwhelm traditional storage architectures. Next is format complexity. Footage may arrive in H.264, H.265, AV1, or even RAW formats, each with different resolutions and color spaces, complicating preprocessing. Labeling challenges add another layer. Annotating bounding boxes, segmentations, or classifications is both expensive and error-prone, with noisy or incomplete labels common. Finally, edge constraints exacerbate the problem. Latency and bandwidth between devices and the cloud are limited, making it impossible to push all raw data upstream. These challenges illustrate why vision pipelines must be designed differently from text or tabular systems. They demand scale. Standardization, efficient labeling, and edge intelligence all at once. The journey begins with ingestion and storage. High-throughput intake is essential for handling concurrent RTSP or SRT camera feeds. Tiered storage is the next piece. Hot SSD storage for active datasets, cold HDD or tape for archival data. This balance ensures performance while keeping costs under control. Metadata indexing adds structure, chunking footage by time, camera ID, or scene, so specific frames or clips can be retrieved quickly. Finally, granular access allows teams to pull individual frames for training or longer clips for inference. The key design decision is striking the right balance between speed and cost. Hot storage for the data you need now, cold storage for the data you may need later. Without this architecture, pipelines collapse under the dual weight of volume and velocity. Video formats pose critical trade-offs. Higher compression saves storage, but increases CPU or GPU decode costs. A single dataset can differ by a factor of 10 in size, depending on whether it is stored raw or compressed. Hardware acceleration mitigates this burden. NVIDIA's NVDEC or Intel's VA API decode engines can offload work from CPUs, yielding 4 to 10 times faster performance than software decoding. Format standardization further simplifies workflows. H.264, H.265, and AV1 are preferred for storage and streaming. Storing codec metadata and tracking keyframe indices allows for random access and more efficient processing. In short, decoding is not just a pre-processing step, it is an infrastructure challenge. Teams that fail to optimize it often starve their GPUs, turning cutting-edge hardware into underutilized assets. Computer vision datasets live or die by their labels. Annotation costs often consume more than 70% of dataset budgets. Active learning loops help maximize value, prioritizing uncertain or difficult samples for human review. Bootstrap labeling, where weak or automated labels are refined with human-in-the-loop QA, provides scale at lower cost. Deduplication removes near-identical frames that waste storage and bias models toward common scenes. Bias mitigation is equally critical, ensuring diversity across geographies, lighting conditions, and demographics. Without this, models risk overfitting to narrow conditions and failing in the wild. This section makes clear that labeling is not a side task. It is the single largest expense and the most influential factor in dataset quality. Once data is labeled, it must be managed systematically. Version control ensures reproducibility using cryptographic hashes, manifests, and fixed train-val test splits. Augmentation tracking records every transformation applied, resizing, cropping, color jittering, or mix-up, so experiments are fully traceable. Embedding pre-computation using models like CLIP enables semantic search, duplicate detection, and outlier identification at scale. Compliance metadata tracks consent, privacy requirements, and retention rules, ensuring legal obligations are met. A practical tip is separating metadata from raw data, enabling fast querying without scanning massive image stores. This section highlights a truth familiar to production engineers. Datasets are software artifacts. They need the same rigor of versioning, auditing, and compliance as code. Model training in vision often stalls not because of weak architectures, but because of inefficient data pipelines. I/O bottlenecks are common. GPUs sit idle while CPUs decode video or apply augmentations. The solution is to move pre-processing onto GPUs whenever possible. Data loader engineering is another priority. Asynchronous data loaders with prefetching and caching using formats like web dataset reduce stalls. Precision and accumulation techniques. Mixed precision training and gradient accumulation maximize throughput without exceeding memory. Distributed training introduces its own issues. Unbalanced sharding can create stragglers if clips vary in length or complexity. Careful balancing prevents this. The lesson here is simple. GPUs are expensive. Never let them starve. Optimized data loading and pre-processing are as important as model design. Inference is where vision meets real-time demands. Interactive applications require end-to-end latency under 100 milliseconds, from decode through inference. This requires careful batching strategies. Micro-batching maximizes GPU throughput while keeping response times within SLAs. Tracking optimizations reduce per-frame compute. Algorithms like sort or deep sort track objects across frames, avoiding redundant detections. Edge processing reduces bandwidth and latency by downsampling frames or applying region of interest crops before upload. Together, these strategies allow pipelines to meet the unforgiving requirements of live applications, from autonomous vehicles to video analytics dashboards. The takeaway is that serving vision models is not just about accuracy. It is about speed, efficiency, and intelligent trade-offs. The most efficient systems are tiered. At the edge, raw video streams are captured, lightweight filtering models are applied, event triggers are generated, and important clips are buffered locally. The transport layer moves events reliably via Kafka or MQTT with at least once delivery and synchronized clocks for multi-camera setups. In the cloud, heavy models run at scale, correlating across streams, storing results, and enabling historical analysis. This architecture maximizes efficiency by processing data where it makes the most sense, at the edge for filtering, in the cloud for aggregation and analysis. It reduces bandwidth while maintaining intelligence. This section demonstrates a principle that underpins modern AI systems. Distribute computation intelligently across edge and cloud to balance cost, latency, and capability. Video data introduces acute privacy risks. Security breaches expose biometric information, faces, or license plates, creating regulatory consequences under GDPR, CCPA, and other laws. Security requires encryption at rest and in transit, TLS for streams, and key management systems for storage. Privacy preservation adds layers like face blurring or license plate masking before cloud upload. Alongside consent tracking, access control ensures only authorized users can view sensitive footage, enforced through role-based permissions and tamper-proof audit logs. Regional compliance requires strict data residency and automated purging policies. This page underscores a sobering truth. Vision data is among the most sensitive forms of personal data. Mishandling it can destroy trust, incur fines, and create ethical harm. Security and compliance are therefore not optional. They are core to responsible infrastructure. The final page distills the journey into core principles. Vision workloads stress I/O, storage, and labeling more than typical ML tasks. Optimizing pipelines, particularly decode and augmentation, is critical to preventing GPU starvation. Edge intelligence dramatically reduces costs and bandwidth, filtering data before it reaches the cloud. Robust dataset versioning and metadata management ensure reproducibility and compliance. And finally, security and privacy are paramount, as video data carries unique ethical and legal risks. The next step for teams is to review their pipeline architecture against these best practices, identify bottlenecks, and prioritize improvements in ingestion and preprocessing. The ultimate message is clear. Building production-grade computer vision is not just about powerful models. It is about resilient, optimized, and trustworthy infrastructure. Computer vision has become one of the most transformative areas of artificial intelligence. But success depends on far more than clever neural architectures. This introduction frames the central theme. Robust pipelines are the foundation of production-grade computer vision systems. Raw image data arrives in countless formats, at massive scale, and with uneven quality. Building reliable pipelines means turning that chaos into consistent, structured inputs that can feed models from training all the way to deployment. The essence of these pipelines is repeatability, automated flows that deliver the same high-quality preprocessing, augmentation, training, and logging every time. They also need end-to-end management, seamlessly connecting data ingestion to production validation. Finally, scalability is critical. A good pipeline is not just a research experiment. It must transition smoothly into production environments without breaking under load. This page sets the stage by emphasizing that infrastructure, not just algorithms, determines whether computer vision can succeed in the real world. Data preparation is the first stage, and it cannot be overstated how crucial it is. Ingestion happens from many sources: cloud repositories, edge devices like cameras, or archival datasets. Each source introduces different formats, file structures, and metadata. Normalization ensures consistency, resizing images, aligning color spaces, and standardizing channels. Without this step, models see inconsistent signals that degrade performance. Validation is another necessity. Corrupted files, mislabeled data, or missing frames must be caught early or they propagate errors downstream. Increasingly, privacy controls are also embedded directly into pipelines. Face blurring, license plate masking, or watermarking ensure regulatory compliance. Together, these steps transform raw, messy data into clean, consistent, and compliant inputs. This stage is not glamorous, but it is decisive. Poor preparation guarantees poor results, no matter how sophisticated the model. The next stage is augmentation, which multiplies dataset diversity without additional collection costs. Geometric transforms like flipping, rotating, cropping, scaling, and perspective shifts teach models to recognize objects across orientations and viewpoints. Photometric transforms, brightness, contrast, saturation, or hue jitter prepare models for variable lighting conditions. Noise and degradation methods, such as synthetic blur, Gaussian noise, or cutout, harden models against real-world imperfections like motion blur or occlusion. Policy-driven approaches like auto-augment and rand-augment automate augmentation, searching for combinations that yield maximum robustness. These strategies not only expand datasets, but also improve generalization. A well-designed augmentation stage helps models succeed in the wild, where no two images are ever identical. Labels are the backbone of supervised learning, and managing them consistently is one of the most overlooked challenges. Consistency is critical. Uniform class definitions must be maintained across dataset versions, and metadata must track exactly how datasets are split into training, validation, and testing. Annotation standards and quality metrics should be documented to avoid drift across labeling cycles. Beyond labels, feature management provides opportunities for optimization. Pre-computing embeddings allows for similarity checks, duplicate detection, and even semantic dataset search. Implementing feature stores ensures embeddings can be reused across models or experiments, accelerating iteration. Caching processed data further reduces training startup times, removing repetitive pre-processing overhead. This page underscores that as datasets grow, label and feature management become central infrastructure challenges. Without discipline here, projects quickly spiral into inconsistency and confusion. Training is where pipelines begin to feel like machine learning proper, but even here, infrastructure choices are decisive. Transfer learning has become standard. Pre-trained convolutional networks or vision transformers provide strong foundations, cutting down data requirements and training time. Optimization techniques like automated mixed precision AMP balance memory savings with speed gains, enabling larger models to train on the same hardware. Distributed training frameworks, such as DDP or FSDP, extend this further, allowing training across many GPUs to tackle bigger datasets and models. Logging closes the loop, with platforms like MLflow, weights and biases, or ClearML tracking metrics, artifacts, and hyperparameters. These tools transform training from a one-off experiment into a reproducible, collaborative process. This section makes clear modern CV training is as much about orchestration and optimization as it is about model design. No model should be trusted without continuous validation and monitoring. Performance metrics, accuracy, precision, recall, mean average precision must be tracked across different classes and conditions. It's not enough to know a model performs well on average. It must perform consistently across all segments of data. Data drift detection is critical in production, where lighting, environments, or even the objects themselves may change over time. Failure analysis provides a feedback loop, categorizing errors and visualizing where models go wrong so improvements can be targeted. Finally, alert systems automate monitoring, notifying teams when performance dips below thresholds. This page emphasizes that validation is not just a checkpoint at the end of training. It is an ongoing process that continues long after deployment. At scale, manual orchestration is impossible. This section introduces the automation tools that tie pipelines together. Kubeflow pipelines bring Kubernetes native orchestration, containerizing preprocessing, training, and deployment steps into manageable workflows. Airflow and Prefect offer flexible scheduling and dependency management. ensuring pre-processing tasks trigger training jobs seamlessly. MLflow provides experiment tracking, artifact storage, and a model registry for reproducibility. Weights and biases offers comprehensive logging, hyperparameter sweeps, and collaborative dashboards for teams. These tools turn complex, fragile workflows into robust, repeatable processes. In short, automation is the glue that enables reproducibility and scalability in modern computer vision systems. The best practices page distills lessons from experience. Version everything. Datasets and models should be versioned together, with augmentation reproducible via fixed random seeds and experiment configurations stored in code. Measure what matters. Throughput in images per second per GPU, GPU memory usage, and bottlenecks provide better insight than just accuracy. And most importantly, optimize for deployment conditions. Edge devices have constraints vastly different from cloud servers: smaller memory, lower compute power, and limited bandwidth. Training pipelines must reflect these realities, preparing models that are not only accurate, but also deployable in target environments. Best practices emphasize discipline, documentation, and foresight, ensuring pipelines scale smoothly from research prototypes to production systems. The final section ties everything together. End-to-end integration is essential. Computer vision pipelines must connect data preparation, augmentation, training, and validation into cohesive workflows. Reproducibility is non-negotiable, with orchestration tools ensuring complex workflows can be repeated reliably. Augmentation strategies and transfer learning accelerate development, reducing time to value in resource costs. Continuous monitoring ensures production reliability as real-world data evolves. The message is clear. Building vision systems is not just about algorithms, but about disciplined infrastructure. Teams that master these practices move faster, scale further, and deliver systems that consistently perform. The takeaway is simple but profound. The future of computer vision will be shaped not only by model architectures, but by the pipelines that make them practical, reliable, and scalable. The story of computer vision at scale is ultimately a story of balance. This introduction frames the central tension. Bigger models tend to perform better, but they are slower, more expensive, and less deployable. Smaller models are faster and lighter, but often underfit, failing to capture the complexity of real-world visual recognition tasks. The challenge for engineers and researchers is to navigate this spectrum, selecting architectures that meet both accuracy needs and operational constraints. EfficientNet was developed to address precisely this issue. By offering principled scaling strategies, it enables practitioners to find better trade-offs between accuracy, latency, and compute. The introduction reminds us that model design is not just about chasing benchmarks. It is about fitting models to real-world contexts, from constrained edge devices to powerful cloud platforms. Scaling matters because it touches every layer of deployment. Larger models yield higher accuracy, but demand significantly more compute, memory, and time. Inference latency rises, GPU usage spikes, and energy consumption grows. Smaller models, by contrast, are efficient but risk losing nuance in complex tasks such as fine-grained object detection or scene understanding. These trade-offs become even more pressing in diverse deployment scenarios. A self-driving car cannot tolerate lag, no matter how accurate the model. Edge devices must operate within tight power budgets. Cloud services must balance throughput against cost. This section highlights that scaling decisions are not purely technical. They are strategic. Every deployment context demands careful evaluation of the balance between accuracy and efficiency, making scaling a cornerstone of production computer vision. Traditional scaling methods were crude, often increasing only depth or width, leading to diminishing returns. EfficientNet introduced a compound scaling approach that balances three dimensions simultaneously: depth, width, and resolution. Depth allows the model to capture more complex hierarchical features. Width enables richer feature maps by adding channels. Resolution improves sensitivity to fine details in input images. The innovation of EfficientNet was to tie these dimensions together with a compound coefficient, ensuring balanced growth. Instead of trial and error scaling, practitioners now had a principled way to design models that offered stronger accuracy efficiency trade offs. This systematic approach gave EfficientNet a significant advantage over predecessors like ResNet and DenseNet, especially when accuracy and efficiency had to coexist in the same deployment. EfficientNet is not a single model, but a family designed for different scales. B0 is the baseline, with just 5.3 million parameters, making it ideal for mobile or edge deployments. B1 through B3 represent mid-range models, balancing performance and resource usage for mainstream production tasks. B4 through B7 scale up to as many as 66 million parameters, offering maximum accuracy but requiring significant compute and memory. The second generation, EfficientNet V2, added further improvements, faster convergence, stronger regularization, and improved performance on modern hardware. Together, this family provides a toolkit for practitioners to select the right model for the right job. Whether the goal is minimal latency, balanced performance, or state-of-the-art accuracy, there is an EfficientNet variant designed to fit. This page highlights the real-world costs of scaling. Moving from B0 to B3 may deliver stronger accuracy, but typically causes a 2 to 5 times increase in latency. Memory usage grows even more steeply, with GPU RAM requirements jumping 10 to 15 times between B0 and B7 when training on high-resolution inputs. Accuracy gains diminish at the higher end. Scaling from B5 to B7 may deliver only a 2% improvement. Despite quadrupling parameter counts, energy usage follows a similar pattern, with power consumption rising nearly eightfold from baseline to largest model. These figures underscore a crucial point. Scaling delivers improvements, but at exponential cost. Engineers must evaluate whether the marginal accuracy gains justify the increases in latency, memory, and energy, particularly in production scenarios, where efficiency matters as much as raw accuracy. EfficientNet's flexibility shines in deployment. On edge devices, variants like EfficientNet Lite or quantized models such as Int8 versions are best, optimized for low-power chips with limited throughput. In real-time video analytics, models like B0 through B2 balance accuracy with frame rate requirements, maintaining 15 to 30 frames per second. For cloud inference, mid-range models like B3 through B5 are ideal, leveraging GPU acceleration and request batching for maximum throughput. At the high end, research applications prioritize state-of-the-art accuracy above efficiency, using B6 or B7 even at significant compute cost. These deployment contexts illustrate the importance of matching model choice to workload. A one-size-fits-all approach fails. Instead, scaling must be contextual, aligning resources, latency, and accuracy to the environment. The landscape does not end with EfficientNet. New scaling paradigms are reshaping computer vision. Vision transformers, VITs, replace convolutions with patch embeddings and self-attention, offering improved performance for large-scale training. Neural architecture search, NAS, automates architecture discovery, producing designs optimized for specific hardware targets. Mixture of experts, MOE, models, activate only relevant parts of the network per input, drastically improving efficiency for certain tasks. Finally, ConvNext and RegNet modernize convolutional networks with transformer-inspired innovations, applying systematic scaling rules. These emerging paradigms suggest that while EfficientNet remains highly relevant, the future of scaling will involve diverse approaches, each tuned to different tasks, hardware, and performance requirements. Scaling is not just about selecting a model, it's about how you implement it. Best practices begin with establishing a baseline using B0 to B3 models, giving you reference accuracy metrics for your dataset. From there, profile key metrics directly on your target hardware. Latency, memory usage, and power consumption often vary in practice. Next, apply optimizations like mixed precision training, pruning, and quantization to improve efficiency without major accuracy loss. Finally, always match model scale to workload. A real-time analytics system on mobile hardware cannot afford B7, while a cloud-based research task may demand it. The principle here is discipline. Use empirical profiling and careful matching to select the optimal model, rather than assuming bigger is better. First, principal scaling matters. Efficient Net's compound scaling approach provides a systematic method to balance depth, width, and resolution for optimal efficiency. Second, context determines optimal scale. The right model is always situational, depending on hardware, latency requirements, and accuracy goals. Third, deployment optimization is critical. Techniques like quantization, pruning, and distillation bridge the gap between research performance and production feasibility. The call to action is clear. Benchmark different efficient net variants against your own tasks and target hardware. Then identify the true optimal operating point. The future of computer vision is not about the biggest models alone. It is about models that deliver the right balance of accuracy, latency, and efficiency for their intended environments. This introduction sets the stage by reminding us of a key truth. Real-time video inference is not just a technical curiosity, it is the backbone of modern, time-sensitive applications. From autonomous driving to security surveillance, from robotics to augmented reality, systems must process streams at 30 to 60 frames per second, and each frame must be analyzed in under 100 milliseconds. The stakes are high. A delay in detecting a pedestrian could cause an accident. A lag in identifying suspicious behavior might compromise safety. Delivering predictions at this speed requires carefully architected pipelines that encompass every stage: video ingestion, decoding, pre-processing, inference, and post-processing. This opening frames the journey ahead, a deep dive into the performance challenges, infrastructure optimizations, scaling architectures, and monitoring strategies that make real-time video inference feasible in production environments. The second page explains why these constraints are so demanding. Stream density is the first challenge. Each camera can generate 30 to 60 frames every second, and scaling to dozens or hundreds of cameras creates massive computational loads. Next comes the latency budget. Mission-critical applications, from cars on the road to drones in the air, require responses within 100 milliseconds per frame. Anything slower risks rendering the system useless. Finally, the pipeline complexity itself is non-trivial. Data must flow through decoding, pre-processing, inference, and post-processing seamlessly. Each step introduces potential bottlenecks. This section emphasizes a critical point. In real-time AI, performance is not just about accuracy. It is about timeliness. Even a perfect model is worthless if it arrives too late. Here we see the canonical pipeline broken down into 5 stages. First is capture, ingesting streams from cameras, RTSP feeds, or stored sources. Second is decode, where GPUs handle video decompression through NVDEC or VA API, offloading CPUs from overwhelming tasks. Third comes pre-processing, resizing, normalizing, and cropping regions of interest to prepare frames for efficient inference. Fourth is inference itself, where convolutional networks or transformers execute predictions on GPUs or edge hardware, often with precision optimization to save time. Finally, post-processing extracts meaning, applying non-maximum suppression, tracking algorithms, or metadata generation from raw outputs. Each stage builds upon the last, and the efficiency of the whole system depends on careful optimization across all 5. This structured pipeline turns raw video into actionable insights within milliseconds. This section outlines the major bottlenecks in achieving low latency performance. GPU saturation is a constant risk, as continuous inference imposes sustained load, demanding careful scheduling and resource allocation. Bandwidth constraints appear when multiple HD or 4K streams overwhelm memory buses or network interfaces. Multi-camera synchronization adds another layer of complexity, as distributed sensors must align in time for coherent analysis. And finally, there are the accuracy versus speed trade-offs. Models must strike a balance between being powerful enough to detect subtle features and efficient enough to run in real time. This page makes one point abundantly clear. Building low latency video inference systems is not simply about raw power. It's about eliminating bottlenecks, managing resources, and making trade offs that ensure both reliability and speed. Fortunately, there are powerful levers available to improve performance. Frame batching aggregates frames across multiple streams, amortizing kernel launches and exploiting GPU parallelism, yielding 2 to 5 times throughput improvements. Pipeline parallelism uses CUDA streams to overlap decode, preprocessing, and inference, minimizing idle time by ensuring different stages run concurrently. Inference optimization leverages frameworks like TensorRT or OnX runtime, applying quantization, kernel fusion, and layer optimization to achieve 3 to 4 times speedups. Finally, edge preprocessing filters redundant or low-value frames at the edge, reducing bandwidth and downstream workload. Together, these techniques form the playbook for building efficient systems. They exploit parallelism, reduce redundancy, and optimize inference kernels to push hardware to its limits without sacrificing latency. Once pipelines are optimized, the challenge shifts to scaling deployments. The document describes 3 deployment models. Single GPU edge systems, like NVIDIA Jetson or Intel NUC devices, enable localized, low-latency inference where connectivity or latency demands prevent cloud reliance. Multi-stream servers pack high-density GPUs in data centers, handling dozens of streams concurrently and delivering centralized scalability. Finally, hybrid edge cloud architectures combine the two. Lightweight detection runs at the edge, while heavier, more complex analysis occurs in the cloud. Reliable event distribution is enabled through message brokers such as Kafka or MQTT, ensuring scalability and resilience. This layered approach ensures that video inference systems can scale flexibly, balancing cost, latency, and analytical depth depending on the use case. Building real-time systems is one thing, keeping them reliable is another. Monitoring begins with performance metrics, including frames per second, end-to-end latency, GPU utilization, and queue depths. Health monitoring extends to stream connectivity checks, frame drop detection, heartbeat verification, and model serving status. Finally, resiliency features are critical. Node-to-node failover ensures continuity, stream reconnection logic minimizes downtime, and redundancy prevents single points of failure. Graceful degradation allows systems to scale down intelligently rather than collapse under stress. Dashboards powered by Prometheus and Grafana provide real-time observability with alerts tuned for anomalies or threshold breaches. This section drives home that monitoring is not optional. It is the foundation of reliable, always-on inference systems. The power of real-time video inference comes to life through use cases. In smart cities, vehicle and pedestrian detection across traffic cameras enables safety systems and traffic optimization with responses under 100 milliseconds. In retail analytics, real-time shopper tracking and shelf monitoring prevent stockouts and optimize layouts. Industrial safety applications include PPE detection and hazard alerts, with instant notifications reducing workplace accidents. And in sports analytics, real-time event detection powers instant replays and coaching insights, transforming fan engagement and athlete performance. These examples reveal the breadth of impact, from safety-critical environments to consumer experiences. Real-time inference is reshaping industries across the board. The final section distills everything into clear lessons. First, performance is critical. Both high throughput and low latency are required to handle multiple video streams at frame rate. Second, end-to-end optimization is essential. Every stage, from capture to post-processing, must be tuned to prevent bottlenecks. Third, leverage accelerators. Tools like TensorRT, Triton Inference Server, and DeepStream maximize efficiency. Finally, hybrid deployments balance edge and cloud intelligently, optimizing for latency, scalability, and cost. The conclusion is clear. Real-time video inference is not simply about running a model on video data. It is about architecting robust, scalable, and optimized pipelines that deliver actionable predictions within milliseconds. The organizations that master this discipline will set the standard for AI-powered vision systems in the years ahead. Let's talk about DeepStream, NVIDIA's complete solution for building scalable, production-ready video analytics systems. It frames DeepStream not merely as an SDK, but as a comprehensive platform designed to turn raw camera streams into actionable insights with remarkable efficiency. Built for developers, researchers, and system architects, it provides every building block needed to manage end-to-end pipelines. DeepStream specializes in real-time, multi-stream video understanding, ensuring minimal latency even under heavy workloads. It is also cross-platform, running seamlessly across NVIDIA Jetson devices, discrete GPUs, and distributed edge-to-cloud deployments. At its core, DeepStream leverages GStreamer, the open-source modular pipeline framework, giving developers the flexibility to build and customize video workflows. This introduction sets the stage. DeepStream is not just an optimization. It is a turnkey foundation for anyone seeking to build high-performance, scalable video AI solutions. On this page, we dive deeper into the essence of DeepStream. It's NVIDIA's SDK purpose-built for video understanding at scale. Unlike generic AI frameworks, DeepStream addresses the unique challenges of real-time video, decoding multiple streams simultaneously, minimizing end-to-end latency, and scaling from tiny Jetson devices to massive data center clusters. With its GStreamer backbone, it offers modularity and extensibility, allowing developers to plug in decoders, inference engines, trackers, and publishers as needed. Importantly, DeepStream is designed for multi-stream efficiency, capable of processing dozens or even hundreds of live feeds with optimized performance. This page emphasizes that DeepStream is not a tool for experimentation alone. It is engineered for deployment in the real world across diverse domains like smart cities, healthcare, retail, and industry. This section highlights why DeepStream stands out. Unlike ad hoc solutions that require stitching together multiple frameworks, DeepStream provides a complete end-to-end pipeline. It begins with hardware-accelerated decode, enabling efficient ingestion of multiple video feeds. Next comes pre-processing, where frames are normalized and transformed for consistency. The inference stage leverages TensorRT-optimized models, ensuring lightning-fast predictions. After inference, post-processing extracts bounding boxes, object metadata, or classification results. Finally, outputs can be displayed, streamed, or published as metadata to external systems. Scalability is central. The same APIs and workflows scale smoothly from a Jetson Nano at the edge to A100 GPUs in the data center. This page reminds us of a critical truth. DeepStream reduces complexity, enabling developers to focus on applications rather than reinventing pipelines. Here we encounter the building blocks that make DeepStream powerful. The NFIN for plugin handles inference, supporting TensorRT and ONNX formats, configurable batch sizes, and built-in modes for detectors and classifiers. The NFIN Tracker plugin enables multi-object tracking, maintaining identities across frames with algorithms like sort and deep sort, essential for trajectory analysis. The NFIN Video Convert module provides GPU-accelerated transformations, handling format conversion, scaling, and overlays with minimal latency. And the message broker integrates DeepStream with external systems, publishing metadata to Kafka, MQTT, or REST endpoints with customizable schemas. These core components show why DeepStream is considered a production-ready SDK. It combines efficiency with flexibility, offering a toolbox of highly optimized, interoperable modules. DeepStream's versatility shines in its real-world applications. In smart cities, it powers traffic optimization, congestion prediction, license plate recognition, and pedestrian safety systems. In retail analytics, it enables customer journey mapping, real-time inventory tracking, queue management, and staffing optimization. In healthcare, It tracks patient movement, detects falls, monitors occupancy, and enforces hygiene compliance. And in industrial environments, it enforces PPE compliance, monitors safety zones, and detects defects on assembly lines. Each example underscores the same truth. DeepStream is not abstract. It is powering practical, mission-critical applications across industries. Its ability to analyze multiple streams in real time makes it a cornerstone of next-generation infrastructure. This cage explores how DeepStream adapts to different environments. Jetson Edge deployments enable compact, self-contained inference for factories, hospitals, and retail stores, where low latency and on-device processing are critical. Multi-stream servers aggregate dozens or hundreds of feeds in centralized deployments, ideal for smart city command centers. Cloud-hosted analytics leverage Kubernetes orchestration to scale dynamically, supporting fluctuating workloads with elastic infrastructure. Finally, hybrid edge cloud architectures split workloads intelligently. Lightweight inference occurs at the edge for real-time responsiveness, while heavier analysis and archival storage are handled in the cloud. These scenarios reveal DeepStream's flexibility. The same SDK adapts across edge, data center, and cloud, ensuring consistent development and deployment experiences. DeepStream does not operate in isolation. It integrates seamlessly with industry-standard tools. Triton Inference Server manages flexible model deployment and versioning, ensuring production reliability. Event streaming platforms like Kafka, RabbitMQ, and MQTT handle real-time metadata distribution. Data storage systems like PostgreSQL, Elasticsearch, or Redis enable efficient query, indexing, and analytics. For observability, Grafana and Prometheus track system performance, latency, and throughput, giving operators real-time insights into pipeline health. This ecosystem integration is what makes DeepStream enterprise-ready. It ensures that developers can plug video analytics pipelines directly into broader IT infrastructures, from monitoring dashboards to storage backends, without reinventing the wheel. To maximize DeepStream's value, best practices are essential. First, profile pipeline performance. Measure frames per second and latency at each stage using NVIDIA profiling tools to identify bottlenecks. Second, optimize models with TensorRT, achieving 2 to 5 times throughput improvements with INT8 quantization, boosting efficiency on edge devices. Third, balance GPU workloads by monitoring decode and inference distribution, dedicating specific GPUs for heady functions where necessary. Fourth, implement batching strategies, especially cross-stream batching, to fully utilize GPU capacity. Tools like Nsight Systems provide visibility into GPU utilization patterns, guiding configuration. These practices transform DeepStream pipelines from functional prototypes into production-optimized systems, squeezing the maximum performance out of available hardware. DeepStream is a turnkey SDK, offering a complete solution for building real-time video analytics with minimal custom code. Its scalable architecture works consistently from Jetson Edge devices to multi-GPU data centers, offering developers a unified experience. Its rich ecosystem accelerates integration with external systems, from inference serving to data storage. And above all, it is an industry enabler, already powering applications in smart cities, retail, healthcare, and industrial safety. The message is clear. DeepStream transforms video data into actionable intelligence at scale. For developers and organizations looking to deploy real-time video AI, DeepStream is not just a toolkit. It is the backbone of production-ready computer vision. Modern video processing challenges are too big for any single layer of infrastructure to handle alone. Raw video streams from cameras and IoT devices generate staggering data volumes, straining networks, and overwhelming traditional architectures. Sending all this raw data directly to the cloud is costly, slow, and often impractical. At the same time, relying solely on edge devices limits the sophistication of analysis. This introduction presents the solution, a distributed edge-to-cloud framework that balances the unique strengths of each layer. The edge delivers real-time processing and privacy protection, while the cloud provides scalability, storage, and advanced analytics. The message here is clear. The future of video AI is hybrid. Engineers must think not in terms of edge versus cloud, but edge and cloud, working together to build resilient, intelligent, and cost-effective systems. This section explains why edge to cloud has become the standard paradigm. First, video scale is overwhelming. A single 4K camera generates gigabytes of data per hour, and multiplying this by thousands of devices produces a flood of information that cannot be shipped upstream in raw form. Second, latency matters. Many use cases, from autonomous vehicles to security systems, require sub-second responses that cloud-only pipelines cannot guarantee. Third, bandwidth is expensive. Transmitting terabytes of raw frames consumes enormous bandwidth, driving up costs and straining infrastructure. Edge processing solves these issues by filtering, compressing, and analyzing locally, while still sending key events or summaries to the cloud. The cloud then provides aggregation, advanced correlation, and long-term retention. This dual approach optimizes for both immediacy and intelligence, making it the only feasible architecture for modern video applications. At the edge, intelligence begins. Real-time inference enables object detection, tracking, and classification directly on constrained devices like Jetsons or IoT gateways, often achieving sub-100 millisecond responses. Pre-filtering ensures that only high-value information, such as anomalies, events, or metadata, is transmitted upstream, reducing bandwidth used by 90 to 95%. On-device caching adds resilience, buffering video during network outages so that operations continue uninterrupted even under connectivity issues. Finally, privacy filters blur or mask personally identifiable information such as faces or license plates before upload, ensuring compliance with privacy regulations right at the point of capture. This section underscores that the edge is not just about compute offload, it's about immediacy, resilience, and trust, all of which are critical in real-world deployments. If the edge delivers speed, the cloud delivers scale. Heavy compute workloads, such as running large computer vision or language models that exceed edge hardware, are handled in the cloud, providing depth of analysis without local constraints. Cross-carrier correlation aggregates events across multiple sources, identifying objects or patterns that span different physical locations. Long-term storage and replay allow video to be archived efficiently, with intelligent indexing enabling rapid retrieval during audits or investigations. Finally, the cloud supports system integration, connecting insights to BI dashboards, alerting platforms, and enterprise applications through standardized APIs. This section highlights the cloud's role as the layer of intelligence at scale, complementing the edge by performing the heavy lifting that requires vast compute, aggregation, and enterprise connectivity. The architecture of edge-to-cloud video systems follows a clear flow. Capture begins at the edge, where devices like Jetsons or IoT gateways ingest raw streams from cameras. Pre-processing and inference then extract metadata and select regions of interest using lightweight local models. Next comes transport, with Kafka, MQTT, or REST protocols streaming events upstream efficiently. Finally, the cloud layer performs advanced analytics, aggregates results, and powers dashboards for visualization and decision-making. This event-driven architecture optimizes bandwidth by transmitting only the most critical data while maintaining end-to-end intelligence. This section emphasizes that such designs are not linear, but cyclical. Local inference influences cloud analytics, and cloud insights feed back into edge operations, creating a continuous feedback loop of intelligence. Scaling edge-to-cloud video processing is not without obstacles. Bandwidth bottlenecks loom large. 4K multi-camera setups can generate more than 100 gigabytes per hour, overwhelming networks. Synchronization issues arise when multiple edge devices must maintain temporal consistency for accurate correlation across streams. Edge model accuracy is another hurdle. Constrained devices cannot always run the most powerful models, creating trade-offs between speed and precision. Finally, cloud costs can spiral quickly as storage, egress, and compute expenses balloon at scale. These challenges illustrate that while edge to cloud is powerful, it requires careful engineering to balance resources, accuracy, and cost. Without deliberate optimization, even the best designed systems will falter under real world pressure. This page lays out the strategies for overcoming performance and cost challenges. Intelligent compression reduces bit rate by downsampling frames while preserving details in regions of interest. Event-driven transmission sends anomalies or metadata rather than continuous streams, cutting bandwidth use by up to 95%. Model cascading deploys smaller edge models for fast detection, with cloud-based models verifying results to balance speed and accuracy. Distribution optimization uses CDNs and regional cloud zones to minimize latency and ensure compliance with data sovereignty laws. Together, these strategies create a finely tuned system where every stage, from edge preprocessing to cloud analysis, is optimized for performance and efficiency. The message is clear. Optimization is not a single tweak, but an end-to-end discipline. The power of edge to cloud comes alive in real-world applications. In smart factories, edge systems detect defects in under 100 milliseconds, while the cloud aggregates data for predictive maintenance and process optimization. In retail analytics, the edge counts customers for immediate staffing decisions, while the cloud analyzes long-term trends across locations. In transportation, vehicles are detected at the edge for real-time signal control, while the cloud forecasts congestion and supports infrastructure planning. And in security, edge devices generate instant alerts, while the cloud enables video replay, investigation, and cross-camera tracking. These scenarios illustrate the hybrid model's versatility. The edge delivers immediacy, while the cloud provides context and depth. This section distills practical lessons. First, adopt an event-driven architecture rather than a frame-driven one, drastically cutting bandwidth needs. Threshold-based triggers and metadata-first design are essential here. Second, prioritize edge privacy protection, blurring faces or masking license plates before transmission to reduce liability and regulatory risk. Third, implement performance monitoring with dashboards and automated alerts to track bandwidth, GPU utilization, and latency, ensuring bottlenecks are addressed proactively. Finally, embrace hybrid deployment with cloud autoscaling, load balancing, and graceful degradation to handle variable workloads while maintaining consistent edge performance. These practices turn theoretical frameworks into resilient production systems. The edge handles speed, delivering real-time responses, bandwidth efficiency, privacy protection, and resilience during disruptions. The cloud handles scale, performing heavy compute, aggregating across sources, providing long-term storage, and integrating with enterprise systems. The synergy between the two creates a robust, intelligent, and cost-effective infrastructure for video AI. The message is clear. Success lies not in choosing between edge and cloud, but in orchestrating both effectively. This hybrid model is the future of video processing, balancing latency, bandwidth, and intelligence to power the next generation of AI-driven applications.